A very good morning to one and all. On behalf of organizing committee, I welcome you all to the second day sessions. We will start with the first invited lecture by Professor KNVB Varaprasad Garu. And I request Professor KKM Sharma Garu to please chair the session.
Good morning, all of you. Good morning. My scholar is coming to you. Professor Koti NVV Varaprasad, Department of Mathematics, Guru Ghasidas Vishwavidyalaya, Bilaspur. He is going to present his talk on some results on weak contraction conditions. He did his PhD from the University of Andhra University. He did MSc, MPhil and PhD. His area of research interest is fixed point theory and applications. He has more than 10 paper publications. He under his supervision, one PhD is awarded. He has 25 plus years of experience teaching. He has several responsibilities as an administration. Now I request Professor Varaprasad to continue his talk, deliver his talk. Thank you.
Good morning, respected Professor. First of all, I would like to give a thanks to my Guru, Dr. C.V.R. Bhaskar. Because of his guidance, I completed my PhD in this university. It's a great opportunity. Great opportunity to me for giving a talk in this department, home department, and also I'm very grateful to you and Professor KPR Sastra Garu and Head of the Department Anuradha Kameswar Garu, Nananji Garu, KKM Garu, PDN Srinivasa Garu, Rajashekar Garu, and C.S. Srinivasa Garu. So my name is actually I completed my PhD here in 2008, awarded here. On the topic of fixed point applications. After that, I joined in Guru Ghasidas Vishwavidyalaya as assistant professor in 2012. From that 2012 onwards, I am working there. Now, actually, today our topic is actually that is discontinued fixed point. But unfortunately, my colleague is also giving the same title. Therefore, I changed the title and then given suddenly. Yesterday, I know only. The company is also giving the same topic, discontinuity at a fixed point actually. So that I changed the topic with some results on weak contraction conditions. Just 4 days back, this talk, this content is published in ICPAEMS Press. So today's my talk title is that some results on weak contraction condition. So, first of all, I would like to give you basic concepts first. We know that the Vargas theorem. Next. So I would like to stand there and read the talk.
Varaprasad, half an hour time.
Sure, sir. Sure, sir.
5 minutes before.
Maximum I will try to. First of all, I would like to First is the basic facts we'd like to give before going to enter my talk. And time is 9:33, 9:30, 10 o'clock before I try to come. So this is the Banach experiment in 1922. Banach is proved the very important result known as the Banach contraction principle, in which it states that every self-map K defined in a complete matrix plus XD, they have to X dy less than equal to alpha times of the of XY for all X, Y, and X, and alpha is lies between closer to the semi interval 0 to 1. And then after that, several generalizations have happened here due to the space lines and contraction lines also. So recently in 2001, recently 2012, Wardowski generalized Banach contraction principle and he proposed one new type of contraction, that is F contraction, that is a mapping from F is the R plus to R satisfying the following conditions. One is that F is strictly increasing and for each sequence I alpha n of positive numbers, alpha n tends to 0 if and only if limit of F of alpha n equal to minus infinity. And third condition is there is just k in 0 1 such that alpha for k f of alpha is equal to 0. That capital we are I'm going to use the capital F is the set of all functions satisfying the both the equations, and mapping T is a self map on x to x is said to be F contraction if there is just tau is greater than 0 such that for all x1 x, and whenever d of dx dy is positive, then we are going to be taking tau plus f of d of dx dy less than equal to f times of f of x1, and it is published in fixed point in 2012. And these are supporting examples on F contraction. And later on 2014 also Wardowski and Randu is also established one of the contractions by introducing the V contraction condition. That is XB definition of that one is that XB a metric space and EB a self-map on X is said to be an FV contraction on XD. If there is just a capital F, it belongs to family of capital F and the tau is positive such that for all X, Y, and X satisfying d of dx dy greater than 0, and the condition is following condition of the mapping is like this tau plus f of dx dy less than equal to capital F of maximum of d of xy x dx and d of y dy half times of d of x dy plus y dx. And I'm used in this paper some hypothesis here. I mentioned in the comprehensive type. That is the let dbs self-map on x and the alpha is x cross x tends to r plus b a function. Then t is said to be alpha admissible. That is alpha of xy is greater than equal to 1 implies that alpha of dx dy is greater than equal to 1. And second one is that triangular alpha admissible. That is, if t is alpha admissible, satisfying this condition, alpha of xy greater than equal to 1, alpha of yz greater than equal to 1, implies that alpha of xz greater than equal to 1, and xyz belongs to x. And third is that alpha arbitrarily admissible. If alpha of x dx greater than equal to 1, implies alpha of dx is square x greater than equal to 1. And the fourth one is that triangular alpha arbitrable admissible. If T is alpha arbitrable admissible and alpha of xy greater than equal to 1 and alpha of yty greater than equal to 1 implies that alpha of xty greater than equal to 1. And here of that I am giving you some remark that means of implications about definitions. Each alpha admissible is mapping is an alpha arbitrarily admissible. Similarly, triangular alpha admissible is triangular alpha orbital admissible. And the conversation not happens here. So I provided an examples here. That is this example. And after that, in 2014, Wardowski and Dung is generalized the condition. After that, Gopal and Abbas is introduced the new contractor condition, that is the alpha type F contraction on X. That is let X to be a metric space and T be a self map on X. Then T is said to be alpha type F contraction on X. If tau plus alpha of xy, f of d of dx dy less than equal to f of d of xy. And the second is that alpha type fv contraction on X. If that T satisfies tau plus alpha of xy, f of d of dx dy less than equal to f times of maximum of xy xdx yty half times xdy plus ytx for all xy and x satisfying when d of dx dy is greater than 0 and function f is belongs to family of capital F and tau is positive and alpha is x cross x tends to and actually my paper is a space. I'm also taking the spaces in B metric space. So therefore I would like to first of all that is the metric the B metric space definition also I would like to present here. That is Kristevik in 1993. He introduced the B metric space definition. That is let X be a non-empty set and S is greater than or equal to 1 be given real number and the function T is x plus x tends to R plus is a called B metric. If it is satisfying the following conditions b1, b2, b3, and b3 is a s times of d of xy plus y d of yz. And if you are taking s is equal to 1, then it is reduced to the metric space. And this triplet xds is called a B metric space. Its quotient s. And I'm using this definitions also. That is the altering distance function. Kahn and Swale and Sessa, 1984. They introduced it as an altering distance function. A function size mapping from r plus to r plus is said to be altering distance function if it is satisfied with the following conditions: f is continuous and non-decreasing, and psi of t equal to 0 and t equal to 0. And after that, in 2017, Swangsu is introduced the weak altering distance function. So they introduced this function. A function is a size mapping from r plus to r plus is said to be weak altering distance function and has two conditions. Only the reduced that is Si is a lower semi-continuous. The rest of the all is taken from the altering distance function. So in my paper, I'm taking the two inequalities. That is, I introduced these two. That is generalized nonlinear alpha f v contraction type 1, and that is tau of d of xy plus alpha times of d of x alpha of xy f of d of dx dy less than equal to capital F of m of xy. And second is that generalized nonlinear alpha f v contraction type 2. And if alpha of d of xy plus alpha of f times of alpha of xy, d of xy dx dy less than equal to f of m of xy, and m of xy is mentioned in the last line, that is this one. And here it is 7 and 8. These two both are independent inequalities. I provided an examples. This one, this is the condition. One is holds and second condition is not hold. This example is type 2 is holds and type 1 is not holds. So because these two examples, I can say that these two are independent inequalities. So now I presented this theorem including of main results, that is the TBA continuous generalized nonlinear alpha f v contraction type 1 and with capital X belongs to capital F, then D has a fixed point in X if the following conditions are followed. First one, I'm taking the T is a triangular alpha orbitally admissible, and second is that there is an x one x such that alpha of x1 tx1 greater than equal to 1, limit infimum x tends to t plus tau of x positive for all x positive. And I'm taking that may impose that continuity of f also be replacing of t. Developed in second term, that is the theorem. Let t be a generalized nonlinear alpha f v contraction type 1 with the capital F is belongs to capital F family of f and f is continuous. The ninth theorem F is not continuous, and the second theorem is F is continuous. Then T has a fixed point in X. Then the following conditions are found, and T is a triangular alpha indivisible, and there is x1 and x in the such that alpha of x1 tx1 greater than or equal to 1. And third condition that if x1 sequence x1 is xn is a sequence in x such that alpha of xn plus 1 greater than or equal to 1 for all n in n, and xn tends to x as n tends to infinity, then alpha of xn x greater than or equal to 1. And the fourth condition is as it is from the ninth. So now I am introducing this one also, that is strictly triangular alpha arbitrarily admissible. So that is let T be a self map on X, alpha and X, alpha of X plus X tends to R plus be given function such that alpha of X Tx greater than 1, alpha of Tx T square greater than 1. Alpha of xy greater than 1 and alpha of yty greater than 1 implies alpha of xty greater than 1. If T satisfies 1 and 2 conditions in arbitrarily admissible conditions, then we can say that that is strictly triangular alpha arbitrarily admissible. And now, with using of this definition, I developed this theorem, that is TPA continuous generalized nonlinear alpha f weak contraction type 2 satisfying with the F1. F1 then T has a fixed point in X if the following conditions are found. And the first one is the above definition level, and second is that there is X1 in X such that alpha of X1 Tx1 greater than 1. And with using a same definition, I mean type 2, also I am developed the fixed point. Using that strictly triangular alpha arbitrary admissible, I used it with the alpha f weak contraction type 2 also. Same conditions with using of second inequality, non-linear generalized non-linear alpha f weak contraction of type 2 satisfying with the F1, then T has a fixed point in X. The following conditions are found. One is that T is a strictly triangular alpha arbitrarily admissible, and the second is that there is a x1 and x is that alpha of x1 tx1 greater than 1. Third, if xn is a sequence in x is that alpha of xn plus 1 greater than 1 for all n belongs to capital N. Thus, the limit n tends into xn equal to x, then alpha of xn x greater than 1 for all n in n. And fourth condition is that limit n tends limit infimum x tends to t plus tau of x equals 2 for all x greater than equal to 0. Now, next theorem. Let T be a self maps on x such that for all x1 x, Tx d of Tx dy equals to tau plus f of d of Tx dy greater less than equal to m of xy, where tau is positive and f belongs to f is a mapping from r plus to r plus with f belongs to capital F. Then T has a unique fixed point in x if either T is or f is continuous. So these are supporting examples here of main theorem of theorem 2. And this is holds my theorem, and this is not holds published papers and Gopal's, Abbas and Patel's papers also not applicable. Therefore, and this is also another example for type 2 second inequality. Now, there is another some results also. In another paper also, I gave this definition: nonlinear alpha type tau f weak contraction condition. If the register function f is a mapping from R plus to R plus satisfying the f1, and another function tau is running from R plus to R plus, thus that for all x, y, and x, d of dx dy positive, then in the condition 11 is going to be taking, that is tau of dx dy, d of xy plus f times of alpha of d of dx dy less than equal to capital F of m of xy, where alpha greater than 1. So this is the second m of xy means this condition. I'm using this definition in B metric space. This is the supporting of my proved, introduced theorem, and this condition is not in tau contraction, and it is not a weak contraction. Now, this is the then let XD be a complete B metric space, and a continuous mapping from T x to x be a nonlinear alpha type tau f weak contraction condition, then T has a fixed point. So, avoiding the continuity condition, we are going to be taking this one, let x be a complete B metric space, and T is running from x cross to x to x. T is mapping from self map on x, be a nonlinear alpha type tau f weak contraction. Then T has a fixed point if the following conditions are followed. F and D are both are continuous, and limit infimum x tends to 0 plus tau of x positive. So the next one is that I'm taking several conditions in this theorem. First condition is S by alpha is S less than alpha, and the second condition is that limit infimum x tends to T plus tau of x is positive. And the second is that x to be a complete metric space, D metric space, T be a mapping from satisfying that tau is positive. For any x y and x, D of x y dx dy is positive. Tau plus f of alpha d of dx dy less than equal to f of m of xy. Alpha is greater than 1, and f is a mapping from R plus to R satisfying the condition f1. Then D has a fixed point in x. Either T is a continuous or f and T are continuous. This is a supporting example. And another paper I introduced that W generalized psi phi weak contractive type conditions are. So that Q be a W distance. This is on a metric space HD, and the two self maps S and T, x to x, two mappings actually. This I'm not to give because it's going to be developing now. Actually, this is the end part. Definition 1920. It is rejected this paper from the one journal due to some lack of the mistakes. Therefore, I would like to skip this these things. These are applications of the rejected papers contents. Recently, Coptron paperism and this one also applications on the Atangana Pelino functional derivative. So recently this contents actually need to delete it. So this is the applications I list to add. I'm also given applications on our theorem on Tangana Balino and the fractional derivatives also. This is completely my talk. Last 33, definition 39 to up to 40, need not to present this one because it was rejected. Need to tolerate. So this is my talks today. Thank you very much, sir. Please open some questions. First one is published, sir. Second, this one is recently it is rejected.
What you say?
Actually, I need not to mention here. No, once it is presented, I would like to say frank. So therefore, and because one, I think so, one VAT lecturer is published that paper, there is a mistake there. I rectified that mistake. Unfortunately, they mentioned a small cause he rejected. So again, also I'm going to be committed
To some other exam.
Ah, yes.
Okay, thanks.
Thank you very much.
Thank you, Dr. Varaprasad. You have presented a nice talk on fixed point, in particular the weak contractive conditions. Any questions from the audience?
First time I heard the person saying that my paper is rejected.
That is your modesty.
Modesty?
Honesty also.
Okay. So, in the absence of questions, I congratulate you. Thank you.
Sir, small talk.
కూర్చోండి మీరు దాన్ని నేను మిమ్మల్ని ఎక్స్పెక్ట్ చేస్తున్నాను తెలుసు సార్ బ్లే కాలేజ్లో నేను చేశాను కదా అప్పటి నుంచి తెలుసు
సార్ రండి రాజశేఖర్
పేపర్లో పడితే బోర్డు అది గౌరవం వచ్చేది.
చెప్పారు. వెరీ హ్యాపీ.
ఉంటా. ఆ పక్క పైన పైన కనిపించాలి పెట్టమ్మా.
హరే కృష్ణ just back sir. How is it?
ఓకే థ్యాంక్ యూ వెరీ మచ్. అప్పుడప్పుడు వస్తూ ఉంటుంది.
ఆయన ఎప్పుడు వస్తారు సార్ ఇప్పుడు బాధ్యత అంతా ఆయనకి అప్పగిస్తాం నెక్స్ట్ విష్ టు ఫెలిసిటేట్ లేదు
ఇంకా సాయంత్రం ఇది చైర్లో ఫార్మాలిటీ ఇచ్చే అయిపోకూడదు.
రండి మన యుఎస్ఎంఎస్ ఓ థ్యాంక్ యూ
ఇన్ని పంచకండితో పట్టుకొచ్చారు. ఎక్కడి నుంచి పట్టుకొచ్చారు? రకరకాలుగా ఉన్నాయి సాగవాలండి. సీఎం ఓకే థ్యాంక్ యూ. నీకెందుకయ్యా బాబు, నువ్వు రిటైర్ అయ్యావు కూడా. యూ వాంట్ టు గో ఫర్దర్ హై.
ఆశీర్వచనాలు ఎప్పుడు ఉండాలి
ఆయన దండం పెట్టడానికి
ఎక్కడ పని చేస్తావా?
అదే
బాగానే ఉంది. నీళ్ళుగా చేస్తావా? ఏ బాగాలేదా?
షెడ్యూల్ ప్రకారమే వెళ్తుంది.
తర్వాత ఎవరు? You want board, no? Huh? Board to tackle kada? Then the note board. So board also. What? Board also? No, no. Board. Only board. Board.
సార్ ఒక్క నిమిషం
సురేష్ రామా.
సురేష్ ఒక్క నిమిషం ఆగండి చెయ్యి ఒకసారి అందులో ఇది ఓపెన్ చెయ్యి మనం రాసుకుంటాం కదా ఒకసారి ఓపెన్ చేయాలి
బోర్డు అరేంజ్ చేశారమ్మా కాదు వై ఇందులో అందులో గూగుల్ లింక్ దీని మీద పెట్టండి ఇప్పుడు మౌస్ తోటి అయిపోతుందండి ఆ మౌస్ సెల్స్ లేక అవ్వలేదు తెప్పించండి
Next talk is by Professor Vishnu Narayan Mishra, and I request Professor L.A. Kameshwari Madam to please chair the session. And I invite Vishnu Narayan Mishra Garu for us.
Sir, please.
Now Vishnu Narayan Mishra, I'll say few things about Vishnu Narayan Mishra sir. And he is well-known Indian mathematician, presently working as a professor and head of the Department of Mathematics at Indira Gandhi National Tribal University, Nagpur, Amarkantak, Madhya Pradesh, India. Prior to this, he has held academic positions as an associate professor, assistant professor, and lecturer in various institutions. He received his PhD degree in mathematics from Indian Institute of Technology, Roorkee in 2007. 2007. His research interests are the areas of pure and applied mathematics, including approximation theory, variational inequality, fixed point theory, operation theory, Fourier approximation, nonlinear analysis, special functions, Q series, and Q polynomials, signal analysis, and image processing, optimization, etc. He is a referee of several international journals of pure and applied mathematics and applied economics. And he is authored more than 400 research publications. And he authored 13 students, PhD scholars. Under his guidance, 13 students were guided. 13 students were awarded. And he delivered many talks in several international conferences, workshops, and many research programs as a resource person. Now, he is a reviewer of many international journals, and moreover, he serves as a Professor Mishra worked globally with many well-known researchers. He has his topics with topics covering very broad spectrum. Much of his work, Mishra, centers around the linear positive operators. He worked on different problems dealing with applications of quantum calculus, converging estimations, rate of approximations in real and complex setting, difference estimates, etc. Now, professor's expertise and dedication to the field of fixed point theory make him available aside to the academic community. Now I request him to give a talk on approximation by sampling Domerian operations in weighted space of functions. Now,
Thank you, Rameshwari Madam, for introducing about me.
so your allotted time is 30.
Okay. So, very much thankful. A very good morning to all of you. Hari Om, Jai Sri Narayan. And I am very much thankful to Professor Srinivas Rao, who gave me the opportunity to interact with you all on this common platform. On this common platform, we enhance our knowledge and share our ideas, our communication, and enhance our teaching as well as research in our programs. And in our Veda, this is the conference which is a common platform on which we can share our ideas, our thoughts among us. In our Veda, there is a slok said that Om Sangachatam Sangvadatam Sangvamanati Janatam Deva Bhaga Pura Sanjanana Upaste. Om Sangachatam Sangvadatam Sangvamanati Janatam Deva Bhag Yatha Purva Sanjanana Upaste. Means let us move together, let us think together, let us work together, let us talk together, working together, thinking together, understanding together, and listening together. So this is the common platform on which we can do like this way. And in our Vedas there is also a slok which is very much famous. That is called Yatha Shikha Mayuranam Nagana Madiyo Yatha Tadvad Vedanga Shakhanam Gardham Murdhan Vartate. Means like Yatha Shikha Mayuranam, in peacock there is crest. Importance of crest is in peacock. And in snakes there is Nagmadi, snake madi, also famous in snakes. Like in this same way, there are different branches of Vedanta. In which the mathematics is the top position, climax position. So, Yatha Shikha Mayuranam Naganam Madiyo Yatha Tadavad Vedanga Shakhanam Vardhan Mordhani Vartate. Mahaviracharya ji also said that what is the benefit to delirium? Bahuvir Palapai Kim Triloke Sacharachare Yat Kinchit Vastu Tatsaram Gaditam Vinanahi. Means what is the benefit to delirium? No object in this universe is without mathematics, and that cannot be understood without mathematics. So mathematics is the queen of all sciences, which is used in our daily life. Okay. So here we discuss some approximation properties of positive linear operators. So what is the operator? What is the operator? First of all, let us see that what is the operator. Suppose capital L is a function, a linear positive operator L is a function such that which satisfies the following properties. Number one, the domain D of L is the non-empty set of real functions. The domain D of L is a non-empty set of real functions all having the same real domain T. And the second thing that suppose F is element of D, then LF is again a real function having the same real domain T. And if F and G are two elements of D and A and B are two real numbers, then their linear combination, that is AF plus BG, is also element of T. This is the linearity property. And fourth property, that is called positivity property, that is F is greater, LF is greater or equal to 0. Any function is positive, F is greater or equal to 0 means Fx is greater or equal to 0 for every x element of domain T. Okay, if this is the positivity, linear positivity of F is greater or equal to 0, Fx is greater or equal to 0 for every x element of T. And this Lf greater or equal to 0, that is L of Ftx is also greater or equal to 0 for every f element of D and x element of T. Okay, so this is the linear positive operator. Approximations, especially Fourier approximation and wavelet approximation, have received great importance during the last few decades because of their use in modern technology, that is signal theory, data compressions in particular. And Fourier approximation was originally evolved from the problem of divergence of Fourier series. Kolmogorov in 1926 has proved that Fourier series of a continuous function of period 2 pi can diverge almost everywhere. And thus one branch of mathematics, that is approximation of functions using positive linear operators, came into its existence. And approximation by a linear positive operator means we assign, suppose, small s to an infinite series, that is sigma un, that is we try to generalize the concept of any non-convergent series. To make the non-existence problem into existence problem, to make unstable problem into stable problem, to make unmeasurable into measurable, to make uncountable into countable, we take the help of approximation of functions using such type of operators. Okay, so let us see here. We know that little LP space, this is frequency space, and capital LP, that is called function space. Little LP frequency space of infinite dimension, and capital LP, that is function space of infinite dimension. Little LP contains the sequences, that is x is equal to xn. Suppose x is equal to xn belonging to LP spaces. One is less or equal to p, less or equal to infinity also. Okay. So if we, that is the norm x p is equal to summation mod xi whole to the power p whole to the power 1 upon p, I varies from 1 to infinity. And this is, if this is finite, then we say that this condition holds good, that is 1 is less or equal to p less than infinity. And then we say that x belonging to little LP space. Little LP space. Engineers use L2 norm is equal to 2, L2 norm to determine the finite energy norm in their research problems. And here norm x infinity is equal to, that is supremum of mod xt, mod xn, supremum of mod xn over n. If p tending to infinity, then we have this much. And this is the frequency space. And the little L2, that is square summable sequences, that is called summation mod xi whole square, I varies equal to 1 to infinity, whole to the power 1 upon 2, that is square summable sequences, square summable sequences. And this is called PS summable sequences, PS summable sequences. And if it is equal to 1, we say that it is absolutely summable sequences, absolutely summable sequences. And engineers use this L2 norm to determine the finite energy norm in the problem. And let us see one thing, that capital LP space, yes, edge element of capital LP space. And what is the comparison between sequences spaces? That is, if one is, in order to define the, that is function space, we let here, 1 is less or equal to p less than q less than infinity, then we say that little LP subset of little LQ. And any function F element of LP over suppose closed interval AB, then we have that is norm FP is equal to integral A to B mod fx whole to the power P and dx whole to the power 1 upon P. If this is finite, where 1 is less or equal to P less than infinity, if this is finite, then we say that the function f is PS integrable functions. And what will be norm f infinity? That is called f infinity. If we tending to infinity, we say that essential supremum of mod fx. Essential supremum. Supremum of a function is unique, but essential supremum of a function need not be unique. That is, essential supremum of function is taken by excluding the countable number of points. Jump discontinuity is also countable. So you take that is excluding the countable number of points, and we pick up the essential supremum of functions, and this property hold almost everywhere. And we know that any property P is said to hold almost everywhere, provided measure of that set in which the property P not equal to true, that is set of measure 0. Then we say that any property P is said to hold almost everywhere. And if P is equal to 2, that is square integrable functions, that is norm f 2 is equal to integral A to B mod fx whole square or dx whole to the power 1 upon 2. If this is finite, then we say that f is element of L2AB. L2LB means that is square integrable functions. And we determine the finite energy norm of problems in L2 spaces. Convergence of Fourier series is also possible in L2 space, because the point one of the main result in mathematical analysis is called as correlation Hunt theorem. And the point-wise convergence of the partial sum of Fourier series is one of the hardest results in mathematical analysis. In 1966, L. correlation proved that is the element of L2 space. The norm SNS converges to fx almost everywhere for every element of L2 spaces. And we in Fourier approximation we take the signal integrable in the sense of Lebesgue, not Riemann, because convergence properties might be better for the Lebesgue integrable functions in comparison of Riemann integrable functions. And every square summable function on unit circle have unique Fourier series converging to the original function under L2 norm. So that we take the signal is integrable in the sense of Lebesgue, not Riemann. And the space of Riemann integrable functions is not complete, that is not closed under taking the limits, which makes the analysis harder to do. And while the space of Lebesgue integrable functions is complete, that is closed under taking the limits, which allows us to take the advantage of the fact that is, for example, compact smooth functions are dense in LP spaces. So we can define and show the things on smooth functions and take the limits and extend our result to such type of LP functions. And such type of analysis is impossible in the smaller space of Riemann integrable functions, so that signal is integrable in the sense of Lebesgue. And in Fourier approximation, that is let us see here, that is Tn ftx is equal to summation k is equal to 0 to n a n k s n ftx, which parent is equal to also 0, 1, 2, 3, etc. So this is the operator sequence to sequence transformation. That is the input signal sequence information. That is SN is called input signal sequence of informations, and the TN is called output signal sequence of informations. And this T is equal to NK, like as Shapley geometrics behaves like as a designing of digital filters with finite impulse response in particular. That is, this is the filtering process, and the filtering process means they reduce the echo-plus noises and gives the best approximation. Output is the best approximation. That is, error in approximation is very less. So this is the, if we can do the analysis on this operator, like by assigning different values of A and K, we get different type of operators. like a Bernstein polynomial. You know that Bernstein polynomial Bn ftx is equal to summation k is equal to 0 to n ck and x to the power k 1 minus x whole to the power n minus k fk divided by n. This is the Bernstein polynomial. By that is Lk is equal to Lck x to the power k 1 minus x whole to the power n minus k. This is the best. This is the called Pnkx. Pnkx. That is called the Bernstein basis functions. Bernstein basis functions. So this is the SNFX. If we take it in trigonometric polynomial, in Fourier approximation, SNFX, that is SNFX is equal to A0.2 plus sigma k is equal to 1 to n ak cos kx plus bk sin kx. That is called trigonometric polynomial of order n, provided a square plus bn square not equal to 0. So if that is, if we take this is also used in Fourier approximation also, wavelet analysis, etc. So this is called Bernstein polynomial of order n. And here that is interval is closed interval 0, 0, 1. And that is property that is Pn1x is equal to 1. Image of 1 under Bernstein polynomial is again 1. And image, suppose ft is equal to t, that is this property is called as safe preservation property. Akriti Sanrachana ka niyam, safe preservation property. That is image of t, suppose ft is equal to t. So Bntx is equal to x and Bn t square x is equal to x square. In general, we can determine Bnt minus x whole square of x with the help of linearity property. This operator is also linear operator, positive linear. This is the best example of positive linear operator. And one thing that is called Bn, similarly Bnt minus x whole square we can also determine, and Bnt to the power nx also determine here, that is moments of order n. This property is called as moments of order n. So this is the basic property of Bernstein polynomial, which is positive linear operator also. And by assigning the different values of a and k, we get different type of operators here. And one more thing that is called here, if we do the analysis here, that is a matrix representation form. If we write here it is in matrix notation form, then this will be, that is, let us see here, T naught is equal to A naught naught S naught. And T1 is equal to A1 naught S naught plus A11 S1. And T2 is equal to A2 naught S naught plus A21 S1 plus A22 S2. And and so on so forth. In general, we say that Tn is equal to A30 S0 plus A31 S1 plus A32 S2 plus A33 S3 and so on so forth. This much. And so on so this. So let us form the matrix representation. This is the output signal sequences. That is output sequence of informations. Tn is the output sequence of informations. And Sn is the input signal sequences. Tn is desired output signal sequences. So this will be, that is called T0, T1, T2, Tn, and so. This is the column matrix. Column matrix because it contains only one column. And this is equal to this. So they form the lower triangular matrix. T is equal to A and K is a lower triangular matrix with real or complex numbers. And A and K is equal to Pn minus K upon capital Pn, where Pn is the generating sequence, then we say that null operator. And here that is A naught naught, A1 naught, A11, A2 naught, A21, A22, and similarly A3 naught, A31, A32, A33, and remaining elements will be 0. Similarly AN naught, AN1, AN2, AN3, ANN. This much, and the elements before the above the principal diagonal is 0. So this is called a lower triangular matrix with real or complex numbers. And here, input signal sequences, that is S0, S1, S2, Sn, This is also called a matrix. Like as in, that is, you know that in order to prove Banach contraction principle, we form the iterated sequences. And the Banach contraction principle says that every contraction mapping on a complete metric space have unique fixed point. So we form the iterated sequences like in same way, and form the matrix representation of this positive linear operator. And this is the beauty of this, that is the if you take here Sn is trigonometric polynomial, then you know that trigonometric Fourier approximation has played a very significant role in the solution of various physical problems, and its applications are of vital importance, have been found in telecommunication engineering as well as stochastic analysis problems also. And what is the filtering process? That is transmitter and receiver. There is some transmitter and receiver. Receiver receives the best signal and they reduces the echo plus noises and gives the best approximation. That is, error in approximation is very less and the degree of approximation is the best. This is the output of this research work. And let us see here more properties. That is we know that this is the omega f delta. There are two type of kernels in Fourier approximation. One is called a Dirichlet kernel and the other is called a Thayer kernel. So Dirichlet kernel, that is a DNT. We know that Fourier series of any signal is given by a naught upon 2 plus sigma k is equal to 1 to infinity ak cos kx plus bk sin kx. And the partial sum, whenever we discuss the convergence or divergence of any infinite series, we take the partial sum of infinite series. Like in same way, that is we take the Sn, that is nth partial sum of Fourier series Sn fx is equal to a naught upon 2 plus summation k varies from 1 to n ak cos kx plus bk sin kx. By putting the values of a naught, ak, bk and solving then we get, that is after solving the steps, because time is very less, otherwise I will show you how to get Dirichlet kernel. Then there is expression that is sin n plus 1 upon 2t divided by 2 sin t by 2. This is called DNT. DNT is equal to this much. So DNT is called the Dirichlet kernel. Dirichlet kernel appear in Fourier approximation. It is given function of t, and if we determine the area of this kernel between t is equal to 0 to t is equal to 2 pi, then we get the result as pi by 2. And one other kernel appear in Fourier approximation, that is called a Thayer kernel. Thayer kernel Fn ftx. Fn ftx is equal to S0 fx plus S1 fx plus plus Sn fx and divided by n plus 1. This is called Thayer kernel. This is arithmetic mean, average of partial sum of Fourier series. Okay? Arithmetic mean of partial sum of Fourier. S0 fx is equal to simple a naught upon 2. S1 fx a naught upon 2 plus a1 cos x plus b1 sin x. Similarly, so arithmetic mean of partial sums of Fourier series is called as the average of partial sums of Fourier series is called as Thayer kernel. Thayer kernel plays very significant role in the research problems working in the area of electronics and electrical as well as computer science also. And this is the Thayer kernel. And one more thing, that is called this is called the Dirichlet kernel and Thayer kernel. And Fourier approximation, that is the summation, a piecewise continuous function, that is sectionally continuous function and a periodic function also. having left as well as the right hand derivative at each point of the interval have the Fourier series with Euler's Fourier coefficients A0, A n, Bn is convergent. And the series summation is equal to that point of continuity. And except the point of discontinuity, suppose x0 is the point of discontinuity, jump point on which the Fourier series summation is equal to 1 upon 2 limit x tending to x0 minus of fx or plus limit x tending to x0 plus of fx. Arithmetic mean of left and right hand limits of the function at the point of jump discontinuity, that is x0. The average of left and right hand limits of the function at the jump discontinuity x0. And this is the series summation, Fourier series summation at the point of discontinuity. And one more thing, that is Gibbs phenomena also appear here. Gibbs phenomena means the convergence of Fourier series is very slow near the point of discontinuity. And Gibbs phenomena is an overshoot a peculiarity of the Fourier series and the other eigenfunction at a simple discontinuity. So it is Gibbs phenomena plays a very, and by the convergence and the divergence of Fourier series, you know a book that is please see, you can see the book that is Fourier and wavelet analysis by George Bachman and Nericki, and it is published from Springer. Now it is available in Indian edition also. So the Gibbs phenomena is an overshoot of the peculiarity of the Fourier series and other eigenfunction at a simple discontinuity. Now next thing that is we discuss here, so time, how much time remaining? Huh? Only two most important tools in the area of nonlinear analysis, 6-point theory, that is called Lipschitz condition, contraction mapping, Lipschitz condition. Everyone knows Lipschitz condition. So we will discuss Lipschitz condition and I conclude my talk. There are two more important tools, that is modulus of continuity and Lipschitz condition also. Modulus of continuity substitute of differentiability. And the Lipschitz condition is stronger than continuity but weaker than differentiability. So any function f is said to be Lipschitz alpha over constant m provided mod fx minus fy is less or equal to m into mod x minus y raised to the power alpha. And suppose the function fx is defined on the intercept AB. Suppose the function fx is defined on intercept AB, okay? For every element of either it is open interval AB or closed interval AB, left open, right closed, left closed, right open, or whole real line that is minus infinity to infinity. So any function f is said to satisfy contraction mapping provided this condition. This is Lipschitz condition. Where 0 less than alpha less or equal less than 1. Because alpha greater than 1, the nature and the behavior of the function will be constant function. So when we are talk of let's say class, we always take 0 less than alpha less or equal to 1. And suppose every contraction mapping is also Lipschitz condition. Suppose f belonging to Lipschitz class, then the function must be uniformly continuous also. And the modulus of continuity, that is defined as omega f delta is equal to supremum of mod x minus y, supremum of mod fx minus fy over mod x minus y less or equal to delta. This is the modulus of continuity. This is called substitute of differentiability. Okay, since if infimum or supremum of any non-negative number is non-negative, so omega delta is always greater or equal to 0. Okay, supremum of infimum of any non-negative number is always non-negative, so it is obvious that omega delta greater or equal to 0. And 0 less than delta 1 less than delta 2, then omega delta 1 less than omega delta 2. Omega delta is increasing function with respect to delta. And integral, similarly, in similar concept arising here, integral modulus of continuity also. The integral modulus of continuity has the same properties as the modulus of continuity has. Okay. So can I? Okay. Thank you very much for joining us and listening in patience carefully. And very much thankful to chairperson and other senior professors. एंड बहु नहीं कृतघ्न कभी मैं द्रोह न मेरे उरावे गुण ग्रहण का भाव रहने दृष्टि न दोषों पर जावे। ओम पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते। ओम शांति शांति शांति। हरि ओम। श्री गुरुभ्यो नमः। हरि ओम।
But I think it is a classroom lecture what we do whenever. Classroom lecture is for MSc students. Board institution we can't take.
By assigning different values of A and K, we get different type of operators. Approximation properties.
So Sir has given wonderful presentations on various operators, summable functions, Fourier approximations, and etc. So thank you very much, sir. So I thank the organizing members, especially Professor Anuradha Kamesri Madam, Professor C.S. Srinivas Rao, Professor K.P.R. Sastry Garu, K.K.M. Sharma Garu, for giving a chance to be a chair of an eminent Professor Vishnu Narayan Misra. Thank you all. Next, we have an invited lecture by Professor G. Nanaji Rao Garu from Department of Mathematics, Andhra University. I request Dr. K. N.N.V. Varprasad Garu to please chair the session. I invite Nanaji Rao Garu to deliver his lecture.
మెయిల్ చేశాను కదా అది ఇప్పుడు నేను ఒకసారి పేరు చెప్తాను తెలుస్తారా ఆఫ్లైన్ సార్ ఎక్కడ ఉంటారు మన స్క్రీన్ షేర్ చేయాలి
Good morning, sir. Now,
అందులోనే డైరెక్ట్ పెట్టారు ICPAEMS ఒకసారి చూడండి
now I would like to invite Professor G. Nanaji Rao Garu.
ఒకసారి ఈ మూడు
G. Nanaji Rao Garu. Lecture on pseudo-complemented almost distributive lattices. G. Nanaji Rao Garu he joined in this organization in 2006 as assistant professor, later 2017 associate professor, in 2001 onwards he is a professor, and he completed PhD degree in this same university under the guidance of G. Rao Garu in 2001. And in 2001 he is qualified the CSIR net also, and he produced, he given the PhDs in 9 PhDs including foreign students and 9 MPhil students also, and more than 42 research papers he published. and he is giving a invited, as a resource person also he is giving a lectures national and international level also, and particularly he is attended as an invited resource person China in 2007 and in Jian, China in 2007 again, Indonesia in 2010 and Hong Kong in 2007, Malaysia and Thailand is also giving us invited as a resource person for lectures, invited talks, and he um, recently he got an Best Survival Radhakrishnan Best Academician and Research Award also. And he served as a head of the department in 2020 to 23. After that, he is serving as a warden an international guest house, an international students hostel, and recently he is nominated AP Set regional coordinator also. And also he is giving some several keynote addresses also given in the national, international level uh, bodies also. And now I would like to invite Professor Nanajarao Garu. Please start your session. And the time it starts, I think so maybe maintain the 30 minutes. Thank you very much. Good morning, everyone. So thank you very much, Professor Prasad, for introducing me. And also most of the audience are in the back side of almost all my students. So they know very well. First of all, I am very much thankful to the organizers for giving this opportunity to present my lecture in this international conference. I have, since from my PhD student onwards, I was attended many conferences in the presence of the legendary mathematicians like Professor N.V. Subramanian sir and I.H.N. Nagarajara garu, Professor U.M. Swami, Chakradhara garu sir. At the time, I feels in the conference because my teachers and their teachers, in that presence, I always feels as like his son, so that I am more comfortable in the attending such conferences. But now, the time being, so one by one, it's very unfortunate. So these number, the sense these legendary mathematicians by the time, so we lost many of such great personalities because it's very painful to me because I missed many of my teachers. Because I have seen in every conferences in the gathering, majority of my teachers' presence is it gives more happiness and gives certain energy to me, but we lost. So we cannot do anything because time pattern. Okay. So now coming to my lecture, in 1854,
George Boole, all of you know very well, introduced an important class of algebraic structure in his research work on mathematical logic called, in his honor, is called a Boolean algebra. And Boolean algebra has many applications in computer science, switching circuits. For example, you see this room that you have a board and in between wires, we can take it as a Boolean polynomial. Then, by using Boolean algebra, we can minimize the given Boolean polynomial with the same functional value. That is a very on application of Boolean algebra. And there are so many applications in computer sciences. So later, in 20th century, Ernest Solder and Peirce introduced the concept of lattice, and many legendary mathematicians developed extensively this lattice theory. So very few of them, Birkhoff, we call it as the father of lattice theory, and M.H. Stone, P.R. Halmos, Glivenko, Newman, K.B. Lee, T.P. Speed, such great mathematicians, they developed this lattice theory to maximum extent. And then, SAS. So this lattice theory, further development in lattice theory in the direction of, pseudo-complementation, pseudo-complemented lattices, complemented, relatively complemented, distributed lattices, etc. So these concepts were developed by SAS. And in 1980s, my teachers, Professor U.M. Swami and Chakradhara sir, introduced the concept of almost distributed lattices, which is a common abstraction of existing ring-theoretic generalization of Boolean algebras. And it is actually the PhD work of my teacher, Professor Chakradhara sir. And it is actually the thesis, only a single paper published in Australian Mathematical Society, based on that concept. Now there are more than 40 PhDs awarded on the concept of radials. And later, myself introduced a pseudo-complementation on that aerial structure with my teachers, U.M. Swami and Professor Chakradhara sir. So this is actually my talk. I was introduced a pseudo-complementation on almost distributed lattices is almost like pseudo-complementation on distributed lattices. That concept we can extend it to almost distributed lattices. Actually, this was done very long back. And later, very recently I have seen on book that lattice algebra, that means it's a lattice together with linear algebra. It's called lattice algebra, and it has many applications at present in artificial intelligence. I have seen very recently that book. Artificial intelligence, neural network, and image analysis, pattern recognition, all these concepts are included in that book. So next I will try to sway my direction towards that artificial intelligence, because we have very long background with lattice theory, and with this lattice theory, this is actually one track, and I was very recently introduced almost lattices, parallel to lattices, And so this track is going on. So that already we have an applications of artificial intelligence in lattice theory. So we will try to extend all these applications in my structure, almost lattices, and pseudo complemented almost lattices. This is actually, so I feel it's a new direction because everywhere everybody asks what are the applications of your theory, but theory is very strong, but applications also equally important. Okay, so that so now I will turn out to application part in my developer theory that is called almost lattice theory. Okay, so today title of my lecture is pseudo complemented almost distributed lattices. So please. Already we have a pseudo complementary lattice is a lattice with zero such that to each A belongs to L, there exists A star belongs to L such that A meet X is equal to 0 if and only if X less than or equal to A star. That means pseudo complement of an element A means it is the largest annihilator. That means suppose you can meet with 0, then you can choose the largest element. Such element is called pseudo complement of an element A. And the pseudo complement A star is uniquely determined by A so that star can be regarded as unit operation. Star can be regarded as a unit operation. Because why it is unique? Suppose for the element, A, suppose A star is one pseudo complementation. Suppose B star is other pseudo complementation. Then we know that A star is less than or equal to B star as well as B star is less than or equal to A star. So therefore, by antisymmetric, A star is equal to B star. So therefore, that A star is uniquely determined in the case of lattices. And because yet 0 meet X is equal to 0 if and only if X less than or equal to 0 star, this is true for all X. So therefore, any pseudo complemented lattice can be treated as it's a bounded lattice because it has already 0 and that 0 star is the largest element, so that it can be treated as a bounded lattice. And because this can be treated as a unit operation, so therefore, this pseudo complemented lattice can be regarded as an algebra. Algebra means all of you know is a non-empty set together with a set of operations. So it can be treated as an algebra of type 2 to 1 0 0. 2 to means already it's the binary operation. 2 binary operations. 1 denote unit operation, that is pseudo complementation, and that 0 0 denote 2 nuller operations means that is the least element and the greatest element 0 star. So this is an algebra. The fact that the class of pseudo complemented distributed lattice is equationally definable was first observed by Raben-Boeing, and also K.B. Lee proved that the class of pseudo complemented distributed lattice is generated by finite members, and a complete description of this lattice of equational class of pseudo complemented distributed lattice is given. So then later, Grazer, all of you know that is very, after Birkhoff, the Grazer is also very important person in lattice theory development. So Grazer studied about the pseudo-complemented semi-lattices and proved that if L is a pseudo-complemented lattice with pseudo-complementation star, then the set of all star elements, so those form a Boolean algebra. These form a Boolean algebra. Please next slide. So already I told you that the ADL concept was introduced by Swami and G.C. Rao. Already it is the generalization of Boolean algebra. So next, please. So next one. Next one. Next one, please. So this is actually the definition of an almost distributed lattice, because lattice structure means join is commutative, meet is commutative, and associative of both the operations and absorption laws. But here you have seen that the almost distributed lattice is a non-empty set L together with the two binary operations join and meet satisfying meet distributive over join both sides, and these three absorption laws and the zero element, 0 meet X is equal to 0. for all x belongs to L. This structure is called almost distributed lattice, and this was introduced in 1980s. At that time, we don't know still join is associative or not. Still, this investigation is going around 30 years, but this is unsolved problem. And 2 years back, Professor H.P. Senkapnawar visited our department, and already he wrote a book, Universal Algebra, written by H.P. Senkapnawar. And so I actually explained about this problem because join is associated in ADL or not, still we don't know. We cannot prove, or we can give an example of join is associated, non-associative ADLs. Still, most of the researchers are working on this concept, but still it's an open question. But after 30 years, with the help of Senkapnawar, finally we found a solution that there is an example that ADL, non-associative ADLs of join. So finally, that was solved in 2 years back. So now, here onwards, almost distributed lattice means join associative is also one of the condition. Join is also one of the condition. It's mandatory. Okay. So this is an ADL definition, and so there are certain elementary properties which you are using in the further text. Please, next one. Go back. Yes. So this is very, very important example in the study of almost distributed lattices. Any non-empty set can be make it into an almost distributed lattice by defining two operations join and meet like this. So A join B is equal to A if A is not equal to A naught, and B if A is equal to A naught, and meet is also same. A meet B is equal to B if A is not equal to A naught, and A naught if A is equal to A naught. So then this an ADL, it satisfies all the properties of ADLs, and which is called a discrete ADL with zero, and this zero element is nothing but A naught. So we have used this example for any observations throughout my ADL research. Next one, please. So these are some of the important properties which are used in the further text. Next, please. So as usual, homomorphism means any fundamental operation preserving mapping is called homomorphism because we have two binary operations and one unary operation it preserves. That is called a homomorphism. Next one. Next, the ideal concept already ideals in lattices. That means it is closed under join and closed under meet with an element in the set and element in lattice. But here, because we don't join and meet are not commutative, so that the second condition for any x belongs to y and a belongs to L, x meet a, that is important, not a meet x. X meet a belongs to y, that is ideal second condition. And for any subset A, the ideal generated by is defined as, so join I is equal to 1 to n AI meet x, where A belongs to A and x belongs to L and n belongs to Z plus. If such A is a singleton set, then we can write as, instead of bracket A, you can write a small bracket A. It is called principal ideal generated by A. And in the same lines, we have defined the prime ideals, similarly filters and prime filters. Next one. So this is, so already you know that in a partial order set, maximal element, minimal element, least element, greatest element, and the interval also in the lattices. Same like here also have defined the same concepts. And that A star, that is more important, it is called annihilator of A, and it consisting of all x such that A meet x is equal to 0 for all A belongs to A. And this is an ideal, and this is called the annihilator ideal. And if A is equal to singleton 0, instead of capital A star, we can write small a bracket star if A is a singleton A. And we are using these notations in the coming text. Please, next. So these are some properties of ideals. In general, you see that 4 and 5 conditions, we don't know, actually in ideals, join and meet are not commutative, but ideal generated by A intersection ideal generated by B is equal to ideal generated by A meet B, which is also equal to ideal generated by B meet A, and similarly join also. But in general, A join B is not equal to B join A, but in coming to principal ideas, those are commutes. Okay, next one. So here, this is actually my lecture. So in this section, we have introduced the concept of pseudo complementation on ADL. So this is the definition. Let L join meet 0 be an ADL with 0, then a unary operation A going to A star and L is called pseudo complementation. If for any AB belongs to L, it satisfies these following 3 conditions. So A meet B 0 implies A star meet B is equal to B, and A meet A star is equal to 0, and A join B whole star is equal to A star meet B star. In the case of distributed lattices, this P3 condition is a consequence of P1 and P2 in the case of distributed lattices. But in the case of ADLs, these 3 conditions are independent. So for this, we have given an example. Please, next one. So this first example shows that this is an ADL which satisfies P1 and P2, but not P3. So this is a description. Next example. Next, please. So the second example, it shows that it satisfies P2 and P3, but not P1. And the next example shows that it satisfies P1 and P3, but not P2. So therefore, these 3 conditions are independent. So that therefore, but in the case of P1, P3 is the consequence of P1 and P2, so that we skip the P3 condition. But in the case of ADLs, we are using these conditions in the definition of pseudo complemented ADL. Please next. So this is an important example for an ADL with pseudo complementation. So let R plus 0 be a commutative regular ring. To each A belongs to A, let A power 0 be the unique idempotent element in R such that AR is equal to A naught R. Now we define binary operations join, meet, and unary operations star as follows. A meet B is equal to A power 0 B, and A join B is equal to A plus 1 minus A naught into B, and A star is equal to 1 minus A naught. Then this is clearly an ADL with 0 and star is a pseudo complementation by using a regular ring. So regular ring means it is a ring in which to each A there is a B such that A is equal to ABA. So such ring is called regular ring. Okay. Next one, please. Next slide. Okay. Already I told you in the distributed lattices, pseudo complementation, that is the unary operation. If it exists, then it is unique. If it exists, then it is unique. But in the case of ADLs, there are several pseudo complementation. There are several. So this is an example. This shows that an ADL have any number of pseudo complementations. So let X join meet 0 be a discrete ADL. Already I told you. For any X not equal 0 in X, define A star is equal 0 if A not equal 0 and X if A is equal 0. So then this star is a pseudo complementation on X. Here with each X not equal 0, we get a pseudo complementation. So therefore, the number of pseudo complementations depends on the number of elements in capital X. Next, please. So this is a more generalized form of the above example. This is also an ADL with more than one pseudo complementation. Next, please. So this theorem actually defines that any relatively complemented ADL with 0 with the maximum element M0 can be converted into ADL with pseudo complementation by defining for any A belongs to L, A star can be defined as the complement of A in the interval 0, A join M0. Then this star is a pseudo complementation on L, and this is an ADL with pseudo complementation star. So this theorem actually defines that any relatively complemented ADL can be treated as an ADL with
pseudo complementation. Next, please. So these are some important properties of pseudo complemented almost distributed lattices. So these are all elementary properties, but very useful in the coming text. Next one, please. So yes, there are some certain properties. Next, please. Yes. So this theorem is very important. In universal algebra, you know, a class of algebras are said to be variety. Variety means it is a class of algebras which is closed under subalgebras, homomorphic images, and direct products. So such class is called a variety. And in universal algebra, they proved that a class of algebras become variety if those are equationally definable. Those are equationally definable. So in this, our pseudo complemented ADLs are equationally definable. This is the theorem. Let L be an ADL with 0, then a unit operation star and L is pseudo complementation on L if and only if it satisfies that 5 conditions, and that is the second one also another set of conditions. So therefore, these two theorems says that the pseudo complementation on an ADL is equationally definable. So therefore, the class of ADLs, those form a variety. So with these two theorems. Next one, please. So next, already in semi-lattice with pseudo complemented star, the set of all star elements they form a Boolean algebra. Here also we have proved that if L is an ADL with pseudo complementation star, the set of all star elements form a Boolean algebra. Here you take any two star elements, their meet is their meet is as usual in the meet in the original ADL, but join is defined like this. For any two elements, A star join B star is defined as A double star meet B double star, whole star. Actually, there is a whole star. That is the least upper bound of any two star elements. With these two operations, the set of all star elements, those form a Boolean algebra. Okay. Next, please. Yes. So this is very important lemma, and I am very interesting on this lemma because why it's very interesting, I told you later. So already I told you pseudo complementation is not unique on ADLs. There are several pseudo complementations. Suppose star and perpendicular with two pseudo complementations, then we have the following results. A star meet A perpendicular actually is equal to that is A star. Okay. And A star join A perpendicular is equal to A star. A star perpendicular is equal to A double perpendicular. And this is the sixth one is more important. Sixth one, A star join A double star is equal to 0 star if and only if A perpendicular join A double perpendicular is equal to 0 perpendicular. So this is very important condition to introduce, this motivates us to introduce a stone ADL. Stone ADL means already I think third semester students, Banach algebra, you know stone lattice. Stone lattice means it is a distributed lattice with 1 in which A star join A double star is equal to 1. Such distributed lattice is called a stone lattice. So here A star join A double star is equal to 0 star if and only A perpendicular join A double perpendicular is equal to 0 perpendicular. This is true for every A. So with this condition motivate us to introduce this called stone ADL. So this is actually very important, and I like it, this paper very much still. And most of the people are now working on this stone almost distributed lattice concept. Still is going on. So next one, please. 2 minutes. So next, this is also an important theorem that how we can count the number of maximal elements in an ADL. That means you can find number of pseudo complementations, then we can find number of maximal elements. So this is a theorem. Let L be an ADL at 0 and star be a pseudo complementation on L, and M be the set of all maximal elements in L, and PCL be the set of all pseudo complementation on L. Then for any M belongs to M, define star M is from L to L by A for star m is equal simply A star meet m for all A belongs to L. Then the mapping m going to star m is a bijection on m onto PCL. That means because there is a bijection, you know the cardinalities are same. So therefore, the number of pseudo complementation on L is equal to the number of maximal elements on L. And this count is very important in further development. Okay, and also we have two more than one pseudo complementations. Already we proved that if a star is a pseudo complementation, then L star is a Boolean algebra. And perpendicular is also pseudo complementation. Therefore, L power perpendicular is also Boolean algebra. But these two Boolean algebras are isomorphic. That means the Boolean algebra is independent of the pseudo complementation star, because you take any number of pseudo complementations, all those Boolean algebras are isomorphic. So therefore, it is independent of the pseudo complementation star, these Boolean algebras. So next one, please. So before going to star almost distributed lattices, because there is no time, actually, so the continuation, but there is no time. First of all, before going to stone almost distributed lattices, we have introduced the star almost distributed lattices. In the presence of star almost distributed lattices, then we are introducing stone almost distributed lattices, and these stone almost distributed lattices characterized in terms of minimal primordials and primordials in both topological and algebraic characterizations. So please scroll this. Go fast. So these are all characterization theorems. So this time is over. Because I want to say one thing, that for preparing this work, this is actually research work done by me and my teachers. It took 3.5 years work. So it explains within half an hour is impossible, no doubt. So this work actually, the span of this work is 3.5 years to 4 years work. Within half an hour, it is more difficult to explain. So I will try to explain some concepts. Sir? Yeah, yes, sir. Thank you so much, sir. So please, if you are interested on who are working on this concept, also I have introduced almost lattices, as now the work is going on around the world, because I have seen my research gate. So almost many people are working on almost lattices in USA, Canada, Japan, African continents. So you are also, if you are interested on this almost lattice is available in Google search. Okay, please contact me, and I will help you up to my knowledge. So thank you very much for giving this opportunity to present this lecture.
Thank you, Professor G. Navajmura Garu. So this is time for the questions. So requesting the audience, if any questions, please ask now.
So I have faced some problems in some interviews. So most of the professors, I faced one problem in one interview, that your theory is very strong, but what are the applications? There is a question. In abstract algebra, it's very difficult to identify immediate application, no doubt. It is accepted because our legendary mathematicians from our department, like Professor N.V. Subramanian sir onwards, they developed theory background is very strong, but direct applications is very difficult to produce in abstract algebra particularly. But definitely there is an application, no doubt at all. Yes.
Actually, I wanted to ask, but sometimes asking is not good. You said about the topologically. So what it means, and then can you see like some later on that condition of compactification or something like that in this theory? What do you mean by topological in your lecture? Recently you shared that. Yeah.
You know, in ring theory, you collect all prime ideas. They form a topological space. It is called prime spectrum. So the same thing we have ideal theory in this also. And then we have defined a topology on that prime ideals and minimal prime ideals. And we have a topology structure. Those are called the Hull kernel topology, you know already. So we can characterize our stone ideals and star ideals in terms of those topological terms. That is because we have ideal theory. Okay. Yes. Spectrum, prime spectrum. Yes. Yes. Okay.
Any questions from audience? Thank you. Thank you very much, Professor G. Nanajirav garu. Thank you very much, Madam Organizing Secretary, Head of the Department of Funds, the Commission garu, and C.S. Srinivasarao garu, and Yalakshi Sundaram Society and Uttaraandhra Society for Mathematical Science. Thank you very much. Now, I request you to please, Professor Nanajirav garu, please come. And take it now.
Can I share? No. Can I share one website just for 1 minute? Go to
Now, I would like to invite, before starting the next lecture, I would like to invite Professor G. Rajashekar garu. He will give us some address about IMS, Indian Mathematical Society. Sir, please.
Thanks. Since many youngsters are there, I thought let me use this opportunity. So there is a reason. Just I would take 1 minute. Where is the website? Just now I shared. Can you share the website? So this is on behalf of Indian Mathematical Society. I would like to introduce the society to the younger participants. So please try to become life members of the society, and in particular, we have a large number of awards and prize sessions for youngsters. But every year we don't get enough entries for participation in this awards and prize session. So the motto of the society is to encourage youngsters. So please go to the website of Indian Math Society. Can you click, sir? Awards and prizes. Awards and prizes. Yeah, prizes. So the call for this year will be given very soon, maybe in this week. Okay. So this 90th IMS will be held in MIT World University, Pune. Every year it will be held at various places. So, for example, in 17, University of Kalyani, 18, IIT Kharagpur, so then VIT, so then Mahatma Gandhi University, then last year VIT Mestra, then last year it's Hyderabad. So this year it will be held at MIT World Peace University, Pune. So it's a large gathering. So you have 6 symposia. In each symposia, about 6 speakers. So you can imagine. Then 2 plenary and about 10 invited. So it's a large contingent of spectrum of mathematicians. For example, last year we were very glad to have Professor Manjul Bhargava for one of the plenary. Of course, could not make it physical, but online. So my earnest appeal to younger colleagues is, from now on, you become life members and actively take part in IMS activities. And thanks for the organizers for giving me this opportunity. Thank you.
Thank you very much, sir. Now, the next talk is Professor Ramesh Kumar Watts. He's giving a lecture on what? And online. For the conducting of this inventory talk, I would like to invite to Professor B. Munswami Garu. Sir, please come and conduct this.
Yeah.
Hello. Sir Ramesh Kumar sir, please unmute your mic.
Yes, I can unmute myself.
Ramesh Kumar sir.
Should I start?
Yeah. No, line out sound pitch.
Should I start? Am I audible to all?
Ramesh Kumar sir, please connect one device. Echo is coming.
I connect only one device, na?
Yeah.
Should I start now? Am I audible?
Yeah, you are audible, sir.
Okay. Should I start?
1 second, sir. Just, yeah. So, good morning to one and all. My name is Professor B. Munswami, Head Department of Statistics, Andhra University, Visakhapatnam. I am chairing the session to Professor Ramesh Kumar Words. Once again, I welcome to the International Conference on Pure Applied and Engineering Mathematical Sciences. I thank the organizers for giving an opportunity to chair the session. Now, today's speaker is Professor Ramesh Kumar Words, Associate Professor in the Department of Mathematics and Scientific Computing, National Institute of Technology, Hamirpur. His area of research interest is fixed point theory, functional analysis, fractional calculus. So he published more than 72 research papers in national and international reputed journals. And also his readers is 8,880. Citation is 374. So now, his talk is controllability of fractional order systems, recent advances and perspectives. So now I request to Dr. Ramesh Kumar Words to deliver your talk. Thank you, sir, for accepting the invitation. Thank you.
Thank you very much for nice introduction to me. First of all, I am thankful to the organizer, especially Professor Srinivasan, for giving me the opportunity to share my views on this topic, that is controllability of the fractional order systems, recent advances and perspective. I just would like to elaborate about the controllability in the fractional order system. And in this system, in this controllability, what are the recent advances and the what will be the perspective of this mainly controllability under the banner of this fractional order system?
Sir, excuse me, sir.
Yes.
Sir, your time is allocated to 30 minutes, sir.
Okay.
Yeah, okay.
Just a minute. Okay, these are my contents, that is fractional calculus, fixed point theory, and controllability under the fractional order system, then recent, and then finally we would like to consider one of the problem of the controllability using the fixed point theory. Then in this talk, what we will do, we will outline the concept of controllability, which refer to the degree to which a system behavior can be directed or manipulated by applying inputs. What is the controllability? Controllability is a crucial for ensuring desired outcomes, especially in the context of the fractional order system, which deal with the derivative and integral of the non-integer order, extending the concept of the differentiability and integration to the non-integer powers. We will explore controllability using fixed point theory, which investigate mathematical objects in the space that remain unchanged under a given transformations. Especially we basically plays on the transformation and the differential equation and the differential operator to get the controllability of the system. Then first we would like to continue, introduce, that is what will be the fractional calculus. That what you have seen above the C, that is not complete. It means it is a part of that completeness. That is a fractional part. Then come to the part of the derivative in the fractional derivative. Why n in nth order derivative has to be a positive integer. You should consider the, if it is negative, then it is equivalent to be the n times of the integral. That means n times of the derivative is the reverse process, and that will be considered as a identical functions. It turns out that this question has been asked by the Hospital in the letter of to Leibniz in 1695. What would happen that is Hospital wrote in letter what would happen if we take n is equal to 1 by 2 in the nth order derivative, which comes in the under this nth order derivative. Then the Leibniz replied that this is an paradox from which one day will draw useful consequences. Then in 1738, Euler introduced the alpha order derivative of x raised to power beta, where alpha beta both are positive real numbers. It comes to the part of the that is in gamma function, and gamma functions comes from the nth order derivative, which is the formal generalization of the elementary fact. This is the nth order derivative of x raised to power m, where mn both belongs to the natural number, and then this factorial m is a gamma function of m plus n, and in denominator we have factorial m minus n, that is a gamma function of m minus n plus 1. It comes, that is above definition, that is gives in the 1734, is introduced by the generalization of this elementary fact. Around 1830, Livoli considered functions that can be written as a series. That is, a function can be written in the series form, that is summation this one, and derivative of the series with respect to that function and alpha order is again we get a series. Then but these definition leads to the controversies. What controversies? Let us now compare this with the definition given by the Euler to see if they agree. By Taylor series, we get e raised to power x is this an expansion. If we consider by the definition of the Euler, we consider the alpha order derivative of e raised to power x, that is using the previous definition defined, that is not equal to be e raised to power x, but e raised to power x derivative is e raised to power. So it leads the contradiction. By Livoli definition, the alpha order derivative of e raised to power x is e raised to power x. This leads the contradiction. And to remove this contradiction, in 1823, Abels considered the Teutogon problem and posed his solutions in terms of the integral equation. Later on, this problem was considered the first application of the fractional calculus. What I think everybody aware about the Teutogon problem. What is the Teutogon problem? In this one, and we consider 3-4 balls at the different places along this trajectory curve. We kept at the same time at the different positions and then throw all the balls at the same times. We will observe that all the balls reached at the destiny at the same time, instead of starting point is different. One consider as a blue ball, another is a red ball. That is a place where we kept and initially start from that green and yellow. We start at the same time and we observe that they reached at the same place. This is called Titokono problem. In the mid of 19th century, Riemann and Livoli introduced the fractional derivative. This is the definition of the fractional. Before introducing the fractional derivative, they introduced first the Riemann-Livoli fractional integration, so that for getting the fractional derivative, that integral RL fractional integral will be used. This is the definition of the Riemann-Livoli fractional integral, where alpha greater than 0. That means alpha lies between minus infinity to infinity. A is the order of this order. Then using the previous definition is you're using the Cauchy integral formula for n-fold. This n times of the integral can be converted to the single integral using the Cauchy integral formula, which is given by this one. The Cauchy formula for repeated integration compress n times integral of a function into a single integral. The Riemann-Livoli fractional derivative of order alpha is defined as, this is the definition for the Riemann-Livoli, in which that they use the J, that is a Riemann-Livoli integration. This J stands for the Riemann-Livoli integration. That's why they introduce integral first, then derivatives using that integral. In 1967, Capito introduced the Capito fractional derivative by exchanging the order of derivative and fractional integral. The Capito fractional derivative of order alpha is defined by this one. This is the definition introduced by the Capito in 1967, where alpha lies between n minus 1 to n. That means any fractional quantity. There is a relation between the Riemann-Livoli and Capito fractional derivative. There is a relation between these two derivatives. One is a Riemann-Livoli, another is a Capito derivative. This is the relation. The right hand side, this is a Capito derivative, and this is the Riemann-Livoli derivative. Then this is the relation between these two. And thus, the two types of the derivative coincides for the zero initial condition. If we consider the zero initial condition, these two types of the integral coincides. Then Rudolf Hilfer introduced the new definition of the fractional derivative at the end of 20th century, known as Hilfer fractional derivative. It is also known as the generalized Riemann-Livoli fractional derivative. This is the definition given by the Hilfer, and this is a simple definition of where mu is equal to be sigma plus v minus sigma v, provided the right hand side exists. The definition exists, only the right hand side exists. This is the J stands for the Riemann-Livoli integration. J stands for the Riemann-Livoli integration. We have given a remark on this one. If we consider v is equal to be 0, the Hilfer fractional derivative becomes the Riemann-Livoli derivative. It means it is the generalization of the Riemann-Livoli integration. It is also generalization of the Capito derivative. You can consider if v is equal to be 1, then Hilfer derivative becomes the Capito fractional derivative. It means mainly the Hilfer is generalization of both the derivatives, which are Capito as well as the Riemann-Livoli. Then this is the basic application of the fractional calculus, where we can apply it. During the last decade of the 19th century, Heaviside successfully developed his operational calculus. In 1892, he introduced the idea of fractional derivative in his study of the electrical transmission lines. And there are so many applications of this fractional derivative to increase the speed of response, to decrease the relative stability, to decrease and eliminate the steady state error, and fractional damping. This is oscillation with the fractional damping, where k is a given function and these are the constants. This is basically introduction of the data. You can go through these papers by seeing the application of the fractional derivative in control theory, in image processing, in bioengineering, and telecommunication, electronics, signal processing, economics. There are so many applications of the fractional derivative. Now come to the next part, that is a fixed point theory. There are fixed points throughout the lifetime where things must stay exactly the way they are. When I stir my cup of coffee, at least one speck of liquid winds up exactly where it started. That means the existence of the fixed point. In mathematics, a fixed point theory is related with the fixed point of a map. A function f will have at least one fixed point if there is a point x naught in the domain this one. This is the intersection point of the graph, and the line y is equal to bx gives the fixed point in the given graph. Fixed point theory is a fascinating subject with enormous application. The knowledge of existence fixed point has relevant application in many branches. Fixed point theorem are basically mathematics tools. The importance of the fixed point theory lies mainly in the fact that most of the equation arising in the various physical formulas may be transformed to the fixed point equations and inclusion. Means basically what is the fixed point? That means we have so many fixed point theorems. Basically whatever we have the physical problem, try to convert those physical problem into the fixed point theorems, and then we can apply that fixed point theorems to get the solution of that physical problem. And you can see only one fixed point of this graph. This graph is sine of x by 2. That is, y is equal to bx line intersect this graph only at one point. There are two fixed points. The y is equal to bx lines meets this graph at 2 points. That's why it has two fixed points. The 7 fixed point, the graph of the line y is equal to bx meets this graph at 7 points. That's why we can say it has 7 fixed points. Infinite many fixed point, the graph of this function meets the line y is equal to bx at infinitely many points. That's why we can say it has many fixed point theorem. It means a given function may not have, may have one fixed point, two fixed point, many fixed point, infinite many, and no fixed point. And before getting this, next one is we have some basic theorem which are to be useful to get the controllability to which are to be applied in our system. Schroeder fixed point theorem, that is a function f from b to b is a continuous function where b is a convex compact subset of a Banach space y. Then f has a fixed point. And Sadowski fixed point theorem, y be a Banach space, B be the closed, convex, and bounded subset in Y. If this function, the self map, is a condensing map, then F has a fixed point in B. And then come to the point of what is the condensing map? Then let Z and Y be two Banach space. A continuous map is said to be condensing map if F takes the bounded sets into the bounded set, and this contraction apply for all bounded sets for this one. Then Krasnow-Celsky fixed point theorem, let B be a convex, closed, and bounded subset of a Banach space Y. Let F1 from B to Y and F2 from B to Y be two mappings such that F1 Y1 and plus F2 Y2 belongs to B. For each pair, Y1 Y2 belongs to B. If the operator F1 is contraction and the operator F2 is completely. In earlier theorem, we have considered only one operator on which we consider the different conditions. But here we have considered two operators. One have a contraction and another operator is completely continuous. Then the operator equation F1 Y1 plus F2 Y2 is equal to Y as a solution on B. Then come to the part of the controllability. You can't control without being controlled. You can see in the beauty of this words, you can't control without being controlled. Then everything will looks good if it is controlled. If it is uncontrolled, then it destroy the system. That means the controllability is a fundamental concept of the mathematical control theory. So before this, we throw light on the history of the control theory. That is brief history. Control theory is an interdisciplinary branch of engineering and mathematics that deals with the behavior of the dynamical system to achieve the desired goal. Basically, we have some input and we require some output. That to get the desired output, to get the desired goal, that means under these circumstances, under the given circumstances, that means using some different parameters of the system, that means it is a control system. The control mechanism are widely spread in the nature. For example, in biological system of the human body, our body temperature and blood sugar level need to be controlled at desired set of points. Otherwise, doctor says you are BP patient, you are any other patients. Then insect and the animal population are controlled by very delicately balanced pre-predictor relationship and several man-made control systems such as missiles, nuclear reactors, automatic washing machines, etc. These are using by the control theory. However, whether the system is natural and man-made, they have a common aim, that is to control or regulate a particular variable within the certain operating limit. Now, control mechanism has been seen since ancient time. Some experts believe that the control theory is more than 2000 years old and originated in the ancient manner, where the control of the irrigation system was also a well-known art. You can go through for getting the control system in the irrigation, you can go through the paper under the toolbar, that is at the bottom toolbar. The modern development of the control theory starting during the 17th century. In 1656, the pendulum clock invented by the Christian Huygens was a modern example of the development in control theory in which the problem of speed control was analyzed. Control theory nowadays being viewed from two perspectives: a theoretical foundation for the control engineering subset of the, that is system engineering, and a mathematical disciplines. How do I explain controllability to a layman? That imagine that we have a toy remote car in a room. We have its remote and it is built such that it can only move left and right from the bird's eye views. We also have a sensor on the left wall measuring the distance of a car from the wall, which we decide to call. You can see this moment of the car can be in this one by applying the sensor on the one wall. Since we have the remote, we can move the car by changing its position X. Thus, its position X is controllable. Imagine that we are interested in being able to make the car go to any point we want in the room. To be able to define any point in the room, we call the car distance from the lower wall as Y. But since the car can only move left and right, we do not have any means of the influencing its position Y. Its position Y is uncontrollable. We thus decide to upgrade the car, and now it can also move upward and downward directions. Now we can also influence the car position Y, thus its position Y becomes the controllable. We decide to solve this problem by installing a sensor on the lower walls. Now its position X and Y are both controllable since we have the means of the influence them by the remote and the car wheels controllable. The controllability is a fundamental concept of the mathematical control theory introduced by the R.E. Kalman in 1960. Controllability is a qualitative property of the dynamical control system that plays an essential role in developing modern mathematical control theory in finite and infinite dimension space of the system representing by ordinary differential equation. Controllability means that the dynamical system can steer from an arbitrary initial state to the arbitrary final state with the help of some admissible control functions. The controllability of nonlinear systems represented by evaluation equations or inclusion system in abstract space lead to some important conclusion regarding the linear and nonlinear dynamical system. Many scientific and engineering problems are nonlinear and can be described in infinite dimensional space. So the study of controllability in infinite dimensional space becomes significant. And motivation for the controllability, consider one-dimensional initial value problem. We have considered a differential equation that is initial value problem in this one-dimensional dx upon dt is equal to this under this definition. Choose the final state, that is after this 2 seconds, it reaches to be 6. The trajectory of the system starts from the initial state 3 and does not reach the final state in the interval 0 to 2. But after applying some control function, that is ut is equal to be this, in this differential equation, we can see our desired goal will be achieved within 2 seconds. That means final state it reaches to be at 6 point. Similarly, you can see the tank problem. We have a water inflow rate R, concentration of the salt water is this, and one is a tap outflow of this rate R. Then amount of the salt is V. Both taps are open and water through tap 2 is getting mixed into the solution instantly. The differential equation formulation is as follows by that water tap problem, tank problem. In particular, R is equal to this, V this one. The differential equation formulation becomes like this one. And we got the trajectory point from this one. After point this, after 6 seconds, it reaches to be point near below the 3, below 0.3. How much salt, then the concentration of the salt is decreasing. How much salt should be mixed into the solution per unit time so that the concentration of the solution remains constant, that is 0.5 at T is equal to be 6. Because at T is equal to 6, the concentration of the salted water is 0.26, near about to be 0.26. But our aim is it should be 0.5 after T6 second also. In order to sustain the concentration of the solution at T6, we formulate the differential equation as follows, where ut is a control function that has a different formula to calculate. For the different problem, it should be the different one. So then after T is equal to be 6, the concentration of the salted water will be the 0.5. After adding this control function, the solution of the control system using the transition matrices. Consider the n-dimensional linear system. Earlier we have taken one-dimensional system. Here we have considered the n-dimensional linear control system. This is where AT and BT are the matrices. The solution of the control system is given by this one. This is the solution by given this. The system is controllable if and only if for arbitrary initial and final state x0, x1, there exists a control function u such that this condition will be holds. The conditions for the controllability. Now, whether every system can be controlled, then what are the conditions for the controllability? This system 14 is controllable if and only if this u belongs to L2 such that x1 is the initial conditions, then this x1 is equal to this one under this initial condition. Then define an operator C from L2 to Rn by defining this equation number 19, and where C is a bounded linear operator, range of C is subspace of Rn. Since x0, x1 are arbitrary, the system is controllable if and only if C is onto. Range C is called the reachable set of systems. Now next to the controllability gramming. The controllability gramming matrix is given by this one, this formula. This is the controllability gramming matrix by which we can find the control functions. The result, the linear control system is controllable if and only if this gramming matrix is invertible and the steering control that moves from x0 to x1 is given by this one. By using this gramming matrix, we can calculate this control function ut for the different type of the problem, and the system is controllable if this gramming matrix is invertible. That is the condition of the controllability. Controllability problem, consider linear system. We have considered linear system under this initial condition where A and B are the matrices of the different order. Then Kalman rank condition, we have a result that is named as a Kalman rank condition. The system 22 is controllable if and only if the rank of B, this is an augmented matrix, B semicolon AB, then A square B, then A cube B, up to the A raised to power n minus 1 B, where n is the order of the matrix A. If it is equal to be n, then this system is said to be controllable. This is a condition that is named as a Kalman ring condition. Then we consider a two tank problem. Earlier we have considered a single tank problem. Now consider two tank problem when x1 be the water level in the tank 1, x2 be the water level in the tank 2, alpha be the rate of outflow from the tank 1 and beta be the rate of outflow from tank 2. Let U be the supply of the water, U be the supply of the water to the system. Then this is the differential equation by using this tank problem. Then you can see this A and B are the matrices and U is the control functions. We can see this Kalman rank condition, that is B semicolon AB, that is augmented matrix, its rank is 2, that is equal to be the order of the matrix, hence this system is a controllable. This system is a controllable. Now consider the another tank problem in which the first tank does not have any inflow, only outflow is there. After some time the first tank will be empty. You can see mathematically also, these are the mathematical equations from that tank problem. You can find the rank condition, Kalman rank condition, it is equal to be 1. So this is, that is not equal to be the N2. That's why this system is not controllable. That is under the Kalman rank condition. Again, we consider an example, consider the spring mass system having the unit mass with a spring constant. Then this is the condition, this is the equation, mathematical equation for this system. And differential equation, you can see spring mass where A and B are these matrices. Then B is the system is not controllable because B is equal to be 1, 0. That is spring mass is controllable if B is equal to be 1. If we consider, but we take B is equal to be this one, then system is uncontrollable under the Kalman rank condition. Now we have some different type of the controllability. One is exact controllability. It means our final state is exact. We would like to get the exact final state. Another is a automatic. This is one of the example for this exact control. Modern automobiles are equipped with the cruise control system that allows drivers to maintain a constant speed without continuously pressing the accelerator pedal. The cruise control system provides an excellent example of the exact controllability. The speed of the vehicle VT is controlled by the adjusting the throttle opening. The dynamics of the vehicle speed can be represented by the first order linear differential equation, where m is the mass of the vehicle, ut is the control function representing the throttle opening. The exact control, let us define the well-defined control function. This is a defined component where A represents the specific throttle opening. All of the exact is praised to be this one. Then this is the realistic example. Next come to the part of the approximate controllability. That means we do not have any final, we cannot achieve the final state exactly. We would like to achieve in the neighborhood of that system. That is example for this in temperature control in a room. It means that is the Newton law of cooling. Then this is the rate of change of the room temperature. K is the constant representing outside temperature, inside temperature. Ut is the control functions. And this is another if representing heating effect. And HC constant representing in this example approximate control means the using the control function, the room temperature towards the desired comfort level. It's a too cold, too heater. That is a simply. Third one is a trajectory controllability. That is we move a specified path. We would like to move. Yeah.
Hello.
Yeah.
Sorry, you have 2 minutes more, sir.
Okay.
Yeah. Okay.
This trajectory controllability means we have a specified path for this particular one. Trajectory controllability specified. Next is a null controllability. This is any state vector may be steered to the null vector. This is the best example for the null controllability. The height of this one. This is a null controllability. Come to the total controllability. That means in a complete sub intervals. Yani our system will be controllable in the sub intervals also. This is the best example for the total controllability. Then these are some examples which are to be controlled, but that is blood sugar is to be controlled, rocket missiles, regulating inflation. Then come to the part of the controllability of the fractional order. Recent advances of perspectivity. That means controllability of the fractional differential represents a fascinating and evolving domain within the broader field of the control theory. Over the past couple of decades, researchers have made significant stands in the extending classical control concept of the accommodate the unique characteristics of the fractional order. The Kilbas initiated foundation work by the advancing theories in the fractional calculus, paving the way of the understanding complex dynamics is in significant influence the analysis and the control of the fractional order system, particularly in exploring control of the stability YQ chain, a prominent figure in the control theory being this one. These mathematicians, among others, have collectively propelled the development of control theory. One notable aspect of this development is the formation, that is theoretical framework analyzing the understanding controllability perspective. That means here are some journal perspective and potential advances in the controllability. The controller design for the fractional system. These are the basic examples. Stability and robustness. In the coming days, the robot is coming to do the every work. Robot is coming days. That is also the using of the control functions. That the application is science and engineering, fractional differential equation, the combination of the fractional order. These are the basic example. Now come to the part of our problem, that is using fixed point theory. How can we define a fractional order system? How can we find a controllability using some of the fixed point theory in infinite dimensional space? We have considered the particular problem, that is approximate control non-densely defined Hilfer neutral differential system with no local initial conditions. We consider the non-densely difference. This is the non-densely defined Hilfer delayed neutral differential system with no local condition, where these are some basic parameters of this differential system. These are the basic parameter. Now come to the part of instantaneous impulses. The during of these changes is negligible in comparison with the duration of the entire evolution, such as shocks and natural disaster. And non-instantaneous impulses, the duration of these changes stay for a finite time interval. Very well application of the non-instantaneous impulse in the introduction of the insulin in the blood streams, which is an abrupt change and the consequent absorption, which is gradual process as they remain it active in this one. We now review the essential result for discussing the primary finding. We consider these are the mild solution, that is our whatever the basic problem, convert that non-linear basic problem into the linear problem. The solution of that linear problem or integral equation is named as the mild solution of our given system. First, we convert the given system into the some non-linear problem, that is integral equation. Then using the fixed point theory or approximate controllability, we can find the solution of that linear problem or integral equation. The solution of that integral equation is named as the mild solution. And finally, we use the Krasner-Selsky fixed point theorem, which already defined the Krasner-Selsky. We apply all the conditions. If our given system satisfy all the conditions of the Krasner-Selsky, it means we can apply this Krasner-Selsky fixed point theorem. That means for proving the existence of mild solution approximates controllability, we require the following assumption. These are the assumptions which are to be required. And then control function is to be defined for this one. Then come to the part of the result one. In first result, we would like to find the mild solution. This is a mild solution. There are different steps to get the mild solutions. Then come to the part of the next result by using the sub-law approximate controllability system. The sufficient condition for the existence of the mild solution, the approximate controllability of the class of non-densely defined. These are the references. Hanji sir.
Thank you, sir.
Thank you very much.
For your nice presentation.
Thank you very much.
Yes, sir. So you have covered point theory, control theory, and its applications.
Yes, of course,
okay.
Of course.
Yeah. Now time for questions and answers. Right. So any questions from the audience? Okay, thank you, sir.
Thank you very much.
Presentation. Yeah, thank you. Once again, I thank on behalf of the organizers
for accepting your lecture in this seminar. Thank you.
Thank you very much for giving me opportunity. Thank you very much.
Thank you, Professor Muniswamy Garu, and thank you very much for Ramesh Kumar Award, sir. Now, sir, I would like to invite the Professor P. Muniswamy Garu. Taking the first. Sir.
I'm running. Yes.
Thank you very much, sir. Now, the next invited talk is Professor Dhananjay Gopal, sir. In this talk, Vishnu and Vishnu sir taking a share of this session. I would like to invite to Professor Vishnu and Vishnu sir. Please take this session. Sir.
This is the one. You can make it large. This is section. Okay. This is first one. Okay. This is next one. Okay. Next one. Okay. Next one. Once I share the screen. Yeah.
Sir, please do.
Next.
Hari Om, Jai Sri Manaran, a very good noon to all of you. Now it's time for next speaker. That is the next speaker is Professor Dhananjay Gopalji, and we worked with jointly at FVNIT Surat. I joined FVNIT Surat in 2007 as the assistant professor of mathematics after completing my PhD program from IIT Roorkee in 2007. And Dr. Gopal joined as assistant professor in the IIT Surat, that is Sardar Vallabhbhai National Institute of Technology, Surat in 2009. And we worked together from 2009 to 2017. I left IIT Surat on 31st May 2017 and joined here IIT Amarkantak as associate professor. Professor Gopal left IIT Surat on 2020, and he joined as associate professor of mathematics in Guru Ghansdas University, Bilaspur. And brief profile, that is Dr. Gopal research focuses on algebraic topological fixed point theory and fuzzy analysis with possible applications for solving differential and integral equations, along with utilizing the fuzzy analysis and the related fixed point theorems in quantum mechanics and computer sciences. Professor Gopal, visiting professor, also University Jaén, Spain,
in 2023. And Professor Gopal education qualifications are that 1997 he did BSc from Guru Ghazidas University, Bilaspur, and 2001 he did MSc from same university, and 2006 he did PhD from Guru Ghazidas University, Bilaspur with Professor A.S. Randivendra, and this thesis title on some fixed point theorem. And he was also awarded 2009 Young Scientist Award NKMC Conference Chhattisgarh, India, and he is also gold medalist in MSc Mathematics. And he completed his CSIR project, and the title Study on Fixed Point Theorem for Single Valued and Multi-Valued Mappings and their applications to best approximation. As I told earlier, he did job of assistant professor of mathematics in Sardar Vallabhbhai National Institute of Technology, Surat, from 2009 to 2020, and he has published a very good number of papers, 125 research articles in esteemed journals, and his citations, number of citations, 1,810, and he has gained H index 24 and I-10 index 56. So we invite from this organizing committee a renowned mathematician, Professor Dhananjay Gopal, to deliver his talk on the title that is Solution to the Roads Problem under Minimal Metric Structure. So Professor Gopal.
Good afternoon to everyone. Thank you very much, Professor Mishra, for introducing me. And I also thank to the organizing committee. That is a very nice moment for me to be here and at least to see and have interaction with so many legendary professors. One of is Professor K.P.R. Sastry, and I remember that I tried to mention that I read his paper nearly he has written or published during the 90s with the orbital continuity that is related to the non-unique fixed point. It is in the Indian Journal of Pure and Applied Mathematics. This is like a motivation. So thank you very much once again. The title which he mentioned is somehow I missed, but the main thing is the same. So as we work in the fixed point theory. So the idea of the today presentation is to somehow, there is a experienced person or the mathematician, and the other is the research scholar. That means those who are pursuing PhD or those who are about to complete. So this is somehow related to maybe not for the experienced one, but for the research scholar, in the sense that Professor Raj Sekhra mentioned very well that if you are attending any conference or workshop, if somehow we can have some inspiration or some problem to work on, and if somehow we can do it and it is published, then it will be really the real outcome of that the meetings or the attendance. So that is the main purpose. So before starting my table of contents, yesterday Professor G.V.R. Rao Babu, he has completely introduced starting from the idea of Banach contraction principle, is various generalization and fundamental generalization. So especially there is the two parts we can say in any mathematical theory. One is the theoretical part, and other is looking for the application part. So sometime even the mathematical part has some interesting consequences. So starting from, so I am writing in a short. BCP stand for the Banach contraction principle. So as I mentioned that this has been somehow extended or generalized. So I am writing this is a Cannon map. So this is the R Cannon. So this is this is everyone know 1922 and this is a 1968 paper. So this is the one paper which tells that the simple idea that every complete metric space with a particular contractive type mapping admit a unique fixed point. That is the Kannan map. Okay. But Kannan himself was not knowing that there would be some nice property that has been already mentioned by the Professor G.V.R. Babu. So what properties later on introduced is the following. In 1975, Professor Subramaniam from IIT Chennai, he showed that. So what is the Kannan mapping? What is the Kannan theorem is that every Kannan mapping in a complete metric space admits a unique fixed point. What the Subramaniam shows that, he shows that the characterization of metric completeness through Kannan mapping. So that is an interesting property, you see. Well, that's I mentioned that even the Kannan, Professor Kannan, but might not be knowing that there would be a characterization of the completeness of the metric space. So what is the point is that in some sense we have to be also very much try to look at the analytical properties of the theory itself. So this is the one. The other one inherently inside was this was the first operator or the mapping in the sense that it admits a fixed point, but the mapping may not necessarily be continuous. In contrast to the Banach contraction, which is more than uniformly continuous. At least it is of course it is more than uniformly continuous. So Professor G.V.R. Rao Babu mentioned about the Rhodes. He was legendary fixed point theories. Most probably, the same era with Professor K.P.R. Sastry. Professor Rhodes died, I think, 2 or 3 years before. So he studied contraction conditions. Initially, he studied around 25 contractive conditions. And he published in the Transaction of American Mathematical Society. This is around, I think, in between the 80s. I exactly do not remember the year. And what he found is that all the contractive conditions that admits the fixed point, but none of the operator was discontinued at fixed point. So this property of discontinued at fixed point, he posed a problem as an open problem that is it possible to find out an operator or a theorem which the mapping which admit a fixed point, but that point should be discontinuous. That was the open problem. So what is the purpose of today's talk is that, so now we can see that, I don't know whether it is visible or not properly. So discontinued fixed point in a metric space, that is the main purpose of today's talk. And at the end of the talk, there is a one problem which we can we can think over. So in 1998, Professor Pant. So what is happening and what is the problem? The problem is in the metric space, find an operator set E in such a way that it should satisfy some conditions, some contractive type conditions, and admit a fixed point. So call it any point to be a fixed point. Suppose this is a fixed point, but at this point, the mapping T remain discontinuous. So that is the problem. And what is the story behind is that if we talk about even the Banach contraction principle and any generalization of Banach contraction principle, so we have only one kind of inequality, and it has a generalization. One of generalization is I am purposefully mentioning it. That is called the Boyd and Wong. So this function phi has to be some property. Some property. If in the case it is a lower semi-continuous, or if it is continuous, then it's a very nice one. So then we can get this constant k. So what I mean is that any generalization of Banach contraction like this one, this should not be any arbitrary. This should have some property so that we can prove the fixed point theorem. So in all this process, we have only one kind of inequality. So the question was, find out an operator or mapping which admit a fixed point, but that point remain a discontinuous. So in 1998, Pant solved the problem posed by the roots. And you see, we will come to, please, next slide. Again. Next slide. Again, next slide. Okay. So we will use some notations, but mostly I will try to explain what is the main problem and what is the solution. So the solution is something like that. We can think, we can try to imagine that how Professor Pant thought about this idea. What he did is that he did it. There is another contraction that is called the Meyer-Killer contraction. That is epsilon is strictly less than dxy is less than or equal than epsilon plus delta. This will imply dx dy is strictly less than epsilon. This is sometimes called the strict Meyer-Killer contraction. So this is more general than this one, even this one. So what, again, in this case, this delta is a function from positive real numbers to positive real number. It should also have some property. I remember that there is a very nice paper by Professor I.H.N. Rao in around the 90s that first time shows that this delta should have at least either the non-decreasing or lower semi-continuous. That is a legendary paper, we can say. So in all these cases, this either the delta or the phi should have some nice property. If we take it as an arbitrary, then we cannot guarantee it for the even the existence of a fixed point. So Professor R.P. Pant, what the idea was that he took it as a combination of these two inequalities, two type of contracting, and what, so he is taking more than one, but at the same time, if you are taking more than one, that means we are in advantage, but then there is no way to do it. But what is the, what he has considered another way is that he did not impose any kind of the restrictive condition in the function, either the p or delta. He only took the two kind of combined the operator or the inequality, and he proved that yes. With this, he proved that yes, we can prove existence of a fixed point if an unique fixed point, and this fixed point remain a point of discontinuity. So look at this, the idea. So he proved this theorem 1.01. This with mxy is the two term. He has in his first paper he used only two terms: x fx, y fy. Distance between x fx and y fy. So he used, you can see 1 and 2, the two different conditions. This is, the first one is like this Boyd and Wong kind of contractive map, and second one is the Meyer-Killer contractive map. Okay, please, next. Okay, so Professor Pant provided an example that he showed that yes, this is an example where this mapping satisfies both the condition. In fact, all the conditions of the theorem, and it admits a fixed point, and the point is a discontinuous point. So his paper is published in Journal of Mathematical Analysis and Applications. Okay, sorry. Just one, please. So I have to go back. How to?
Sir, the down one is back. The down one. Sir. Sir. This is the back. Sir.
Okay. 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 Yeah. How to do the next? This one.
Next one is this. Previous one is this.
Okay. Okay. Sorry for disturbance. So this is the result given by one initially with the two terms. You know, but again there was a question whether we can increase these two terms either by the three terms or four terms or five terms. So there are only the maximum is the five terms. So in 2017, he again generalized his result. He introduced instead of two terms, other terms also, which is published in Mathematical Analysis Application. Okay, so what is the purpose of today is that there is a this problem has solved for the metric space. There are the generalization of metric space in the sense of weak. In metric space, we know that the triangle inequality is the most important point. So there are other the weaker form of the metric. One is the P metric, and there are others. Now the question is that is it possible to have a kind of minimal metric structure, and the same this problem has an answer in that metric structure. So in 2020, we introduced the idea of what we call, actually we have not introduced, the other has been introduced only. We studied the topological properties, that is called the non-triangular metric space. So in the non-triangular metric space, there is a mistake. This has to be x is equal to 0, instead of 0 it has to be y. dxy is equal to 0 if and only if x is equal to 1. So we can see that there is a the property, the third one is a something like a convergent sequence, and we don't have a triangle inequality. So the point is whether the problem of discontinuity at fixed point can also be solved by weaker form of metric structure. So we have done this one, and so this is the idea of the non-triangular metric space, and then we formulate it. So these are the terms which is important. The first one is small mxy having two terms, capital mxy having 1, 2, 3, the fourth term, and there is a star, m star, double star xy having other kind of the terms. So we have this is the other one, mxy, which means this 1, 2, 3, 4, 1.0.2. So we proved the theorem in non-triangular metric space with this property, which is a property we call CC, and with this one we proved that the problem has a solution in non-triangular metric space. And in fact, it is very difficult to find out the other weaker form of metric structure having the same solution. If it is so, the metric has to be coincide, or the properties of metric has to be coincide. So this is the weakest one, the non-triangular metric space, the weakest one, where we have the solution for the discontinuity at fixed point. So this is the one theorem where we have used capital mxy, and this is a example. In this example, you can see how we have defined the distance. It is not a classical metric. It doesn't satisfy the triangle inequality. So there is a crux in this idea that without triangle inequality, it has a solution. So these are calculations of our example. Now this is a one corollary. We can get it m1xy. So I'm skipping a few more things. This is okay. This is the important one. In the following example, we'll see that if we consider this term in the previous theorem, that means in our theorem, then it is unable to guarantee fixed point result by observing that the Picard sequence is not an even Cauchy sequence. So look at the importance of this term 1, 2, 3, 4, 5. If you consider the 5 term, then it is not necessary that even we have the fixed point. So what is the next? That is the example which talk about that. Okay. In the following example, we'll see that if we replace M1xy in the theorem 1.0.6 as mxy, then it guarantees the fixed point for the usual metric. But it does not guarantee a fixed point for non-triangular metric. In fact, for the B metric. For metric, it will, okay, we can find out the fixed point. But if we try to weak somehow the metric, it is not possible. That is an example. So the terms are very important, how much term we can take and how much term we cannot take. It seems very simple at this moment, but if we really calculate and go for the research, if we go for the calculation, it is very, very hard to get the example, counter example. So then we have another aspect of the last two example tells that in this case it is not possible. In this case it is not possible. What are the most possible situation where we can do it? So this is, you can see that we have the term. This is something like the fourth and fifth term is something like the rational kind of inequality or the rational kind of terms. So we use it and then we prove the theorem. This theorem, which is the solution of the Rhodes problem. And this is the corresponding example. This is continuation. This is the corollary. That means the previous result we generalize. These are the previous result we generalize. Now, what is the conclusion I can say is that there is a very unnoticed, or maybe I don't know, it is noticed, but I search and then find only few things. In 2003, Journal of Mathematical Analysis and Application by W.A. Kirk, he introduced an idea of asymptotic contraction. Asymptotic contraction. And in this paper, he proved that some kind of the asymptotic contraction has a unique fixed point, and the proof is a very non-constructive, completely non-constructive, in contrast to all those proofs of fixed point theorem related to the contraction. Chomsky actually improvised the Kirk the proof, and he has some remarks related to that. So only I found that the 3% work on this idea, all is published in Journal of Mathematics. Kirk first, 2004 Chomsky, and 2006 and 7 Suchki. So what is the role of this asymptotic contraction at this moment is that for the research scholars, what we have done, the solution of the Rhodes problem, okay. Solution of the Rhodes problem, we have considered with kind of the two inequalities, like a Ward and Wong kind of contraction and mere killer kind of contraction. Now the question is whether this one or this one can be replaced by asymptotic contraction. Okay, yeah. Whether this one or this one can be replaced by asymptotic contraction. If it is so, then it shows that we have a new solution to the Rhodes problem. And it seems to that our paper is recently published, which I discussed in the Journal of Analysis. If we can find out a solution, this new solution, then we expect that it is a good one. And the last,
Is that a unique?
the-
Is there a unique solution there? Or is a multiple solution?
no unique solution.
And it is not constructed.
That one, no? Constructive in the sense the proof is used the diametrical idea in the sense that something like in fixed point theory. I will show another one. So in fixed point theory, the proof of Banach contraction we start at the one point and then keep pushing and then prove that the Cauchy sequence like that. But the asymptotic contraction is a contraction in a different sense. Even it is not necessarily non-expansive. That is the biggest, completely different. So if it is completely different, it seems that the proof style should not follow in the same way. So therefore, what I mean the non-constructive, that is very technical. It has unique fixed point. So that is the one for the research scholar. If we can look at whether we can use a kind of asymptotic contraction or not, that we don't know. The other one, which I would like to take only 2 minutes, in the sense that what I am going to just show is that recently I found a very interesting paper. It is published in 1990 from one American mathematician, an alternative proof of all kind of contracting methods. So there is a one way to Banach contraction as usual. There is another one which is the Cantor intersection theorem, but this is another one. I don't, it seems to be very unnoticed paper. So therefore, what is the idea is that for the research scholar, which we are working in this area, we should also try to focus on what kind of alternative proofs, whether it is available or not. So instead of doing many proof, for all contraction, you take it only one way. You can prove for all. That is, I only wanted to show, and then I will finish it. और मैंने भेजा था इसको क्लोज कर दूं इसमें और कुछ है ना पीपीटी को छोड़ के एक पेपर हाँ another file can you open it no that is not next one other one this one only okay you can take it then can you
No.
okay this one okay these are not but okay you can open that the last one the PDF issues one here they're in there this one open it and then just make it
Downloading.
This one is it downloading so it is downloading it will take only half a minute yeah you can make it big this is you can try it big that is the paper by Joseph and other people alternative proof of alternative approach to proof of contraction mapping and fixed point. It is published in some journal it's an upside but the year is 1990. It's very very interesting and very simple idea. So this is the motivational paper which we try to read who are working in the fixed point theory. So for the today, it was the two motivation. One was look at for this problem, and other one is that this is also a very nice idea. Somewhere we can, so many result has been introduced by Professor G.V.R. Babu. I think we can follow this technique again to prove this, give the alternative proof of those results. So these are the two particular motivations for the today. So thank you very much.
Thank you, Dr. Gopalji, for your nice presentation. Dr. Gopal discussed asymptotic contraction and discontinuity at fixed point in the metric space, discontinuity at
fixed point in non-regular metric spaces, similarly asymptotic stability, asymptotic expansion, and in approximation theory we also derive Gurunaskaya type asymptotic formula also. So very much thankful to Dr. Gopal for presenting his thought with this nomenclature file. Let us thank his speaker once again. Any questions from audience, please? किसी को कोई प्रॉब्लम हो गई समझ में ना आया हो या कोई डिस्कशन करना हो तो यू कैन डिस्कस विद डॉक्टर गोपाल इन लंच पीरियड आल्सो so thank you very much Professor Vishnu Mr. sir let's conducting of the Dhananjay Gopal sir now I would like to invite the Dhananjay Gopal sir please take a honor of fellowship. Thank you very much, Professor. Now, before starting the presentation, the last session of this morning spell, ASV Ravikant sir, offline.
Offline, he missed his flight.
Online. Ravikant Mishra, ASV Ravikant sir is online now. I would like to invite Professor G. Nanajirao Garu. Please conduct this invited talk from the ASV Ravikant sir. Hello. Sir, Ravikant sir?
So I'm not just
Hello.
Yeah, please.
Is it ASV Ravikant sir?
Yes. Namaskar ji.
Yeah. Sir, first of all, I thank the organizers for giving me an act as a chairperson of the invited speaker, Dr. ASV Ravikant. Dr. ASV Ravikant is an associate professor from NIT Kurukshetra, and his area of interest is numerical analysis, numerics of Euler differential equations, fractional differential equations, numerical methods with analysis, and singular boundary value problems, and
he published 61 research papers in both the national and international reputed journals. And under his able guidance, 4 PhD students were awarded and 2 MTech students are awarded under his guidance. And he gave 12 invited lectures and completed 4 major research projects sponsored by NBHM, DRDO, and he served in different administrative positions like head of the department and served as a professor in examinations, professor in charge in examinations, professor in charge in academic examinations, and etc. Now I invite Dr. ASV Ravikant sir to give his lecture on computational simulations for a class of fractional partial differential equations. Sir, please give your lecture on this topic.
Thank you so much, Professor. At the outset, let me thank Professor Srinivas Rao for inviting me for this talk. I'm extremely sorry. I thought of to come offline. Unfortunately, there is a reschedule in the flight, and that flight may reach today in the afternoon. So then I thought, let me come back, Kurukshetra, and join the meet through this online. Thank you, Srinivas, to give me to share my thoughts towards my recent works on fractional calculus, especially in the fractional partial differential equations. So, 1 minute, let me share my screen. Is my screen is visible?
No, sir, no.
It's not visible. 1 minute. Hope it is visible now.
Just a minute, sir.
No, sir, no, sir.
Lecture
I think it should be visible.
Yes, sir.
Yes, sir. Now it's visible.
Yeah, my talk related to the computational simulation for a class of fractional partial differential equations. Before proceeding to actual content, let me emphasize towards fractional differential equations and why we need to go ahead with these fractional concept towards differential equations. In fact, fractional differential equations are a type of differential equations that involve derivatives of non-integer order. While ordinary differential equations deals with the derivatives of integer order, fractional differential equations extends this concept to include derivatives of non-integer order, which have proven to be useful in modeling various phenomena in science and engineering. Few reasons say, for instance, modeling complex phenomena. These fractional PDEs provides more flexible framework for modeling complex systems with memory effects, anomalous diffusion, and long-range interactions. In fact, they can capture phenomena that cannot be adequately described by classical integer order differential equations, such as we can say non-local interactions, power law behavior, and factoral phenomena. These things it is difficult in handling in normal differential equations. Not only that, memory and heredity effects, these can be very useful properties These things we can see by incorporating fractional derivatives. We can see inherently incorporated memory effects, which are essential in modeling systems with memory or hereditary properties. These systems can be included, say, for example, viscoelastic materials, fractional order control systems, and biological systems with memory. When we are discussing about the diffusion process, in many natural processes, particularly in physics, chemistry, and biology, diffusion does not allow classical laws, which is described by integer order differential equations. Whereas fractional differential equations provide a powerful tool for describing enormous diffusion phenomena observed in complex media, such as porous materials, biological tissues, and even in the disordering environments. There are many areas we can see in these enormous diffusions. When we come across to the field of signal processing and image processing, fractional differential equations have quite few applications, particularly in diagnosing, enhancement, and future extraction of tasks. Fractional order operators can be provided better results in processing signals and images corrupted by non-Gaussian noise or with long-range dependency. Even earlier speaker, he talked about the fixed point theorem utilization in the control theory. In fact, fractional order control systems have gained attention due to their ability to achieve superior phenomena compared to classical integer order control systems. Fractional differential equations used to model these systems, allowing for the design of controllers that can achieve desired phenomena specifications more effectively. When it talks about the biological applications, in modeling various biological systems, including neuron dynamics, population dynamics, epidemiology, these fractional differential systems captures the complex behaviors of biological systems more accurately, leading to better understanding and control of physiological processes. In fact, when we go for fluid dynamical systems, these fractional differential equations, nowadays people are using it, and they are modeling complex fluid flows and mechanical systems such as a porous media flow, viscoelastic fluids, and fractional order mechanical systems. There are many other systems people are working in this. These models, in fact, provides insights into the behavior of these systems under different conditions and can lead to improvements in design and optimization. At the outset, I can say fractional differential equations plays a crucial role in extending the classical theory of differential equations to better describe understanding complex phenomena across various scientific and engineering applications. They offer more flexible frameworks for modeling systems with memory effects, allows behavior, non-local interactions. Not only that, leading to advancements in theory, computation, and applications. In fact, let us see now. Slides are moving. Whether slide is moving?
Yes, sir. Yes, sir.
Okay. Now my talk goes. Let me first briefly discuss about what is fractional calculus. Then we'll see the history of the fractional calculus. Let's see few advantages what fractional calculus provides us, and if time permits, I'll touch upon my recent works with my students. Let's see what is fractional calculus. In fact, we all familiar with normal derivatives like dy by dx, d square over dx square. In fact, integral 0 to t du. We have first derivative, second order derivatives, or first integral, double integral of a particular function. Now we wish to have half derivative, pith order derivative, or I can say 3 minus 6th derivative of a particular function. Means fractional calculus means derivative and integrals of arbitrary or real complex order. Does it make any sense, or just a mathematical fantasy defining the fractional derivative and the integral concepts? How to calculate half derivative of say a function? Let us say f of x is equal to x. This seems to be recent stuff. How old it is? There are many questions in our mind. Does it have any physical interpretation, geometrical meaning? Why we have to study it? How it is important in engineering? What's the deal? How much serious research is going on in the community? What are their applications? So should we discuss should we discard the integer order derivative? These are all few questions in our mind the moment we say going for arbitrary order or the real or complex order derivative. Now when we go back to the history of this fractional calculus, as we know, as old as normal conventional integer order calculus. In fact, it was born on 1695. A letter correspondence between El Hospital and Leibniz. What if order of derivative is half? In which Leibniz replied a beautiful answer to him. One day it definitely has apparent paradox from which we can see consequences will be drawn in future. Means this particular letter was communicated in between Leibniz and the El Hospital in 30th September 1695. So we can say 30th September 1695 is the birth of the fractional calculus. Subsequently, there are many mathematicians like Leibniz, Euler, Lagrangian, Laplace, Fourier, Levy, Abel, Riemann, and so on. There are many mathematicians, they contributed towards fractional calculus. In fact, the first international conference was conducted in USA in June 1974, fractional calculus and its applications. In fact, there are 15 textbooks so far available in the fractional calculus. In 2004, first time, there was an international conference conducted by the International Federation of Automatic Control, IFAC, and it is regularly, every alternate 2 years, they are conducting a conference, fractional differentiation and its applications. As on today, more than 6,000 research articles published in the same single concept on fractional differential equations. Means, in fact, there are many renowned Indian fractional calculus professors, they are working in this area, like H.M. Srivastav, Loknath Devnath, Lakshmikantam, Saxena, Maiti. There are many other people are working in this area from our country. Rigorous mathematical theory has been developed so far. Integer order calculus is a special case on this. In fact, the geometrical interpretation or the physical meaning, there exists, but not as straightforward as when we see in the integer order derivatives. As I told, there are more than 15 definitions of fractional derivatives available so far. For instance, let's pick n is an integer, a to the power of n. How do we calculate? A will be multiplied on n times. So suppose if n is not an integer, for instance, n is half, means a to the power of half. How do you express a to the power of half? A can be multiplied half times, can we write? Means calculating a fractional derivative is similar to the problem of defining or giving meaning or interpretation to a to the power of in case of n is not a positive integer. I'll pick two different functions and then see what happens the arbitrary derivatives for them. For suppose, as we know, x to the power of n is a simple, beautiful power function. Let us calculate its nth derivative. When we calculate nth derivative of x to the power of n, it gives simply n factorial. So nth derivative of x to the power of m. Here, the beauty is n and m. Both are different integers, and the restriction is m greater than n. Then what could be the nth derivative of x to the power of m? We can easily find out m factorial divided by m minus 1 factorial times x to the power of m minus n. In fact, we know a gamma function. Gamma function defines gamma m plus 1 is nothing but gamma, m factorial. Now we can utilize this particular fact. M factorial can be replaced by gamma m plus 1, and m minus 1 factorial that can be replaced by gamma m minus n plus 1. So nth derivative of x to the power of m, we can easily see gamma m plus 1 divided by gamma m minus n plus 1 times x to the power of m minus n. Here m greater than n. Now for any arbitrary alpha, real or complex, alpha may be real or complex, we can define a note saying that alpha the derivative of x power n can be easily defined. It is displayed here. Now let us pick out an exponential function e to the power of ax. Here let's find out nth derivative of e to the power of ax. It is simply a power n e power ax. So for a arbitrary alpha, real or complex, we can define alpha order derivative of e to the power of ax is a power alpha e power ax. Now we'll utilize these two properties in subsequent slides to define the fractional derivative. In fact, we can extend the idea for the fractional derivative to a large number of functions. Say, as we know, the Taylor series expansion in powers of x for the function f of x is defined sigma n 0 to infinity a n x to the power of n. Now, for arbitrary alpha, here alpha is every time I was saying alpha is real or complex. Let's define and assuming what happens to the alpha the derivative of f of x. You can take the term differentiation inside so that we can catch hold its definition. See d power alpha x power alpha of x to the power of n means, as we have seen in the previous slide, the alpha the derivative of x power n in terms of gamma function. So this has been given lively in 1832. Next, as we know, the Fourier representation of a particular function, which is defined f of x, and g can be defined as in this expression, with this expression. Now let us generalize this. Alpha the derivative of f of x, this can be expressed 1 divided by 2 square root pi integral minus infinity to infinity g gamma. Alpha the derivative of e to the power of exponential function we have seen in the previous slide. We can utilize that same concept. So a is looking like minus I gamma. So a power alpha times e to the power of I gamma x d gamma. This definition is provided by Fourier in 1822. Now we can see the paradoxy between both the definitions. Let us see simple example and let us see when we use these definitions what happens. If I use exponential function approach, I just want to calculate half derivative of 1. What happens? We can write e is 1 you can replace at e to the power of 0x. half derivative of e to the power of ax. Now you 0 power alpha, 0 power half, alpha is half here, e to the power of 0x. Now this gives you 0. Means half derivative of a constant. When we are using the exponentially function concept, we got 0. Now let us see a paradox. When we use power functions approach, half derivative of 1 we can write again x to the power of 0. So as we have seen in our previous slide, alpha derivative of x to the power of n, that we can write it a gamma function. So gamma 0, here n is 0, gamma n plus 1 divided by gamma n minus m. M is alpha half here, so 0 minus half plus 1, x to the power of 0 half. So we just see we got 1 divided by square root of pi x. There is a paradox. One we have taken a function. The moment we use the concept of exponentially function approach, we got 0. And the half derivative of 1, we got 1 by square root pi x while using the power function approach. So there is a paradox. Now, sorry. There are, as I told you, in the literature, we have more than 15 definitions are available. Out of them, popular definitions are few. I just picked 3 different popular definitions, and then we'll discuss on it. Lacnico fractional derivative, which is defined in 1890, which is given in this expression, and the properties when we see constant derivative of Lacnikova derivative, we get c divided by gamma 1 minus alpha, and it holds the linearity property and correlation property also. Another popular definition is Riemann-Lively fractional derivative, which is defined in 1832, and fractional derivative, you can see mth derivative of an integral. If we are using this concept, let us see the few properties on this. What happens a constant derivative? In fact, a constant of the Riemann derivative, we don't get 0. Similarly, few properties also you can see. Sorry. When we see the Capito fractional derivative, one of the popular derivative, and you can see the definition of Capito derivative, which is given in 1969. Till people are using this because of constant derivative of a Capito sense, it is a 0. It holds all the regular properties like linear property and other properties. Now let us see what exactly we have noticed from this fractional derivative. Definition of fractional derivative involves an integration. And integration is a non-local operator as it is defined on an interval. Means fractional derivative is a non-local operator. Now calculating time fractional derivative of a function f of t at some point requires all the past histories. That is, all f of t's from t0 to t1 are required. That is what we have seen in the previous definition. Means fractional derivative can be used for modeling systems with memory. Another beautiful thing is, if I'm calculating space fractional derivative of a function f of x at a particular point x is equal to x1, this requires non-local functional values. Means fractional derivative can be used for modeling distributed parametric systems. So fractional derivatives can be used modeling system with memory and modeling distributed parameter systems. In fact, differential equations involve fractional derivatives. They're all known as fractional differential equations. We can see either in the case of ordinary differential equations or partial differential equation. These equations may be linear or non-linear. In fact, existency and uniqueness of solutions, they are well established. Analytical solutions are a bit difficult to evaluate. So dedicated, elegant numerical methods existed in spite of its long history, fractional calculus was not considered eligible for any applications. That's a earlier story. This was due to high complexity and lack of physical and geometrical interpretation. Applications of fractional calculus to real problem is only just a 4 decade old. Now there are many mathematicians, applied mathematicians are working towards applications of these fractional derivatives. Now I will pick a simple diffusive equation where we have encountered with the fractional diffusion equation together with impulse function as input. Say initial condition is ux0 is equal to an impulse function. It is 10 when x is equal to half, otherwise it is 0. With homogeneous boundary conditions, u at 0t equal to u1 0t is 0. Now when we apply a simple fractional derivative concept, let's see how solution is attaining. When we see right hand side, if you see alpha is equal to 1, means it's an integer order case, we can easily notice solution is diffusing very long. Time is taking large. Whereas when we count alpha is equal to half, means when we counted in a fractional case, we can easily notice diffusion is very fast. In a shortest time, it is diffusing. In fact, we have taken impulse function that can be easily noticed. It impulse is 10 when x is equal to 0.5 and it diffusing very fast. In the case of a fractional derivative, half derivative I have taken and you can see it diffuses very fastly. Even 0.75 diffuses very fastly. Exact if you are taking the integer order, diffusion is very slow. This is one beautiful application we can easily study with the fractional derivative. Not only this, we can see the stability analysis. In the stability analysis, for example, if I consider a differential equation with an initial condition x naught, say x dash is equal to mu times t power mu minus 1. Its solution easily we can calculate. It is t power mu plus x0. In fact, mu lies in between 0 1. We can easily say the what I can say the solution is unstable. When we go for the fractional case, say fractional derivative is equal to mu times t to the power of mu minus 1. Here gamma is lies in between 1 and 0 and 1. Its analytical solution is mu gamma mu t power mu gamma minus 1 divided by gamma mu plus gamma.
Welcome, sir.
Sir?
Last 5 minutes.
Okay. I'll wait. Another 2 applications I'll show. Plus, in fact, this solution, when we consider the differential equation with fractional order, it is stable. Means we got the stable solution. Under the limits, mu has a restriction 0 to 1 minus gamma. Not only this, and you can see the differentiability. Let us pick a simple example. X is 1 minus t in the interval 0 to 1 and t minus 1 in 1 to 1 plus epsilon. See, at 1, this function is not differentiable. In fact, at 0, it has first derivative is existed, but at 1, derivative is not existed. When we encounter the fractional sense of this particular function, derivative is existed at t is equal to 1. This is another advantage while counting the fractional derivative. Let me go through our contribution. Briefly, I'll explain it. This work with my Neetu, one of my research scholar. Right now, she is working in NIT Calicut as an assistant professor. And here we have considered a time fractional reaction diffusion equation. Most of the people, researchers, are replaced the differential equations with the finite differences and other methods. The fractional term, most of them, they have utilized the Capito sense. Even we also used the Capito sense. The finite difference replacement for the fractional derivative at a point tk, they have identified, and it gives the order of t minus 2 gamma that is given in this slide. where BN is, it is in terms of gamma. So most of the researchers, they used this particular definition, and the complete scheme is many times it is conditionally stable. What we proposed in our whole research with my 3 students in earlier works, what we did, instead of discretizing the function at tk, we went for a discretion at tk plus 1, k plus half, means half the point derivative we have calculated, and we discretized the capital definition. We got the discretization equation 4. With this discretization, what we did, we went for we have taken our reaction diffusion equation at half derivative, means we used the Crank-Nicholson scheme on time level. So when we use the Crank-Nicholson scheme on equation 3, we get equation 5. This equation is here you can say k plus 1th time level solution. We rewrite this entire expression into equation 6. You can see equation 6 is looking like a sequence of differential equations, spatial in spatial directions. It is, if I am putting k is equal to 0, it looks like a second order differential equation in x. One can use any numerical method. In fact, we used the exponentially B-spline method, tension-spline method, and B-splines we have used. And this work, and we proved this scheme is unconditionally stable, and order of the scheme is 2 minus alpha in the fractional order in the time, and 4th order for a specific case. And this work is published in 2020 in the Journal Computational and Applied Mathematics. For rest of the details, one can see from this paper. And the same idea has been extended for multi-term fractional advection diffusion with the variable coefficients. It was published in Numerical Methods Partial Differential Equations along with another. And we have extended the similar kind of work for the multi-term partial diffusion equations. It was published in European Medical Journal Plus with Netherberg. And time fractional equations has been extended with the similar concept with the Netherberg. Time fractional diffusion equation. Another 1 minute. I'll wind up. And you can see some more articles. And if you, these are few articles. These are the books one can refer in this area. I'm done. The main research is now the point of interest is here we utilize the derivative at t plus half. People can utilize any other point and they can enhance the order of the derivative.
Okay. Over, sir?
Yeah, I'm done.
Oh, thank you. So, Ravikant sir, is a nice presentation. And you discussed about the details of fractional calculus and its applications, and also who worked in previously on this concept. We have also mentioned some names of legendary mathematicians, and also explain about fractional derivations on power series. And thank you very much for your nice lecture, sir. Thank you. Okay.
Thank you. Thank you so much.
On behalf of organizers of the conference, we thank you, sir, for delivering your lecture in this conference.
Thank you, madam.
Welcome.
Sir.
Excellent.
Thank you. Thank you so much. I'm sorry I could not able to come personally. I tried.
So next time.
Yeah, sure. Definitely I'll come.
Yeah, definitely your presence is very much required for this type of conferences next time, okay?
Sure, definite.
So meanwhile, just we'll meet in some other platform, okay?
Okay, thank you so much.
Thank you.
Bye.
Other questions, sir? 1 second, sir.
Sir, fractional order is there. Is there any fractional power? While we are defining order and degree of a differential equation, which is free from radicals and fractions. Just you have explained very well about the fractional big order. Is there any fractional power?
Sir, you're on mute, sir.
Sir, please unmute, sir. Yourself.
Yeah, power functions with the derivative, it is nothing but a factoral derivative. That is another concept which is popularizing nowadays. In fact, one of my another student, she is working in the fractional with the factoral order. Means you have a t power alpha with a d by dt of t power alpha. That's what we are asking. It is a factoral order derivative.
Okay.
Thank you, sir.
Right.
Thank you, Nanaji Garu, for chairing the session. Now we will proceed for paper presentations in parallel sessions, online here and offline in the room number 116 downstairs. All of you for offline presentations, please proceed to room number 116 downstairs. Ground floor. Not ground floor, first floor. So here, I request Professor Nanaji Ragaru to please chair the paper presentations offline. Okay? And I request Professor Vinita Madam to please chair the paper presentations online session here in this seminar hall.
ఆన్లైన్ వాళ్ళు అక్కడ ఉన్నారమ్మా చూడండి ఆన్లైన్ వాళ్ళు ఉన్నారా మా ఫస్ట్ నేమ్ ఎవరిది రెడీగానే ఉన్నాము మాధవి మాధవి స్టార్ట్ యువర్ పేపర్ ప్రెజెంటేషన్
Madhavi?
Yeah, ma'am.
Yeah, you can start your paper presentation. Title
Okay,
is a
ma'am.
high numerical approach for solving two fractional differential equations.
Yes, ma'am.
8 minutes time and 1 minute for question. Okay, Nima?
Okay, ma'am. I will.
Okay.
I will share my screen, ma'am, right now.
Screen is not visible.
Is it visible, ma'am?
Just share your screen.
No. Please share the screen.
Yeah, ma'am. I'm sharing.
Your screen is not visible. Share it once
Is my
again.
screen is visible, ma'am?
No, ma'am.
No.
One second, ma'am. I'm trying to do it. Is my screen is visible, ma'am?
No, Madhavi. No. It's not visible. Inka.
Next year.
Madhavi? Or we'll proceed with Archana? Yeah.
Is my screen is visible, ma'am, right now?
Yes.
Okay, thank you, ma'am. Myself, I am Madhavi.
Open your present.
Yeah.
Zoom it.
Yeah, ma'am. Good afternoon, one and all. Myself is I am Madhavi, working as an assistant professor in the Department of Basic Engineering and Dr. EVR and HS Mick College of Technology. So now my paper title is a highly efficient numerical approach for solving two fractional differential equation. The abstract of the paper is this study focus on deriving a solution of Q fractional differential equation. So by using a Q operational matrix, this operational matrix can be derived by using a Q Hermite polynomials. So and also I use the Q fractional derivative in the capital sense. So we establish an operational matrix for Q fractional derivatives. So in this we apply some new applications also. So additionally, we demonstrate the efficiency of our approach by solving the Q fractional Bagley-Torvik equation using the tau spectral method. So coming to the Q differential equations. So these are the classical mathematical equations that involve the Q derivative, which is the generalization of classical derivative as one. Actually, in the 18th century, Euler obtained the basic formula of this Q calculus. After that, Jackson may have been the first to introduce the notations of the Q derivatives and Q integral also. So this Q differential equation has a lot of applications in such as number theory, orthogonal polynomials, basic hypergeometric functions, and other sciences, quantum theory, mechanics, and theory of relativity. So coming to the fractional differential equation, already sir discussed, explained a lot of things based upon this. Ravikant sir explained that previously. So these fractional differential equations are mathematical equations that involve fractional derivative of a function. So introduced that Leibniz and L. Hospital invented this. The fractional differential equation actually rapidly developed in the 19th century and attracted many of well-known mathematicians and different derivatives, Euler's, Riemann, Capito. The fractional calculus is the generalization of classical calculus and integration and differentiation of basically non-integer order. So the fractional differential equation are multidisciplinary and which can be used in electricity, heat transforms, quantum mechanics, fluid mechanics. So fractional differential equations has been used to model spread in infection diseases, the growth of tumors, and the diffusion of drugs through tissues. So coming to my topic, Q fractional differential equation. This is a combining of fractional differential equation with Q special case. So Q fractional differential equations are the generalization of fractional differential equation that involve the Q derivative. So actually this will be developed in the 20th century. Agarwal and Al-Salam developed various kinds of Q fractional differential operators. The Q fractional differential equations are used to modeling the linear and non-linear problems and play an important role. So it has a lot of applications in different applied sciences, various mathematical areas such as number theory, orthogonal polynomials. So the main advantage of this using Q fractional differential equation is in the numerical techniques we will get the series solution. By using of this particular Q case, we can avoid the complexity of convergence complications. So let us go to the preliminaries of this one. I used the Capito type of differential equation. So and introduce that Riemann-Livio also I mentioned here. The Riemann-Livio type of definition of Q fractional integral of a function f of z is defined jq alpha into f of z. So gamma q of alpha integral 0 to z, z minus qt alpha minus 1 f of t dq of t. And similarly the Capito type of definition, Q fractional integral of the function f of z is defined as dq alpha into f of z is equal to 1 by gamma q m minus alpha 0 to z, z minus qt m minus alpha minus 1 dq power m into dq z power m f of z into dq of t. And I used the properties here in my paper. Some of the properties of JQ alpha is equal to, and if you multiply, if we apply integration, JQ alpha is the integral operator. JQ alpha, JQ beta of f of z is equal to JQ alpha plus beta into f of z. JQ alpha into JQ beta of f of z, we can rearrange that JQ beta into JQ alpha of f of z. And the derivative dq alpha of z power mu, gamma q mu plus 1 by gamma q mu plus 1 minus alpha, z power mu minus alpha. And similarly, integration part, iq alpha of z mu, gamma q alpha plus 1 by gamma q alpha plus 1 plus alpha, z power mu plus alpha. And one more important property, Q Leibniz rule for a hello for a Q for a Q derivative. Sorry, hello. For a Q derivative of a product of two functions, dq power m into f of z into g of z. So as mentioned here. So next we will go to the Q Hermite polynomials. The ith degree of Q Hermite polynomials in the interval lambda of 0 to infinity q are defined here, and I consider the orthogonal condition also. And later, this is the important main topic of the paper, generalized Q Hermite operational matrix for Q fractional calculus. So here consider the function p of z in the form of Q Hermite polynomial. P of z is equal to sigma j is equal to 0 to infinity aj into hj of z. So for this, first I consider the n plus 1 terms Q Hermite polynomial. So then Pn of z can be written as sigma j is equal to 0 to n aj into hj of z. So what I mentioned here, small a of j is the Q numberings one here. So here C transpose into pi of z. So C is the Q Hermite coefficient vector and pi of z is the Q Hermite vector and are given by C. Next. So based upon this, here we first consider the derivative, first derivative n by n plus 1 by n plus 1 terms. So here dq1 is the derivative, capital Q derivative. The fractional derivative of a vector pi of z can be written as here dq of, where dq1 of is the n plus 1 is n plus 1 dimensions is given by dq1. Here we can observe most of the we are getting zeros. So this is the complex convenient we can using of this method. Most of the matrices we will get zeros only. So from that it is clear that dq power n into pi of z by dzqn is equal to dq1 whole power n into pi of z. And based upon this we can derive a lemma. Let hi of z be the Q Hermite polynomial. Then dq mu of hi of z is equal to 0, I is equal to 0, 1, comma, and so on alpha. So we can, by the basic definition only, we can prove the lemma very easily. And similarly, we can construct a for Q Hermite vector. Suppose pi of z be a Q Hermite vector defined and also mu greater than 0. Then we can apply the...
With your presentation.
Hello, ma'am.
Yeah, last 1 minute. Just come to conclusions.
Yeah, okay, ma'am. So these are the applications of Q Hermite operational matrix. So consider the linear capital Q fractional differential equation with the initial condition. We can split the function into Hermite polynomial and we can apply the tau method. So we will get the solutions like this. And I applied the Bagley-Torvik equations. So dq square p of z into dq power 3 by 2 fractional derivative p of z plus p of z is equal to 1. So we know the what is the main advantage of this one is we can, for q is equal to 1 and alpha is equal to 1, we can get the normal differential equation. When q is equal to 1, we will get the fractional differential equation. When alpha is equal to 1, we will get the q differential equation. So 3 categories we can justify. So these are the matrix I got it. And converting after algebraic equation by using of the tau method. So I will get the solutions like this, and which is the exact solution. So by using of this is the conclusion. And we will get the, and most of the main advantage, we can apply so many different polynomials based upon this computationally technique. And these are the references. Please, thank you, ma'am.
Thank you, ma'am, for your nice presentation. Yeah, may I call next presenter, Dr. V. Asuni Kumari. If she is ready.
Stop presenting.
Asuni Kumari.
Ma'am.
Yeah. Aswini Kumari, B. Aswini Kumari.
Yes, ma'am.
Aswini Kumari, yeah?
Yes, ma'am.
Okay. What is your title?
My paper title is co-cyclic Jiggy contraction maps in complete matrix space, ma'am.
Okay.
But it did not share my paper. I don't know.
She can't share the paper.
Why? Just you can share your screen there.
Not possible, ma'am.
చూడండి మీకు స్మైలీ పక్కన ఒకటి అప్వర్డ్ యారో ఉంది కదా కింద స్క్రీన్ లో షేర్ స్క్రీన్ ప్రెసెంట్ నా దట్స్ యువర్
మేడం అక్కడ స్మైలీ సింబల్ పక్కన ప్రెసెంట్
యాక్చువల్లీ స్కేర్ అక్కడ షేర్ ద స్క్రీన్ అదే ఇది చేస్తా నమస్కారం
హలో యా లక్ష్మీ దగ్గర ఓకే ఆన్లైన్ థర్డ్ యాక్చువల్లీ ఆవిడ థర్డ్ లక్ష్మీ దగ్గర ఈవిడిలో ప్రొడ్యూస్
మీ స్క్రీన్ ఒకసారి ఆపండి నేను చెప్తాను షేర్ చేయండి
అశ్విని కుమారి మేడం
మ్యూట్ లో ఉన్నారు అన్మ్యూట్ చేసుకోండి
అశ్విని
షీస్ ఆన్ మ్యూట్ మేడం ప్లీజ్ అన్మ్యూట్ మేడం యువర్సెల్ఫ్
అశ్విని కుమారి గారు she left the meeting. I think Lakshmi Dekkala garu is ready. Lakshmi Dekkala.
మీ ప్రెసెన్స్ ఏం రెడీగా ఉన్నారు she left the meeting లక్ష్మి మేడం అవుతుంది మేడం చేయండి మేడం మీరు స్క్రీన్ షేర్ చేయండి ఫాస్ట్ రాస్తున్నారు మేడం లక్ష్మి దగ్గర రాస్తున్నారు ఎవరికైనా ఒక ఇద్దరికి మరీ అది పక్కన కుదరకపోతే ఒక పీడిఎఫ్ చెప్తాను అంటే అశ్విని పెట్టమని చెప్తున్నాను రాకపోతే హలో
Madam, please unmute, madam.
Lakshmi Dekkala garu, please unmute yourself. Lakshmi Dekkala.
Please unmute yourself.
Please unmute yourself. Are you ready for your presentation? Or next one, next presentation, Bhuvaneshwari Dhanala. Is she ready? Bhuvaneshwari Dhanala. BHU. Next B. Harsha Sastri.
Yes, ma'am.
Yeah. Are you ready with your presentation?
Yes, ma'am. I'm ready with my presentation. I'll share my screen.
Go with Harsha Sastri first. The remaining people can get ready by that time. Now I'll call upon B. Harsha Sastri to present an approach to protect data using CANSAC crypto system. You can share your presentation and start.
Ma'am, is my screen visible, ma'am?
It's visible.
Okay, ma'am. Good afternoon, respected dignitaries and madam. Today, myself, B. Harsha Shastri, research scholar from Geetham University, Visakhapatnam, would like to present a paper on approach to protect. So the agenda is about the abstract, introduction, methodology, results, conclusion, and references. So when it comes to abstract, so today in our digital world, data is made available everywhere and we need to protect the data so that it is not in the hands of the third party or intruder who has a malicious intent of modifying it. So we need strong encryption techniques in safeguarding data and ensuring secure communication in the modern digital environment. Robust encryption techniques refer to powerful and reliable methods of encoding information to prevent unauthorized access. And the effective data protection means successfully shielding data from unauthorized users or access. And secure communication refers to the exchange of information in a way that it protects it from interception or eavesdropping. So the knapsack encryption algorithm is the first general public key cryptography algorithm developed by Ralph and Martin Hellman in 1978. So consider a public key crypto system whose security rests on difficulty in solving a certain combinatorial problem. The idea is to encode messages using a scrambled base system in such a way that only the intended recipients can retrieve the message digits or bits. It was invented in 1970 by Hellman and Murphy. So public key cryptography need two keys. One key tells us how to encrypt a message, and the other key allows us to decrypt the message. The decryption code is normally kept secret, so the person who knows the key can only decrypt the message. It is also possible for a person with a private key to encrypt their message, and later on, the person who is using the public key can also encrypt the same. Now, suppose we are given an abstract of volume B belongs to N and objects of volume A1, A2, so on up till AR belongs to N. Then abstract problem asks whether or not it is possible to a subset of AI whose total volume is V. So this A1, A2, so on up till AN are the objects. And if a particular object is belonging to an abstract, we write it as 1. If the object does not belong to the knapsack, then we make it as 0. So the epsilon values will be taking 0 or 1 basing on the object being chosen into the knapsack. And V is the total volume or the capacity of the knapsack. Suppose if V is equal to 20, the knapsack has a solution. Say 20 is equal to, maybe these are the following items I can consider to be placing into the knapsack. So 0 into 2 plus 1 into 5 plus 1 into 6 plus 1 into 9 plus 0 into 13. So these ones indicates that these are the items that are going to be placed into my knapsack. So again, if I take V equal to 23, there will not be any solution to the problem, because if I take the sum of the first four numbers itself, that is 2 plus 5 plus 6 plus 9, which will be equal to 22. And moreover, this is a knapsack problem where you are not going to break any item or take a part of the item into the knapsack. So either I take the item completely or I do not take that item. So which means that if there is a solution, then the epsilon values will be equal to 1. So here I am considering one of the mathematical concept called as a super increasing sequence. So we say that a sequence AI is super increasing an is greater than an minus 1 plus an minus 2, so on up till a1. Suppose if these numbers must be in the increasing order. So if I take the sequence as a1 equal to 3, a2 equal to 3, a3 equal to 10, a4 equal to 20. So this any value if you take, it will be greater than the sum of the previous three numbers. So that is called as a super increasing sequence. So here an important feature of the solution to knapsack problems involves super increasing sequence in that they are unique. So if AI is a subset of n, be a super increasing sequence and epsilon and delta I belongs to 0, 1, then I equal to 1 to r epsilon AI is equal to I equal to 1 to r delta I into AI, where epsilon is equal to delta I for all I. Then we are taking then I is less than or equal to r summation epsilon I AI is equal to summation I less than or equal to r delta I AI, that is equal to modulus of epsilon r minus delta r into AR. So again, since it is summing over I less than or equal to r, so I put those values, and this value is normally less than or equal to AI, and the whole value should be less than or equal less than AR itself. So the total, when I take a super increasing sequence, the sum of all the elements should be less than or equal to the less than AR. So it is relatively easy to solve a knapsack problem using the super increasing sequence. So then moving on to what is my knapsack encryption. So a public key crypto system utilizing the knapsack problem was developed by Murphy and Hellman in 1978. So we are considering the super increasing sequence AI, I is equal to 1 to r, m modulus, m is greater than 2 into AR, and a multiplier a with GCD of a comma m should be equal to 1. And it also computes BI is equal to a into AI mod m. And we are going to publish the encryption key, that is the public key, k is equal to all the BI values. And here all my knapsack values that are going to be.
Last 1 minute, please come to conclusions and complete your presentation.
Okay, ma'am. So here I have followed all the decryption steps also in order to decrypt the code. And here this is a how to make a public key by taking a super increasing sequence. And I have chosen two numbers, say 31 and 110. And these are my public key values which I will be getting, and these are my private keys. So I am taking a message. So since I am having 6 weights here, I am dividing the code into 6, and then I am setting the 3 weights. I am totaling wherever there is 1. I am just totaling those values, and this is my decoded message. And finally, once the decoded messages come, I am dividing it with the n inverse value, which will be equal to the. I am getting back my code once again. I am getting back my original text once again. So this is the implementation I have done using Python language, and the result is also okay. So in the conclusion, I have shown the public key knapsack crypto system, which is providing the data by encryption and decryption. And also for easy knapsack, I have chosen the super increasing knapsack problem. So it is a sequence in which every term is greater than the sum of all the preceding terms. And these are the references that I have collected for my paper.
Thank you, Happy. Thank you very for your presentation.
Thank you, madam.
Thank you. You can stop sharing. You too. Maybe next, Bhuvaneshwari Dhanala is ready. Presentation. Bhuvaneshwari. Lakshmi Dekkala. Okay. Lakshmi Dekkala.
Ma'am, good afternoon.
Hello. Maybe Lakshmi Dekkala, are you ready? Or
Yes, ma'am. Yes, ma'am.
Lakshmi Dekkala. Bhuvaneshwari garu just
Yes,
wait for
ma'am.
another 6 minutes. Let us start with the Lakshmi Dekkala presentation first.
Ma'am.
Lakshmi Dekkala garu, please share your screen and start the presentation.
Yes, ma'am. స్క్రీన్ షేర్ చేశాను.
Start sharing your screen first.
స్క్రీన్ షేర్ చేశాను. PPT
PPT. Yeah.
Ma'am, is it visible my PPT,
No,
ma'am?
no, no, no. Your paper is not visible.
again reshare, ma'am. Stop sharing and again reshare it.
Once again, share your screen.
Now open the
A file open chain with presentation. Zoom in. Pick to screen. కొంచెం పెద్దది చేయండి. లేదా స్క్రీన్ రొటేట్ చేసినా సరిపోతుంది. అట్లా కాదు, స్క్రీన్ రొటేట్ చేసేసేయండి.
auto rotate. Rotate the
ఫోన్ లో
screen.
టర్న్ ఆన్ స్క్రీన్ రొటేషన్ చూడండి అక్కడ. యా యా, ఇట్స్ పర్ఫెక్ట్. పర్ఫెక్ట్. యూ కెన్ స్టార్ట్ యువర్ ప్రెజెంటేషన్ మేడం. రైట్. ఆహా, ఇందాక వచ్చిందే కరెక్ట్ ఉందండి, చూడండి ఒకసారి. అగైన్ రొటేట్ ఇట్. Open your presentation first. Lakshmi Garu.
Yes, ma'am.
Please share once again and rotate your phone. లేదా మీకు కొంచెం ట్రయల్ కి టైం కావాలంటే తీసుకుని భువనేశ్వరి గారికి కాల్ చేద్దాం. ఎందుకంటే 17 members ఉన్నారు, టైం సరిపోదు కదా. Are you able to start your presentation or not?
Yes, ma'am. Please take one.
Ashwiniya. అదర్వైజ్ లక్ష్మి గారు మీరు మ్యూట్ చేసి ఒకసారి మీరు ట్రై చేయండి. అశ్విని కుమారి గారు, అశ్విని కుమారి.
Yes, ma'am.
Share your screen.
We will resume after.
Ashwini Kumari garu, just start your presentation. Your screen is visible to us. Stick to the screen bit and start your presentation. You'll be given 5 minutes time. Better to conclude it now in 5 minutes.
Ma'am, good afternoon, one and half. My name is B. Ashwini Kumari. My paper title is Co-cyclic Jaggi type contraction maps in complete metric space. My main motto is to discuss the new class of co-cyclic Jaggi contraction maps and investing the fixed point theorems, common fixed points theorem in some additional hypotheses, and supporting examples are given to the main theorem, and also generalize the Jaggi contraction maps in co-cyclic contraction. Thank you for giving me this opportunity.
Lakshmi Dekle, are you ready now?
Please unmute me. Madam, please unmute your mic, madam.
ఆవిడెవరు మాధవి గారు వస్తున్నారా లేదా లక్ష్మి
Lakshmi garu, are you ready for presentation? Otherwise, we'll call upon this Bhuvaneshwari Dhanala garu. Bhuvaneshwari. She is not there. Anjaneyulu Naik Kalavat. Anjaneyulu Naik Kalavat. Madhavi Kamdi.
Madhavi garu అయిపోతుంది. Madhavi garu అయిపోతుంది.
Hello, madam.
Yes. Messenger, you may proceed. You may start.
Start.
Messenger, you may start.
Okay, ma'am.
The presentation now. You can proceed now. Start your presentation.
Okay.
Share your screen, madam.
Yes, ma'am.
Vijay Prashansha garu, just please share your screen and start your presentation.
Madam, we can't hear you, madam.
Yes, sir.
The option.
Share your screen, madam.
విజయ్ ప్రశంస గారు చూడండి, అక్కడ స్మైలీ హ్యాండ్ కి మధ్యలో ఉంటుంది స్క్రీన్ షేరింగ్ ఆప్షన్. ఓకే.
Ma'am, is it visible?
Yeah, it's visible now. You can start your presentation. Madam, you will be given 5 minutes time.
Okay, ma'am.
Yeah, please proceed with the presentation.
Ma'am, I'm working as assistant professor in Vishaka Government Degree College for Women. I have done my PhD with the guidance of Professor Kameshwari Madam, Anuradha Kameshwari. Now today's my presentation is about a key exchange with binary quadratic forms. And coming to the abstract, a binary quadratic form f of xy is a homogeneous polynomial f of xy equal to ax square plus bxy plus cy square of degree 2 denoted by abc. This is the short form of our binary quadratic form where the coefficients a, b and c are fixed integers and the variables x and y are restricted to integers. So here Actually, in this paper, we are going to give a key exchange protocol, a binary. So, in this paper, we want to discuss how linear transformations of x and y variables can change one binary quadratic form into other form by a unimodular substitution in the key exchange crypto system. And here in this paper, we have proposed the method for recovering the secret key in the key exchange system using binary quadratic forms. In this paper, coming to the introduction, so the basic concept of cryptographic algorithm works in combination with a key which can be a number, word or phrase to encrypt the plain text to ciphertext. A cryptographic algorithm with all possible public and private keys and all the protocols which make it work comprise a crypto system here. A number of crypto systems have been proposed to maintain the security of the message. The security is maintained by using trapdoor or one-way functions in public key cryptography. So in this paper, the importance and use of binary quadratic forms by the receiver and sender in establishing a secret shared key is discussed, and a method for recovering the secret key by the sender and recipient using the binary quadratic forms is proposed. This method is based on the difficulty of computing the unimodular matrices from the equivalent form. So in this paper, we have used some terminologies called binary quadratic forms and the discriminants and the equivalent forms. And coming to the definition of binary quadratic form, as we have already discussed in abstract, so the shortest form of the binary quadratic form is ABC. If these ABC are co-prime, that is GCD of ABC are 1, then this quadratic form is said to be primitive, or else it is said to be non-primitive binary quadratic form, where the discriminant is given as b square minus 4ac. And one more thing, so when we can say a binary quadratic form is equivalent to another binary, and equivalency can be shown with respect to a unimodular substitution here. So here the unimodular substitution is nothing but a matrix, a 2 by 2 matrix belongs to SL2 of Z. Means what? Unimodular matrix means 2 by 2 matrix with determinant 1 here. So we choose a unimodular matrix PQRS and we'll get an equivalent matrix G of XY like this: AP square plus BPR plus CR square, 2APQ plus B into PS plus RQ plus 2CRS, AQ square plus BQS plus CS square. Now in this paper I want to discuss about the key exchange protocol. Here in this key exchange protocol, our protocol starts with the recipient. First, the recipient sets a random binary quadratic form f of xy of a random discriminant. So D with a random unimodular. These two are random with a random discriminant and also with a random unimodular matrix S equal to P, Q, R, and S. So the binary quadratic form, this form f of xy is the public key and S is the private key here. Now the sender sets an equivalent binary quadratic form G of f of xy using his choice of unimodular matrix S1 and constructs a public key using the operator T. So this is the operator we have framed here. So using this operator, the sender will give you a public key here. So he applied this operator to his binary quadratic form G here. Then the operator is
30 seconds, please present the conclusions.
It is given by T of P1 Q1 of A and T of P2 Q2 of B and T of P3 Q3 of C. It is given as A, which is defined as A plus
Please come to conclusions and conclude your presentation.
P plus P2 into Q2 and P plus P3 into Q3, where these parameters Pi's and Qi's are integers such that Pi is greater than or equal to 0 and Qi is greater than 0. Then finally, the sender. Then the sender applies this operator and again the recipient will give, we have given a new definition for the inverse operator T inverse, and the recipient applies this T inverse operator and he will give this and he will get this G star of X. Thus the sender and the recipient uses the secret key G star of S as a key exchange. So this is the key exchange protocol we have followed by using the binary quadratic forms. And coming to the conclusion, the advantage of this key exchange protocol proposed by us using binary quadratic forms is that an attacker with the public key information G and H star of S finds it difficult to recover the secret key G star of S as to compute the suitable unimodular matrix S from the equivalent form is very difficult and the parameters used in the operator as well. So this is the conclusion of our paper, madam. So thank you for
Thank you, Vijay Prasamsagaru. Thank you. Thanks for your presentation. And next, Kotnuru V.S. Nagalakshmi garu.
Yes, madam.
Yeah.
Yes,
You
madam.
can start sharing your screen and start your presentation.
Okay, madam.
And title of Nagalakshmi garu is Working Vacation Queues with Customer Impatience.
Yes, madam. Good afternoon, madam. Myself KVS Nagalakshmi, lecturer in mathematics, Visakha Government Degree College for Women. I am doing PhD under the guidance of Dr. A. Shaila Kumari, madam.
Start sharing your screen first. Share your screen first.
Okay, madam. Madam, is it visible, madam?
Visible, but can you zoom it a little bit? Font is very small. Zoom. Make okay. Okay. Start your presentation.
Some is it moving, madam?
Yeah, it's visible. It's clear. Start your
Yes.
presentation. You'll be within 5 minutes.
Okay, madam. So, my name is KVS Nagalakshmi, lecturer in mathematics, Visakha Government Degree College for Women. I am doing PhD under the guidance of Dr. A. Shaila Kumari, madam, Associate Professor, JNTU, Anantapur. Here, the title of my paper is Analysis of Working Vacation Queues with Customer Impatience. Here, I will share some few words in my paper. See, in everyday life, we have seen that number of people arrive at the cinema ticket window. If people arrive too frequently, they will have to wait for getting the tickets or some visible, madam. Just a minute, madam.
Yes, man, it's visible.
Visible. You can continue, madam.
Okay, madam. So in that we use two representations, two continuous time representation and discrete time representation. In timing representation, time is continuous and the events can occur at any instant. And in case of discrete time distribution, time is divided into discrete intervals and the events can occur at specific points within these intervals. In modeling approach, analyzed using differentially integral equations and Markov processes in continuous time distribution, whereas discrete time distributions analyzed using difference equations and recurrence relations and simulation methods also. In continuous time, the continuous time representation applications are used in mathematical analysis and modeling systems where time is continuous, such as telecommunication networks. Commonly employed in computer simulations and the modeling of discrete systems. Like, so here we
Go to
use
the main content.
here definitions of customers' impatience, that is the balking, releasing, and the jogging. In case of balking, a customer immediately on arrival of a customer decides not to join the queue because of the length of the queue. Releasing, a customer releases after joining the queue if it decides that be longer than can be tolerated. So this behavior may also cause loss of customers to the organization. Other impatient model is jockeying. Customers may jockey from one waiting line to another. In any economic point of view, customers' impatience may result in the loss of potential customers, leading to loss in revenue. Here, I use a probability generating function and steady state probabilities.
Madam, only first page is visible.
Yeah, sir, it's not
Please
moving.
scroll.
Yes, it's not moving.
Go to the main content.
Okay, sir. Just a minute, sir, please. So these are queue disciplines, sir. First come first service and last come first service in case of big godowns. This is single vacation queue and multiple vacation queues and working vacation terminologies. Here I use a single working vacation with customer impatience. Here I use a steady state probabilities. At the time t, L of t denote the number of customers in the system. J of t status of the server, which is defined J of t 0 when the server is in working vacation and J of t is equal to 1 when server is in a normal working period. The process J of t, L of t is an auto process with a state space. Here some difference equations are lambda plus phi pi 0 0 is equal to eta plus alpha pi 0 1 plus mu into pi 1 1. Here lambda is customers arriving according to Poisson process with rate lambda, and the server can serve only one customer at a time with an exponential rate mu. If a queue become empty, the server begins a working vacation of a random length v follows exponential distribution with the parameter phi. And also, if a server is available during working vacation, the customer is served with eta. Suppose if working vacation finishes, server can give service to the customer with rate mu. So, arrival and the departure of an impatient customer without service or independent, the average renting rate of a customer is given by n of alpha. Okay, sir. Here some numerical results are there. It shows how it depends the effect of lambda on E of L, system length, system Q length. Okay.
Okay, madam. References.
So here in this paper, I have analyzed an embedded buffer MM1 single working vacation queue with impatient customers. We obtain the closed form expressions of the steady state probability, some important performance measures of the model, average system or average ranging rate, average vaulting rate are also derived. Okay, thank you so much.
అయిపోయింది
Okay, madam. Thank
సార్
you.
గుడ్ ఆఫ్టర్నూన్ సార్
Okay,
గుడ్ ఆఫ్టర్నూన్ సార్ రెడీ టు ప్రెజెంటింగ్ ది పేపర్ సార్
What is your name, madam?
సార్ డెక్కల్ లక్ష్మి సార్ ఐఎమ్ ప్రెజెంట్ టు ది పేపర్
Okay, madam.
రెడీ టు ప్రెజెంట్
Share
ది
your
పేపర్
screen.
ఓకే
Next, Kiradi Krishna Tumula.
డెక్కల లక్ష్మి సార్
Okay, madam. You can continue.
సార్
Share your screen, madam.
ఇట్స్
Not
విజిబుల్ సార్
visible. Not visible. Share your screen.
ఎస్ సార్ వెయిట్ సార్ ఇస్ ఇట్ విజిబుల్ సార్
No, not visible. Down there is a square arrow.
ఎస్ సార్ స్టార్ట్ నౌ ఆఫ్టర్ వాట్ కెన్ ఐ డూ సార్
Minimize it, madam. Madam, minimize it and open the presentation, madam. Yeah. Continue, madam.
Okay. Okay, madam. Lakshmi, madam, continue.
థ్యాంక్ యూ సార్ దిస్ ఇస్ శ్రీ లక్ష్మి
Already you have
and I am
started.
here part-time basis color in here.
Contents. Lakshmi, madam.
Now I would like to presenting about F derivations. Sir,
Go to the main topic, main content, madam.
overview, abstract, introduction, preliminaries, F derivations and 0 DEL references. Firstly, I will tell you about abstract. The concept of the theory of derivations in zero distributed almost lattices introduced and derived some important properties in zero DAL. Also, I introduced the concept of your principal derivation
Madam, go to the
and
main
isotone derivation.
already started previously.
Sir, introduction, sir.
No need introduction, madam. Go to the main content.
Main papers, sir. Okay.
Main content.
These are preliminaries, sir.
Explain the main statement only.
Oh, okay, sir. In this paper, we introduce the concept of F derivations on zero DAL almost lattices and give certain examples of F derivations on zero distributive almost lattices. Definition: a derivation D is mapping from L to L is called an F derivations on zero DAL. If there exists a function f is mapping from L to L such that d of x bit y equal to dx bit fy join fx bit dy for all x comma y belongs to L. Examples: let d be a derivative on L. If we choose f as the identity function on L, then we get that d is an f derivation on L. Let d be a derivation on L and f be an identity function on L. Define f is mapping from L to L by f of x equal to fy equal to y. Now d of x bit y equal to dx bit y join x bit dy equal to dx bit fy join fx bit dy. Therefore, d is an f derivation on L and every derivation on L is an f derivation on L, where f is an identity function. And another example, every constant function on L is an f derivation, but not a derivation. Let L be a zero DEL with at least two elements and a in L. Define a function on L by dx is equal to 0 for all x in L. Then d is derivation on L and it is called zero derivation on L. Define d and f is mapping from L to L by dx is equal to a and fx is equal to a for all x belongs to L. Yes, sir? Sir?
Okay, madam. Next.
And next definition, an f derivation d on L is called an isotone f derivation d is less than or equal to db. For all a comma b belongs to a. Yes, sir.
Please conclude in 1 minute.
Oh, okay. The following lemma.
Okay, madam. Next.
Some important properties. Some important properties. F derivations. Suppose M is the maximal element of L and D is an F derivation on L. Then we have following these properties. Finally, next we introduce the concept of fixed set and F derivations on
Madam,
L.
please conclude. Go to the reference.
Finally, I conclude this following the theorem. If D is isotone F derivations on L, then dx is equal to d of x join y, be it fx for all x comma y. And also extend my work about biderivations in zero DAL, sir. These are references, sir.
Okay, madam. Thank you.
Thank you, sir.
Next,
Thank
Kushma.
you.
Kushma. Okay. Madam, please conclude in 5 minutes.
Okay, sir.
1 minute.
Sir, is it my screen is visible, sir?
Yes, madam. Yes.
Good afternoon, everyone. My name is Kusma. I am from VNR Vijnan Chaudhary, Hyderabad. Under the guidance of Dr. A. C. Ramurthy Garu, Dr. P. Arikrishna, Associate Professor, we established this paper. So the title of the paper is Existence and Uniqueness of a Couple Fixed Point Theorem for Mixed Monotonic Mapping in Partial Hydrometric Space. So the main abstract of this paper is the aim of this present work to establish existence and uniqueness of a couple fixed point theorem for mixed monotonic mapping in partial Harder-Metric space.
I want to show the title. Previous slide.
Yes, sir. Existence and uniqueness of a couple fixed point theorem for mixed monotonic mapping in partial Harder-Metric space. Can I continue, sir?
Yes, continue. Next.
It's a abstract establish existent uniqueness of a couple of fixed point theorem for mixed monotonic mapping in partial Harder-Metric space, which is an extension of result of Nguyen, Wang, Liang, and Nguyen Chun. So this is the introduction to the
Go to the main.
This is the preliminaries to my paper. The main result of this theorem using the partial harder set using the new contaction principle. This is a new contaction principle using prove the some fixed points and common fixed points of the map. So the proof start with consider the 2 points in the x, and we construct the sequence x and yn in the sequence, and using the mathematical induction prove that x is increasing and y is decreasing functions. And after that, assume that the function d of xr comma xr minus 1, d of yr comma yr minus 1 is equal to 0, and prove that that is the using the theorem property. And after that, you consider the sequence, that is the sequence is monotonically decreasing sequence. Then prove that d value is 0. After that, you consider the sequence, you show that the sequence is
Proof. Go to the next corollaries.
so you establish that after that you prove the uniqueness of the couple fixed point theorem. After that, you establish corollaries based on the theorems. 2 corollaries you establish. And a conclusion, if you put f of u comma v is equal to x, f of v comma u is equal to y in the my main theorem, you get the result of Nguyen, Wang and theorems. Thank you, sir. This is the references for my papers.
Okay, madam. Thank you. Next, Varsha Verma. Varsha Verma is there? Yeah.
Sir, unmute చేసుకో.
Madam, please complete in within 5 minutes.
Sir, unmute చేసుకో. Mic.
Please unmute yourself. Hello?
Just a second, sir.
రెండు డివైసెస్ తో కనెక్ట్ చేస్తాం.
Sorry, madam, you connect only one device.
Good afternoon, sir.
Madam, please unshare one, only join from one device, either mobile or laptop.
Unmute, madam. Unmute.
Hope my screen is there, sir.
Yeah, visible.
Good
Okay,
afternoon, sir.
rotate your screen, mobile screen. Please rotate your mobile.
Auto rotate.
Auto rotate. Yeah. Okay,
Hello,
you can
everyone.
continue. Yeah.
My name is Varsha Verma. I have finished my post-graduation from Sri Satya Sai University for Human Excellence. Here I am presenting on a study on data encryption standard in symmetric key cryptography. My presentation is based on data encryption standard. I'll take you all through an example. Before knowing DES, we need to understand why it was needed at the first place. Cryptography. Cryptography is a method of transforming intelligible message to an unintelligible message and then retransforming it to its original form. Passwords, end-to-end encryption, digital currencies are the application of cryptography. To safeguard our data, it is very much important that it is in a coded form which is not known to anyone except to whom it is concerned. Cryptography is of two types, symmetric key and asymmetric key. In symmetric key cryptography, we see the sender and receiver uses a single common key to encrypt or decrypt the message. Block and stream cipher are its types. In asymmetric key, the pair of key is used to encrypt or decrypt the information. DES. It is an example of symmetric key cryptography under block cipher, also known as secret code making, while uses a fixed length key to encrypt and decrypt the data. 64-bit plain text and 56-bit cipher key is used in DES. This takes us across many substitutions and permutations operations. DES structure, initial and final permutations. These permutations are straight boxes, which is also known as P boxes. They are keyless and predetermined. Round function. DES uses 16 rounds. It takes L0 and R0 from initial permutation boxes and creates L1 and R1 and goes on till 16th round using the previous permutations. Key generator. Here, 16th 48-bit keys are created out of 56-bit cipher key. Now, let us see the same through an example. To work on DES, example has to be 64-bit long, which is not possible for all the messages like my message here. If message is 38-byte long, then this message need to be padded with some extra bytes at the tail end for the encryption. These extra bytes are thrown away at the end after decryption. Message which I have chosen here is not 16 byte. To make it 16 bytes, I added OAOD at the end. Now my message becomes Varsha OAOD. When it is converted to hexadecimal, we get this number 56415253484108 When it is converted to the binary form, we get 64-bit block of message. This message is now fit to work on DES as it is 64-bit block. Our key here should be of 56 bits.
Please
This
conclude.
key, which is of 64-bit long, goes through parity drop, tables, and many other permutation and combination to give us 16 subkeys. Encryption. After applying the initial permutation on the text M, we divide the permuted block into a left half and right half of 32 bits. We now proceed through 16 iterations from 1 to 16 using a function f, which operates on two blocks, a data block of 32 bits and key of 48 bits to produce a block of 32 bits. Then for n, going from 1 to 16, we calculate ln and rn. This result is a final block. For n is equal to 16 of L16 and R16, we take the right 32 bits of previous result and make them the left 32 bits of the current step. For the right 32 bits in the current step, we sort the left 32 bits of the previous step with the calculation. Using E-bit selection and 8 S boxes, which does the real mixing process, we obtain F. Similarly, finding the values till R16 and L16, we apply final permutation IP inverse on the last value and get our encrypted message, which is 973568441DD236B2. Decryption. Decryption is inverse of encryption, following the same steps as above, but reversing the order in which the subkeys are applied. Applying the final permutation IP inverse on R0, L0, we get our original message, which is M is equal to 56415253484108 and at the end 0A0D is removed from the text. DES has its own weakness and strength. Weakly secured algorithm, there is a threat from brute force attacks. A DES cracker machine known as Deep Crack is available in the market. To make it stronger and safe from other different methods, triple DES and AES, which is secure than DES, has been brought in use. I have also done the same using the SAGE, which makes all the mathematical calculation easy for us. Here are a few references given. I conclude my presentation. Thank you.
Thank you, Varsha Verma. Next, Yoshita is ready for your presentation. Yoshita?
Yes, ma'am.
Yeah, Yoshita. Let's start your presentation. Title is Performance Analysis of Sound Isolation using FDM and ADMM.
Yes, ma'am. Is my screen visible to you?
Yeah, perfect. Start your presentation.
Good afternoon, everyone. I am Yoshita, finally a BTech student in ECE at Jawaharlal Nehru Technological University, Kakinada. And today I am thrilled to present our research on the performance analysis of sound isolation using FDM and ADMM. Joining me are Dr. B. Leela Kumari, an Associate Professor, JNTUK, and my esteemed colleagues K. Rishikesh and P. Vandana. Together, we have delved into the world of mathematical techniques to enhance our understanding of sound isolation. So let's embark on this journey together and explore our findings. Throughout this our presentation, we will explore the following contents: introduction to sound source separation, applications of sound source separation, frequency division multiplexing, alternating direction method of multipliers, and results. Finally, we will wrap up with a software demo showcasing our sound source separation system in action. Sound source separation is a technique used to extract individual sound sources from a composite audio signal without prior knowledge of the sources after mixing. In our research, we have developed a sound source separation package using Python libraries. In this image, you can see three humans singing simultaneously. The recorded mixed sound signal is given to our sound source separation package, and we obtained derived sound signals, effectively separating the sound sources. Now we'll discuss about the applications of sound source separation. There are different applications for the sound source separations, which involve forensic audio analysis, which helps in detecting the identifying voices or sounds in recordings for investigations, and in music production allows music producers to isolate instruments or vocals for editing in sounds. Medical diagnosis, it assists doctors in analyzing specific sounds like heartbeats for diagnosing health issues. And finally, environmental identification. It helps drones and robots recognize surroundings by separating different sounds. Let's discuss about the frequency division multiplexing and how it helps in sound source separation. Frequency division multiplexing is a technique using telecommunication to transmit multiple signals simultaneously over a shared medium. In the context of sound source separation, FDM is utilized to divide the frequency spectrum of mixed audio signals into distinct frequency bands. Advantages of frequency division multiplexing include efficient bandwidth utilization, compatibility, and minimized interface. It has different applications like radio broadcasting, television broadcasting, telecommunication networks. At first, we have taken two different audio files as input, and we are going to mix them together to create a combined or mixed audio file. We start by loading these audio files and making sure they have the same sampling rate. Next, we perform FDM on the mixed audio file. This means we are splitting the mixed audio signal into different frequency bands. We create two signals representing frequency bands. Here are those two signals, FDM signal 1 and FDM signal 2. After that, we normalize the mixed audio signal to prevent it from getting too loud or distorted. Now comes the interesting part. We are going to use demultiplexing to separate the mixed audio signal back into its original components. We do this by using Fourier transform to isolate specific frequency ranges. It's like sorting.
Please come to conclusion part.
Okay, ma'am. Okay. And the other one is alternating direction method of multipliers. It is a powerful optimization technique that has gained attention in the field of sound source separation. The system checks if the selected audio file exists and reads the sample rate. A core ADMM object is created to handle the separation projects. There are two threads involved in this process, the main thread and the timer thread. The main thread handles the execution process, while the timer thread displays a loading animation to keep the users informed.
Show the results, Yoshita.
Yes, ma'am. This is the sound source separation package we have designed. These are the results folder where all the results will be stored with the current timestamps, and these are the sources folder which includes different mixed audio files.
Voice
Now,
call from which family?
Yoshita,
yes, ma'am.
please conclude it.
Yes, ma'am. Now I'm taking this video clip as an example. This is a traffic sound and a human sound.
निकालो 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 समझ
And now I'm selecting that sound.
So finally, it is concluded, madam. So we are able to separate the two different sources, signals from two different sources is possible to separate by using FDM as well as ADMM. So the main approach in this article is to analyze FDM as well as ADMM techniques for sound separation using simulation process. We could able to do it, madam. Thank you very much.
Yeah, thank you, ma'am. Thank you all. Actually, next 4 or 5 presentations are there, but we are planning to continue their presentations after these invited talks and maybe after 4:30. Please stay online. Now we'll resume with the invited lecture talks of this session. First invited lecture is by Professor Hemant Kumar Nishane. Now I request Professor L. Ramakrishna Garu from Department of Mathematics, Andhra University, to please chair this session.
Thank you, madam. Sir, Hemant Kumar, sir, are you ready, sir? Join us.
Join us.
We are ready, sir. Just we have been waiting for your. Please come. Sir, Richard, sir.
Anand Kumar, sir, please respond, sir.
Good afternoon, sir. Yeah, I can hear you, but my camera is little some problem, technical issue is there. So,
Okay, sir.
so maybe in between this will start. I don't know.
Okay, sir. Sir. Welcome to the International Conference on Pure and Applied in Engineering Mathematical Sciences. This will be organized by our Mathematics Department and Uttaranta Society for Mathematical Sciences and Professor Meenakshi Sundaram, Society for Mathematical Sciences. Sir, we are fortunate to hear your talk, sir. I know it is my fortunate to introduce you to the gathering, sir. So, Dr. Hemant Kumar Reshani is presently a professor, VIT Bhopal University, and Dr. Hemant Kumar is a doctorate from Pandit Ravishankar Shukla University and pursued his postdoctoral research at Texas and A&M University, Kingsville of USA, as a Fulbright Nehru postdoctoral fellow. He has an academic experience of 20 years and has worked at various levels up to professor and head of the department. He has 170 Scopus publications, including 100 science citation indexes in international journals and 10 book chapters in international publications. He has given 15 innovative talks in the international and the national conference. He has visited the Switzerland, Vietnam, South Korea, Thailand, and Brazil to present research papers. He has completed 4 international and national projects. He has handled the special issues of international journals as a lead editor and editors. He is a reviewer of many journals associated with Elsevier, Springer, Sandway and Tyers and Francis and MDPI publications. He has guided 3 PhD students and his research area is fixed point theory and fractional differential equations, nonlinear matrix equations. He is completed publications 280. Now his topic is hyperpower techniques for the outer generalized universe computations. So welcome, sir. Our delegates are fortunate to listen your valuable words, and they can be definitely. I think that they are enlightened with your speech.
Yeah, thank you so much, sir, for invitation. I am thankful for the organizing secretary in conference, all the different portfolio A special thank to the Professor Srinivas Rao for inviting me for this wonderful event in front of uh, all professor and yeah, so they are having the more experience than what I can say in front of you. But yeah, so my talk is not exactly not related to fixed point theory. Even I work on a fixed point theory. So few years back, I started with the numerical linear algebra related topic, iteration scheme, other thing. So this talk is related to on that area. I will start with the basic. So I'm going to share my PPT.
Sure, sir. Please share.
Can you confirm me? Can you see my screen?
No, sir. No, sir.
No, sir.
It's still the same because I shared already. Sir, can you see the screen or should I again share?
Sir.
Sure.
Sir, you need to reshare, sir. We are
Okay.
not able to see.
Okay, fine. I'm. I think I had to rejoin because the sharing option is not coming now.
Sir, PPT mark pages.
Yeah, so earlier it was showing the sharing option, but now that is not showing. So
Just you can mail it, sir. Just what we can display here.
Sir, chat లో పెట్టండి. Sir, chat లో మెయిల్ ఐడి పెట్టండి.
Sir, please look at the chat box, sir. The mail ID is there. Please send your PPT to the mail ID, sir.
I can rejoin. I can try rejoin.
Okay. Sir, your camera is working, sir, now.
Yeah, you can see me now, right? But yeah. Yeah, I send in the mail. I send the PPT in the mail.
Okay, sir, we will check it.
Can you see the?
Yes, sir. Yes, sir, we can see your presentations.
Okay.
Okay, sir. We can see your presentation, sir.
Okay, fine. Thank you. So good afternoon to all. So I'm, as I said, I'm thankful Professor Sriniwas Rao for inviting me for this conference. So the title of talk is Hyper Power Method for the Outer Generalized Inverse Compression. So but how to? The slide is changing. Can I confirm?
Yes, sir. Yes, sir.
Okay. So as the topic, the one word is there's a generalized inverse. So I'm going to start with the inverse of the matrix. So as we know, if we are having the matrix of the form or if we are having the linear system of equation, that we could write in the form of Ax equal to B. And if A is a non-singular matrix of the order n, then we can find out the solution of the system Ax equal to B as x equal to A inverse B. Means we can find out the inverse of the matrix. So this is only possible when we are having the non-singular matrix, or we are having the square with the non-singular. Then easily by a standard method we can calculate the A inverse and we can find out the solution of the system. But that could be possible if we are having this square matrix, even we can't find out the inverse of the matrix. That could be also possible. Or if the system, what the system we are having, and respect to that, if we are having the matrix and that matrix is a rectangle matrix, then the standard method to find out the inverse is also difficult. So we can't calculate the A inverse by the standard method. So the problem is if we are having the system of equation, and if the system of equation is associated matrix, if we are having, that is a singular matrix or the rectangle matrix, so then in normal sense it is difficult to find out the inverse of the matrix. So the question is, can we again, even we are seeking the solution of the form x equal to capital XB. So x does the similar job as the inverse of A exists. So because the solution of Ax equal to B is nothing but x equal to A inverse B if we are having the non-singular. But if we don't have the non-singular, then still this capital X will give the inverse of the matrix. So in this case, the generalized inverse, the concept come into the picture. So that's my topic suggests some one type of method to find out the generalized, outer generalized. So we'll see what is the outer generalized. Before that, we come up to the certain stage, what is the generalized inverse, or what different type of generalized inverses we are having exist in the literature. So I think everyone is aware that we are having the word pseudo inverse. So pseudo inverse what come when we are having the singular matrix or a rectangular matrix. In this case, the extension of inverse is called the pseudo inverse. So now there are different type of pseudo inverse we are having, and this pseudo inverse will be equal to, or reduced to the normal inverse if the matrix is a square and non-singular. So there is a one pseudo inverse we are having, that is called the Moore-Penrose inverse. So now if A is we are having the complex M cross N matrix, a pseudo inverse of A is defined as a matrix that is called the A DAG of order N cross M, satisfying this four property. So right now X we are saying as a Moore-Penn inverse if satisfying the following condition: Ax A equal to A, X A X equal to X, or the conjugate transform of Ax equal to Ax, and conjugate transform of Xa equal to Xa. So if this four condition is satisfying by the X DAG, then that inverse of A will call the Moore-Penrose inverse, and that will be a unique. So now for any matrix A, the Moore-Penn inverse, that is A DAG exists and is unique. So now other things we are having. A DAG exists for any matrix A, but when the later has a full rank, means if we are having the full rank, full column rank, or full row rank. So what will be the formula for the A DAG or the Moore-Penn inverse if satisfying that property? So if we are having the linearly independent column, so in this case the A DAG, the formula will be A conjugate A whole inverse equal to A conjugate transpose we will have. Or if we are having the full row rank, if we are having, the formula is the later one, that is called the A transpose A, or A star, let us call the A star, into inverse of A into A star. So in this case, so for any matrix A, we can find out the Moore-Penn inverse, and this will be the unique based on the full rank, row rank, or full column rank if we are having. Now, so if we are having, so this A DAG or Moore-Penn inverse can be converted to the normal inverse. So this we can verify. So you can see A DAG equal to, in the first case, when we are having the column full rank. So if we simplify A DAG A whole inverse equal to, by the property, we can write A inverse A star A inverse, and A star A inverse A equal to I. When we are having the A is a non-singular matrix, then only this is equal to I. In the second case also A star inverse equal to I if A is a non-singular matrix. Only in this case we can get the I. But in general case, this is not equal to I. If we are having the singular matrix or rectangle matrix, this is not necessarily this is equal to I. So, so this A DAG or Moore-Penn inverse can be converted into the normal inverse if we are having the non-singular matrix. Like one example we are having, so we are having the 4 cross 3 matrix, and the question is to find out the A DAG, Moore-Penn inverse. So now when we apply the row reduce equivalent form, so we can get the rank. So rank of the matrix is 3, and rank of the matrix and number of column is also equal to 3. That means this matrix is having the full column matrix, full column matrix we are having the rank 3. Full column rank, right? So now in this case, the first formula will be applied, and we can get the A DAG equal to this by using, and this A transpose conjugate equal to A transpose, because these are real matrix we are having. Elements in the matrix are real. And by using this formula, we can easily get the A DAG. So we are having the inverse of the matrix, generalized inverse of the matrix, that is the Moore-Penn inverse we are having. So this is the example when we are having the full column rank. If I take the other case, so also similarly we can find out the Moore-Penn inverse if we are having the full row rank if we are having. Now there are some properties of the Moore-Penn inverse we are having, that is called the characteristic of the pseudo inverse. So now if we are having A is a not square matrix, that is a M cross N, then A DAG equal to A inverse for the non-singular A. A DAG equal to A transpose conjugate DAG equal to A. So this will, like we are having the some characteristic of the pseudo inverse. Now this is next what you can see, that is interesting is there, that as I told you, A into A DAG is not equal to I, or A DAG A equal to not equal to I. So if we don't have the non-singular matrix, so that is not equal to I. Even that this we are having A B DAG is not equal to A B DAG A DAG. So if you are having the non-singular, so this all property are valid. But if you don't have the non-singular or the square matrix, then this property is not following. So this could be verified, or this could be seen by following examples. So if suppose we are taking the matrix A and B, which is a non-square and rectangle matrix we are having, so we can find out the rank of the A by applying the row reduce equivalent form. That is the full column rank, and second one is also the full column rank. Rank is 3 and 2 respectively. Then we can find out by the formula, that formula which we have seen for the full column rank, A DAG equal to 1 by 20 into this matrix, and B DAG equal to 1 by 14 into this one. When we calculate the B DAG and A DAG, we got this 1 by 280 into this matrix. Now we have to check what is A B DAG. So for that A and B we have to multiply, and we have to find out the DAG. So in the next slide we are having AB multiply, and we have to find out the rank, because we have to calculate the DAG, means Moore-Penn inverse we have to find out. So we have to find out this is a full column rank or full row rank. So from on calculation we got the rank is true. That is a full column rank. So by the formula, we got this value. That is the equation number 2, and from the equation 1 previous and the second, we are having this AB DAG is not equal to B DAG A DAG. So this normal property is not following if you don't have the non-singular matrix. And if we are having this property will be valid, AB DAG equal to B DAG A DAG, if we are having this condition, rank of A equal to rank of B equal to R of this order, then we can have this value. This we can check by the taking one matrix A and B. Now, so we have seen one thing by what one formula we are having for the full column rank and full row rank. We can find out the A DAG for the non-singular, for the singular or the rectangle matrix. Now, the second method we are having the singular value decomposition method. So what will be the singular value decomposition for the A DAG that we can see? Before that, we can see what is the singular value decomposition. So if we are having either the square or rectangle matrix, then A can be decomposed as a U, D, V transpose conjugate, where U and V will be the orthogonal matrix we are having, and these are diagonal matrix with the singular values of A. N is diagonal. Okay, this is applicable for the square and the non-square matrix both. So this is the singular matrix, right? So we need the U, we need the V, and we need the D. So if I take the example, then we can see for what will be the single value for the your A DAG. So suppose we are having the non-square matrix, that is a 2 cross 3 matrix. Then we apply the row reduced form, and we can see that this rank is of the A is 2. And because we have to calculate the U, so for that we are calculating the A transpose A, and for that we will get the square matrix, because we have to find out the singular value. So singular value means we have to find out the eigenvalue. For the eigenvalue, we have to construct the square matrix. We are given the non-square. So for non-square, we are calculating the A transpose A. We got this one. We got 0, 2, 3 are the eigenvalues of A transpose A. And the singular value will be for the negative square root of the non-zero values. That will be the square root of 2 and square root of 3 will be your singular values of A. And corresponding eigenvalue and eigenvector, we can get it. And from here we can see root 3 and root 2 will be your singular values, and corresponding vector we can have. And this is orthogonal but not orthonormal. So because U and V are the orthonormal, so we have to divide by the length. So now 1 square plus minus 1 square, that is, and square root will take. So root 2 will divide, root 3 will divide, and we can make the orthonormal. So we can have this V we can construct by taking this one. And because U we have to construct, so U we can construct by using this formula 1 upon sigma 1. That is the first singular value AV1, like that we calculated, and we got the V and U and D. And from here we decompose the A, which is a non-singular, which is the rectangle matrix we had. Now this concept we can use. So in this case we had the full row rank we had. So in this case we got D, diagonal matrix, or the singular value matrix we can say we got D. If we are having the full column rank, suppose in this example, so we are having the 4 cross 3 matrix. So in the similar way we can construct the A transpose A we can construct, and then we can find out the eigenvalue and eigenvector, and then by using the similar way we can calculate the decompose the A. Now, what will be that singular value decomposition for the A tag? For that, we are having this formula. We can use this formula. If we are having the A equal to U D V star, then A DAG equal to this formula we are having V D DAG U star. So already, so to apply A DAG singular value decomposition for the rectangle matrix, even then first we have to calculate the U, V, and D. And then only we can calculate the A DAG. So that's why I showed you the 2 example, and where the V same value what we got in earlier, and U we are having the transpose conjugate, means we have to transpose this one, and D DAG will be this sigma inverse. So we have to find out the eigenvalue, singular value matrix we are having, and we have to find out the inverse of that particular set of block matrix what we had. that is a sigma, we have to find out the inverse of that one. So if I take that same example, we can see. So example is same, we are having the full row matrix we are having. So in the similar way, we got this U, D, and V transpose, and we are, because we have to find out the A DAG. So as per the A DAG formula, this is the we are having. So you can see this mouse which is cursor, this is the V transpose, and we have to find out the transpose of this one, and we got this one. And that U transpose in this side, so this is the same here. And now we have to find out the inverse of this particular block matrix. That is a square root 2, 2, 0, 0, root 3. This we have to find out the inverse, and we will get this one. And that we have to complete the matrix. So 0, 0. So in this case, if you multiply, we can get the A DAG. So A DAG, singular value decomposition, we can we can use to find out the inverse of the matrix when the matrix is non-square, that is a rectangle. And the second example with the same second example of what we had. So in the similar manner, we can calculate. So you can see there are two methods we are having to find out the inverse of the matrix when the matrix is rectangle matrix if we are having, or singular, if even the singular we are having, we can apply this SVD decomposition to find out the inverse of the matrix. So, but this is a normal procedure what we teach generally in the class to the advanced linear algebra courses. But what are the different type of generalized inverse we are having that we are going to see. Okay, so generalized inverse of the matrix are the generalization of the ordinary inverse of the matrix. If A is a M cross N, the generalized inverse of A is the matrix X, satisfying this property, this equation AXA equal to A. And this convert to the normal inverse if it is the non-singular we are having.
Actually, sir.
How the generalized inverse to solve?
Sir?
Yes, sir.
Sir, please conclude your topic, sir. Well, we have 5 minutes, sir. Please.
Okay. I just started now. Okay. Okay, fine. Okay, so AX, because this is basic what we know everything. So I try to cover so flow. Okay, but even then I will try. Okay, so if we are having AX equal to B, and if we are saying X is the generalized inverse, so we can get the most general solution by using this equation X equal to XB plus I minus XA into Y. So, okay, so generalization is coming from the Pedulom in 1903. He started the working on the pseudo inverse. After that, more comes with the idea in 1920. Then combined the more idea with the Penrose 1955. We are having this 4 condition. If any matrix of the equation Ax equal to B satisfy this 4 conditions, so we'll saying this is a more Penrose inverse we are saying. Okay, other type of generalized inverse we are having Drazen, we are having weighted more Penrose inverse we are having. Then outer inverse as the topic I given the outer generalized inverse. So this is coming into the picture now. So okay, so let me go. So if we are having Ax equal to B, and if we are saying Z is a outer generalized inverse, so for that this condition must be satisfying. Z equal to Z, and the range of Z should be if you are taking T, and null space of Z if you are taking S, then this is considered as a generalized inverse if this condition are satisfying. And why this is called the two inverse? Because this satisfying the second condition of the more inverse. Because there are 4 conditions. So 1 inverse, 2 inverse, 3 inverse, 4 inverse, or more inverse if we can satisfying all the inverse. So because this satisfying the second condition of the more inverse, that's why these are 2 inverse even we say. And yeah, so they are different. So if I come down, okay. So the first word was the hyperpower. We had the word. So hyperpower is the general form of hyperpower. This formula is this one. Let it be Z L plus 1. This is the iteration scheme. So in the form of iteration is mentioned there, where RL is called we are having the residual. So now to solve this type of equation for different order, P is the order we are having. This is for the P greater than equal to 2. For different order, 2, 3, 4, different type of researcher is work this one. So what is our main aim? Main agenda is that if if we increase the order, the matrix multiplication should be decrease. If we, how much you can decrease or you can reduce, so that is you achieve the goal. So our aim was the same. So there was a different second order, third order. We are having fourth order, but different 4 multiplication, 6 multiplication. So what we propose in the paper, the published one. So we use this 19 order, and here for the 19 order, only 7 multiplication is enough to solve the problem. This was the achievement for this one because previously the 18 order was considered. For the 18, even the 7 order was there, 7 multiplication. So with the 7 multiplication, we can work also for the 19 order. This we are done. And how we can understand that this is your achievement, because if EI, that is called the informational efficiency index or computational efficiency index, is high as compared to other, then you can say your work is good as compared to the previous one, we can say. Like this table says that EI is 2.71 because EI is P upon R. P is the order, R is the matrix multiplication. So as you increase the order and decrease the multiplication, definitely this value will be increased. And this EC is what? Rth square root of P. So obviously, if this is always, this will be between the 1 and 2. If we are getting the more closer to 2, that will be better. So now you can see in this table 1.52 we are having, that is as compared to other, this is better. So like that we are having initial guess. This is the computational order of convergence we are having. So like that for different, some example we are given in the paper and like that. So we can see here the time tolerance we are having and time with respect to time. So you can see we are having the less time, computational time we are having as compared to previous work. So like that, this was the, but yeah, the main thing is yet to come. So, but the time constraint. Yeah, thank you. What I can say.
Thank you very much, sir. So you have completed your talk within stipulated time, and for that, thank you very much. And any doubts from the audience? So really, your talk is informative, sir. Definitely, the delegates will enrich their knowledge through your talk. Thank you very much, sir.
Yeah, thank you so much, sir, for inviting me for the talk and give us the opportunity in front of all learned professor of the Andhra Pradesh and nearby. So working on a fixed point theory, even I was supposed to come there, but due to that time and this college work, I was not able. Next time, but I will try to come and meet you all. Thank you so much.
Sir, on behalf of the organizers, we thank you for your invited talk, sir. Thank you very much, sir.
Yeah, thank you so much, madam.
Sir, good afternoon, Hanan Kumar Rasina, sir.
Yeah, good afternoon, sir.
So,
yeah, can I see you? Can I see you on the screen? Oh, okay, yeah. Because when I come you next time, I should see your face. Now this is the professor. Now you see my face.
Definitely, sir. Definitely. We are very happy with your presentation and as your invited talk. Thank you, sir. So this is a very rare and good opportunity to all of us, the delegates from various places. Okay, we enjoyed a lot with your.
Yeah. Thank you so much, sir.
Okay. Right, sir.
Yeah,
No. Sir, next time definitely your presence is very much required, sir.
Yes, sir. I think there all the fixed point theory people are there. I think Dr. Dhananjay is there. I think.
Yeah. Already talked over and just he's here only, sir. Please come. Oh, sir, please. See.
Hi, nice to meet you.
Yeah, thank you so much, sir. Happy to see you.
So, Babu sir already yesterday his keynote address is over.
Yes, sir.
Okay, sir. Next time we are planning to organize a 2-day international conference at probably at St. Joseph College in Visakhapatnam.
Okay, sir.
So definitely your presence is very much required there.
Yeah, definitely, sir. I will come. Give me the advance information so that I can plan.
No, definitely in advance, 2 months, 1.5 months in advance, just we will write a letter to you and we will send the invitation to you.
Okay, thank you so much, sir. Thank you.
Okay, thank you very much, sir. So one more important point,
Yes,
our
sir.
Guru Professor KPR Sastri is here only. Just if you want to.
Yeah, hello, sir. Good to see you, even in the online, because we read your paper, but it is fortunate to see you in front of this all.
Yeah. Okay.
Yeah, thank you. Namaskar, sir.
Excuse me, sir.
Yes, sir.
Thank you, sir. Thank you. Again, very much thankful.
Okay, thank you so much, sir. Okay.
Hello, excuse me, sir. Hello.
Now felicitation program is going on for M. Ramakrishna.
Hello, excuse me, sir. Hello.
Ramakrishna Garu for chairing this session.
Yeah, thank
Small
you.
presentation from our side. The next invited talk is by Professor K.V. Venkateswarlu Garu. And we request Professor P.D.N.
Sherlu, Professor of Mathematics, Department of Sherlu, Professor of Mathematics, Department of Computer Science and Systems Engineering, College of Engineering and University. Professor Venkateswarlu is an expert in algebra. His areas of specialization are ordered algebras, in particular Boolean algebras and the Boolean rings. He has vast experience of teaching as well as research. So far, he has published 40 research publications in journals of international repute. He has guided 5 MPhils and 12 PhD students for their research degree. He has spent close to 14 years in Ethiopia serving 3 distinct universities. He is also closely related to several reputed societies. To mention a few, he is a life member of Andhra Pradesh State Mathematical Sciences. He is a member of American Mathematical Society. He is a reviewer for Bulletin of Southeast Asian Bulletin of Mathematics. He is also a reviewer for Journal of Hyperstructures, reviewer for Journal of Algebra, published from Bulgaria. With this short introduction, I would like to request Professor K. Venkateswarlu to speak on ideas of a pseudo-ring. Professor K. Venkateswarlu.
Thank you for the thanks for the organizers for inviting me to this talk. In particular, I thank Professor KPR Sastri, who made me to stand here some long back, 2020, I don't know when. He was my boss at the time, and he said, "You are a good teacher, but bad researcher." He has given a comment, and he said, "You have to do research." I mean, do research means come, but go on. So that's what made me a long inspiration for me, and still now I'm standing in front of him means it is his blessings. So thank you for the organizers once again. But let me begin with a simple concept, the Boolean ring, which is a ring in which A square is A for all A. It's all well-known structure. And also Boolean algebra. A Boolean algebra is a complementary distributive lattice. Now, there are two structures. MX Stone has given a path for these two. Yes. Boolean ring with 1 is equivalent to Boolean algebra. So there are two algebraic systems that are equivalent. People were trying to generalize these things in terms of ring theoretic aspects. The aspect of ring theory, Boolean rings. For example, associate rings by Sussman, P power K rings or PK rings by McCoy, and Boolean-like rings by Foster, P1, P2 rings by N.V. Subramaniam. They all have done a generalization for Boolean rings. So they have generalized. And not only this, there are many. For example, we tried to look into weak idempotent rings. And that's also a generalization for Boolean algebras. Boolean rings. I call it WIR, weak idempotent ring. A ring in which A power 4 equal to A square. So generalizing the concept of Boolean ring. Now, it was not stopped. People were looking at the lattice theoretic path, Boolean algebras, MV algebras, De Morgan algebras. There are many other generalizations for Boolean algebras. So the counterpart of lattice theory, the counterpart of ring theory. Now, MV algebras and many other algebras are there, like almost distributed lattices. Almost distributed lattice is not a distributed lattice. It is not even a Boolean algebra, but it is a generalization. So there were many other De Morgan algebras and P algebras. There are many algebras, So the counterpart of ring and lattice theory. Now, the fundamental question is, there is a pathway from these two structures. Is there a path from the general structure of this to general structure of this, any general structure? While pursuing that, we made an attempt to look into the MV algebra. What is the counterpart of ring structure algebra? The ring structure. And so we were able to penetrate. Of course, it's not our. So, ideals of a pseudo ring. Just I would like to give you the brief part of what is a pseudo ring. And so the first person, the first one who made an attempt to look into the rings, the counterpart of MV algebra is Chasda and Langer. They have pursued a concept called pseudo ring. It's not even a ring. The pseudo ring is not even a ring, not even a group, not even anything, but it is some structure which is a counterpart for MV algebra. So this is what we made an attempt of introducing a pseudo ring. Introducing an ideal concept is new for the pseudo rings, because they have introduced pseudo rings for their general purpose, not for the purpose of studying ideal theory. So look at these axioms. The axioms is associative, commutative, identity. Just let us call it by name as what we know. This is 1 plus 1 plus x is equal to x. If you look into the Boolean algebra, it is 1 plus x is x complement. X complement is x. So x double complement is x, which comes into a square equal to a in ring theoretic part. So it's a very peculiar setup was done for these P1 to P7 axioms. All are independent. P1, P2, P3, P7 are independent. There are having plenty of examples on it. But now it's not for me to discuss on that. And one more observation is, look at this. A distinguished element 0. There was no 0 in this because we always write an algebraic structure in the form of universal algebra setup. R plus dot 1. Dot 1. There is no 0. But 0 is defined as 1 plus 1. A distinguished element 1. Just we have plus as a binary operation. 1 plus 1 is 0. Simply don't question why 0. So that's why we have written 1 plus 1. So, yeah, it's better to scroll than. No, go back. Go back, just further. Further. Yes. Now just move one slide. No, down. Down. Right. Now the counterpart, the lattice part is less than or equal to partial order. So we have x less than or equal to y if and only x into y plus 1 or y into x plus 1. Both are same, they are 0. So x less than or equal to y, x into y plus 1 equal to 0 because I have a commutative property. Hence, I can define an order. And observe, r less than is not a positive. Still, it is not a positive. Some algebraic structure, we are getting it. So, it is scroll there next.
The middle ones. Yes.
So I have a plenty of properties on that. Then x less than y, we have clearly x less than or y is x into 1 plus y is 0. So I have plenty of properties. And look at this. This x plus 0 is about x. 0 plays as an identity. A characteristic of R is 2. That means a plus a equal to 0, which is closely resembling to the Boolean ring. A Boolean ring is commutative. Every Boolean ring is commutative with a characteristic 2. It is characteristic 2, but it's not commutative. If it is commutative, it boils down to Boolean ring. So all Boolean rings, the class of Boolean rings are the class of pseudo rings. I'll write down PR, pseudo rings. But a pseudo ring is not a Boolean ring. We have an example on that. Every Boolean ring with unity is a pseudo ring, but a pseudo ring is not a Boolean. This is an example where a pseudo ring is a pseudo ring, but not Boolean, because you can find an element A in which A square is 0, but it's not A. And then I have a plenty, and a very important thing is Z4. We look at Z4 in this way. Z4 plus dot is a commutative ring with 1, CR with 1. And the property is it's not Boolean. It's not a Boolean ring. And A square is not equal to A, even in this. But we have A power 4 equal to A square. So Z4 is a weak idempotent ring, which is a pseudo ring. So now we can balance it, looking at the pseudo ring and Boolean ring. So I have Z4, which is a commutative ring, but not a pseudo ring. Hence, Z4 serves our example, serves our purpose. And a pseudo ring will be Boolean provided if you add associativity and left distributive or right distributive, whatever it may be. And we have some of the results which are just simply, and let me convert this in terms of, if I look into the Boolean algebra, this is y plus 1, xy plus x plus 1. So 1 plus x plus xy is 1 provided if it is x square equal to x. So if I put y equal to x, it becomes x square is x, 1 plus 1 is 0. I have commutativity, so I'll get 1. right? So this is, I have, proofs is simply simple. We have some more properties regarding this partial order. We need partial order to introduce the notion of a metric ideal. So for that, we have developed this. Now, I would like to introduce the notion of an ideal. 0 belongs to I, of course. And with the setup, R is a pseudo ring. Simply R stands for a pseudo ring. 0 is an I. X plus 1 into Y plus 1 plus 1. We don't have any objection by rotating plus. So, rotating these terms. So, X plus 1 into Y plus 1 plus 1 should be an I. Whenever X less than or equal to Y is an I, X is an I, imitating the idea of lattice ideal. And now the counterpart of lattice ideal, MV, that boils down to MV algebra ideal in MV algebra. So again, and now we have the equivalent proposition as we have done for Boolean. Ideal in a Boolean ring is same as ideal in a Boolean algebra. So we have an ideal in a pseudo ring is same as ideal in a. These two ideals are equivalent. Now, there are certain properties in these ideals. Yeah, some of the equivalent conditions for an ideal of a pseudo ring. And now we have, this is a crucial one. Look at this. This was not named by us. It was named by C.C. Chong when he was introducing MV algebra. He has defined a pseudo metric. He defined a metric. We are also carrying the same nomenclature. We are defining a metric on a pseudo ring. With these conditions, delta xy equal to delta y symmetry, x0 is x, and the delta xy implies x equal to y if and only if it is not there. And look at very carefully, delta of xx cannot be 0, right? No, delta of xx will be 0, x plus x equal to 0, because delta xx is 0, because I have x plus x, I have defined x plus x is 0. So these are the conditions which all the properties the hold for definition of definition of a distance function. Now it's very important to define. See, when we are looking at R by I or B by I, when I is an ideal, quotient of an ideal is defined only when it is well defined. Of course, there should be a 1-1 correspondence between the congruences and the ideals. Then only we can define B by I or R by I. Simply R by S doesn't work. So that's what we were. And so the very important thing is, if I take a pseudo ring, which is not a ring, how do you construct an ideal? How to construct R by I? Unless you have a 1-1 correspondence between the ideals and congruences. So we have defined the congruences suitably, which is related to R. So this was the way, and the relation gives us in terms of now the relation theta on R is in terms of delta function. Delta is a metric function. Sorry. Right? So now a congruence relation gives a unique ideal, and vice versa. And we have a set of results. The ideal generated by, a single set, generated by a set, not a set H. And it will be of this form. It will be of this form, x less than or equal to 1. It's not like something x equal to x1, x2, x. Summation, I is equal to 1 to n. Something something similar to that, but in a different fashion. 1 plus h1 plus 1 into h2 plus 1 plus hn plus 1. Because that 1 is required to boil down to Boolean algebra setup. So smallest ideal. And then the ideal generated by I union singleton A. These are all which was characterized by this. I union singleton A is their existence such that x into a plus 1 whole power n. A plus 1 whole power n means a plus 1 into a plus 1, we have x dot y. So x dot x can be defined, x dot x. So inductively it happens. And this is the ideal is in terms of element wise. These are the certain properties we got. Then we have defined a prime ideal. A prime ideal is not a very interesting fact, but this is we need for to generate a maximal ideal. Xy is not x into y plus 1 is 1. Look at this. If you put y equal to x square plus x square plus x is 0 in Boolean ring. So 0 is always in P. That's not a big issue. The issue is I want to use this for some other purpose to generate. Now we have some examples of prime ideals of a pseudo ring. And simply instead of all prime ideals, the intersection is also gives a prime ideal. And we would like to use this in some other context. Right now we have prepared a base for writing many ideals, many polar ideals, implicative ideals, and then lot ideals are there. So we would like to work on that. So these are all P is the prime ideal, then they are equivalent. If and only P1 into 62 is P, either P1 is P or P2 is P. It's not a new result, but it makes a base. And we have defined a nil radical. Remember that again, I will repeat on R. R is not a ring. It's it's an algebraic structure. It's simply an algebraic structure satisfying those 7 conditions. So N, the nil radical is identified with the set of all nilpotent elements. So it's some of the of course, the proof is a little bit tricky to get. We manipulated with the M and N. So maybe that's the conclusion part for the conclusion, because these references will give more information and more knowledge on the work which we have done. And especially this is the guy who has ring-like structures corresponding to MV algebra via symmetric difference. We have not used symmetric difference. It's not symmetric difference. We have used the delta xy. So this is what we have done. Thank you for giving me this opportunity. Thanks once again for the organizers.
Any questions? In the absence of questions, we thank Professor K. Venkateshwarlu profusely for his commendable contribution on ideas of pseudorings. Thank you very much.
Is there any relation between prime and maximum ideals in this?
Yes, we would like to develop prime ideals like Boolean algebra, prime ideals and maximum ideals coincide. But here it is not. Still, yeah, one prime ideal is maximum ideal is there. Yeah, I have proved it. I mean, we have done it. Maximum ideal will not boil down to prime ideal unless we impose certain conditions.
First floor, second floor.
We go, sir.
Thank you, Venkateswara garu. Sir, Now I invite Professor Ravi Kumar Garu, department, on behalf of conference organizers and UASNS and SNS, we want to honor you. Organizers of the conference. ఆన్లైన్ లో పెట్టి మరి నన్ను క్వశ్చన్ చేసి సౌండ్ మైక్ అక్కడ బ్యాటరీ అయిపోయింది
Next is my turn. I will share my PPT.
Sir, you can mail to this one, sir. I see you.
1 minute. Just shall I mail to this one? To tell me the number of mobile number.
Is the mail.
Mail. I don't know how to mail.
Share to this mail.
Already it is on your phone and downloads.
No, it is there in WhatsApp.
Share use.
Next invited talk of this session is by Dr. Deena Sunil. Now I request Professor NVS Murthy Garu to please share this session.
Thank you, ma'am.
Slide changer is there.
Hello? Shall I start? Hello. First of all, I will introduce myself, Dr. Dina Sunil. Good afternoon, everyone. Our next speaker of the day is Dr. Dina Sunil, Assistant Professor, Grade 2 from Indira Gandhi National Tribal University, Amarakantak, MP, India. The title of his talk is Journey from Classical Computer to Quantum Computing. And quantum computing is nowadays a hot topic. Okay, perhaps he would get some. He would give us some insights into it. His research areas are basically fluid mechanics, magnetohydrodynamics, applications of operations research, optimization techniques, data envelopment analysis, fuzzy optimization, soft computing, performing analysis, etc. He has several publications, around 30, and with a long work experience ideas. Now I invite Dr. Dina Sunil to his talk.
Thank you, sir. Thank you so much. Once again, I thank you to Srinivasa Rao, sir. Sir has given me an opportunity to come and interact with you. So, shall I start my talk? Okay, thank you. The slide is visible. Can you make it? Actually, my topic is very simple: journey from classical computer to quantum computing. Shall I give my talk 100% in English, or shall I Hindi? Hindi someone Hindi में भी चलेगा. English only. No problem. Okay. See, journey from classical computer to quantum computer. Before going to that, how the classical computer, what is the classical computer and what are the quantum computer? Before that, I will talk what is classical mechanics and what is quantum mechanics. Okay, classical mechanics, physics students will know, but what is quantum mechanics? See, quantum mechanics means at a very minute level, the research will be go. At atoms, at micro level, what is happening? Okay, so first slide. See, the first slide I will give this one. See, electromagnetic wave or particle wave. Earlier, the scientist has in confusion whether the light contain particle or electromagnetic wave. Okay, so so many years it is a debatable. So after that, one scientist came and that he told that some scientists say it is a particle or it is an electromagnetic wave. Thomas Young. Thomas Young is a very genius scientist. He had proved that the light has its duality by Young's double slit experiment. Okay, by Young's double slit experiment, he concluded that sometimes light behave a particle and sometimes light behave like a wave. So he has, I will show you the experimental setup. Double slit experiment. So here some atoms will be bombarded and he will observe on the screen what will be happening. So after that, sometime he see that the images like in a particle and sometimes in wave. So after that, after seeing all these results, scientists became confusion. What is going? We are all the instruments and apparatus are same, but we are repeating the experiment again and again. But what is happening here? Sometimes the pattern is different in one experiment. The same experiment if he did again some pattern is different. So after that, this is one of the observer. See, he kept on observer. He observed what is happening. So whenever it observes, it behave like a wave. If no one is observing, it behave like particle. So after that, he conclude that light behave as both nature, electron. This is particle and wave nature. The Nobel Prize in 1921 took as the Sir Einstein for the photoelectric effect. The same result got in this experiment also. Huh. Now I will tell you, see classical computers. We are using all these computers, okay? See, what is happening at micro level, at very atomic level, we can't predict at which position the electron will be. It is very difficult to observe the position of electron because what is the rule and what is the laws applying in classical mechanics when we observing in very minute particle, so the behavior will be changed. So we don't know at what exactly the electron in which position if we come to quantum computing. So classical computers, you know that binary digit, that is bits. Computer, the basic principle of computer will go on bits, either 0 or 1. Either it takes 0 or it takes 1. But the difference between classical computer and quantum computer, I will say, see, the AYUSH. To write this one, the code will be this one. Okay, to write the character is 8. So the computer will store in either 0 or 1. So see that 0 0 triple 1 0 0. To write well, this much code is required. Okay. So these are all the charts. One minute. Back side, please. Okay.
You're doing back.
Back side.
You're doing now.
Okay. So back. No problem.
Middle one.
Middle one. Okay. So next. 1 byte equals to 8 bits. This chart shows 1 byte equal to 8 bits, 1 kilobyte equal to 1024 bytes, 1 megabyte equals to 1024 kilobyte, and so on. 1 GB means 8 crore 58 lakhs, something that is bits required. So what is the difference between this is happening here? See, bits. Bits means either it take a 0 value or 1 value. Okay, but qubits is in a superposition. in 0 and 1. At a time, it is having the both value. It is in a superposition wave. Qubits are not exist in natural. The scientist will build in the lab qubits. See, what is the advantage of qubit? Because electron having spin upward and downward also. Okay. So the important thing in qubit is that, see, at what the 0 and 1, at a time, at a microsecond, we can't predict it is either 0 or 1. So this is having a special principle, that is superconducting. Okay. Next, we come to here. If we will take 2 qubits, the possibility will be 1 1 0 0 1 0 0 1. If you take 3 qubit, 1 1 0 1 1 1 1 0 0 0 0 0 1 0 1 1 0 1 1 0 0 and 0 0 1. If you take the 4 qubit, this much the possibility will be there. So the graph will increase exponentially. The graph will increase exponentially. If you take 48 qubits, then 2 to the power of 58 states exist. Okay. So after that, this is the Summit computer IBM is having. This is the entanglement. See, before that, Google has announced that we achieved a quantum supremacy. We have he announced that in 2019 that we have achieved quantum supremacy, that we can solve a mathematical problem which takes a supercomputer so many years. So he told that we will solve that in 20 seconds. After that, IBM, which has the supercomputer, this is a supercomputer called as Sumit, and which is having Google is having his quantum supremacy, that is psychoman, that is, I'm not exactly name is having. So what is entanglement is there. So if the entanglement happens to qubits, then they will perform the calculations. See, what is entanglement? Entanglement in 2023, some scientist has awarded as a Nobel Prize in working in entanglement. Okay, so entanglement. So suppose this is 1, suddenly this is 0. If this qubit has 0 spin, suddenly this having as 1 spin. Okay, so this is quantum entanglement. This is a mathematical correlation is there. If this 9 qubits, it is in if the 9 qubits in entanglement, they can perform a mathematical correlation. See, this is supercomputing. You can see this picture. Okay.
Can you turn the position of the slider?
Slider should point out this way.
This side.
You kept it.
No problem. See, dilution refrigerator. See, it to make qubit, it is very challenging for the scientists, because it takes minus 273 degrees Celsius. If some minor disturbance occurs, superposition collapse. To maintain the superposition, the scientists have so much challenges. At present, everyone is telling that we have achieved a quantum supremacy. China has announced, IBM announced, Google has announced, so many telling that we achieved a supremacy, quantum supremacy. So this is the image. Previously, I will told you. See, to maintain this, it is chip is there now. To mobile chip, as the size decreases and decreases, at some certain micro level, at quantum state, we can't predict the particle position. Earlier, I told you that. After that, Google is closer than ever to have a quantum computer breakthrough. This is the 72 Google. 1 minute. Google reclaims quantum computer born with 72 qubit processors. After that, simulation. I will come to the topic simulation. So you have seen the video game. 20 years back, we have played a video game nowadays in advanced video game player is game simulation. You know the simulation to become a pilot. One artificial how they will give a training to pilot in helicopter. They will make one instrument like aeroplane. If they will give a training. Okay, so much simulation is coming. So, what is the advantages to making a simulation is that what is simulating with graphics and computers. This is all we can hear at present in 2000 in aeroplane also. Caffeine. If you drink in 1 cup of coffee, 10 gram caffeine may contain 10 gram of caffeine may contain, and this is the structure of caffeine. So after that, 1 cup of tea, 36 milligram caffeine. So 10 to the power 22 molecules. That is this much data. So to simulate one molecule, the computer need so much space, so much bits. So what is a classical computer has a very big challenging. They can't perform this hooky data at a time. But quantum computer can have this ability. But the challenging is that to compute, to simulate one molecule, this much data is requiring to simulate one molecule. This much data is required. So what is if you simulate molecules, if microorganisms and caffeine, this one caffeine molecule, what is the advantages? Then we can in laboratories and in medical health, it is very advantageous. We can find the behavior of virus. You know, virus is very small. It is a very minute. We can't predict what is next, what they may take the shape. Okay, so in conclusion is that at present also scientists is having so many challenges because to simulate one molecule this much bits required. Then classical computers is very difficult. So again they are trying to become a supremacy again and again. See, Richard Feynman, he is given as he's worked in a lots of quantum computing program. And see, this is a diagram. This is one. So before concluding, at present again I am telling you that in future we may build a supercomputer, but it is very challenges. Because why it is very challenges? To make a superposition, it is very difficult because superposition will collapse at a very minor disturbance. Okay, if disturbance, see how to, and we can't take our supercomputer into our home. It is very difficult. In after 10 years or 15 years, if quantum computing may be in high laboratory, because they have to maintain a lot. I think so, in after so many years, 50 or 160 years, computer again the shape will be reducing and it can become to in our home also. So at present, my conclusion is that quantum computing is that the qubits is very important, and qubits are not made naturally. Qubits are made artificially using electromagnetic waves, and it is having so many processes and so many phenomena. So still I am reading so many papers here also. I am working in this field also. I am a starter, not have done so much work. So thank you. If you have any doubt, we can discuss. No problem. Thank you. अगर हिंदी में रहता तो और बहुत अच्छा बोल सकता था. थोड़ा अंग्रेजी कमजोर है और इसलिए जो अटक रहा था लैंग्वेज. ओके, थैंक यू.
Any questions, please, from the audience?
पूछ सकते हैं, डिस्कस कर सकते हैं, कोई दिक्कत नहीं है. मेरे को जितना नॉलेज है मैं देखिए डे बाय डे 0.0001% लेने की कोशिश करता हूँ. डिस्कस करेंगे. अगर नहीं हुआ तो भी मैं आपको फोन या ईमेल में से मैं आपको बता देता हूँ. If you have any doubt, you can ask. No problem. If I don't know, I will try to know. No problem. Any questions? Thank you so much.
That's very kind of you, sir. In the absence of questions, let's please clap.
Want to have a photo?
Thank you, Dina Sunil Garu, for
Thank you.
lecture.
Thank you, madam. Thank you so much. Due to language problem, I can't explain. No problem. You understand? Okay. Thank you so much.
We want to honor you on the organizers of this conference. Bye.
Online
Thank you, sir.
Madam.
Anita Thomas. Next invited talk is by Professor Anita Tomar from Sridev Suman Uttarakhand University, Rishikesh, Uttarakhand, India. I request Professor K. Venkateswarlu Garu to please share this session.
Good evening.
Madam, are you?
Share చేస్తున్నా.
Share చేస్తున్నా. Hello. Good evening. Good evening, Professor Anita Thomas. Am I audible?
Yes, you are audible.
This is
Good
Professor.
morning, everyone.
Um, let me invite you for the conference on behalf of the organizing members. We are very glad to hear your talk on advancements in fixed figures generalization and applications. And I would like to introduce to the audience Professor Anita Tomar is head of the Department of Mathematics, Devi Suman, Uttarakhand Vishwavidyalaya, Rishikesh, and in particular LMS campus. And she has 23 years of experience in teaching and 19 years of experience in research. And her main area of interest is picture point theory and its applications. And she has been to the editor of many journals, and also she has many uh, credentials for her, and she's a reviewer for the Mathematical Reviews and the Division of American Mathematical Society USA, and a member for SCI and the SCIE journals. And also she's, if I'm right, you're an honorary editor for the Journal of Journal of Function Spaces, and it's my pleasure to invite you for the talk. And please deliver your lecture, and it's for your 30 minutes time. Please proceed.
Thank you so much. Am I audible?
Yes. Yes. Please proceed.
My screen is visible. My screen is visible.
Yes, madam. Yes, madam. You may proceed.
Okay. So first of all, I want to thank organizing committee, Professor Srinivas Rao, Professor Dr. Kameshri, and everyone associated with ICPAEMS. I want to thank everyone. This is a great event organized by Andhra University, Vishakhapatnam. So today I'm going to discuss some advancements in fixed figures, generalizations, and applications. So first of all, what is a fixed point? Fixed point is a point that is mapped to itself, means which is kept fixed by the function. Suppose if we consider a non-empty set X and we consider a single valued map T from non-empty set X to itself, then a point Y is called the fixed point if T by is equal to Y. It means the point Y which remain invariant under the given transformation T is called the fixed point of a single valued map T. In real life, we observe the rotation of a wheel. Its every point move except its center. So what is the center of a wheel? Center of a wheel can be compared to a fixed point. The boiling point or freezing point of a substance like water, which is used to calibrate a thermometer or define a temperature scale, is a fixed point. If we imagine a hurricane as a spinning top, then what you see? In the middle, there is a quiet spot, like a tiny island in a stormy sea. So this calm stop is the eye of the hurricane, which can be viewed as a fixed point. So around this point, the storm spins widely, causing chaos and destruction. In graphical term, fixed point is the point of intersection of the curve y equal to tx and the line y equal to x. So the red line is the line y equal to x and blue line is the line of the underlying function. If we define a function like tx equal to 2x, then we see that the line y equal to x intersected only one point, so 0, which is 0. So 0 is the unique fixed point of this function. Similarly, for the sine function, the line intersected at again at 0. So 0 is a fixed point, which is unique fixed point of the function sine x. If we consider a function 4x into 1 minus x, then clearly it has two fixed points. One fixed point is at 0, another fixed point is at 0.75 because the line y equal to x intersect it at 2 points. One is at 0 and another is at 0.75. The function x square also has two fixed points. One is at 0, another is at 1. Sine 3x has 3 fixed points and tangent x has infinitely many fixed points. If we consider cos hyperbolic x, we see that this line does not intersect this graph. So it means it has no fixed point. The function tx equal to x plus 2, it has no fixed point. Clearly, these two lines are parallel and these two lines never intersect. So translation map has no fixed point. So what we conclude from these examples? We see that a function may have a fixed point, it may have a unique fixed point, it may have more than one fixed point, it may have infinitely many fixed point, and there may be a situation when a function may not have any fixed point. So in fixed point theory, we discuss about maps which has a fixed point. Mean what are the conditions under which maps have a fixed point? So what are the conditions? How we determine the fixed point? Is the fixed point unique? There may be situations where the fixed point is not unique. If the fixed point is not unique, then what is the geometry of the set of fixed point? Do these have any applications in real world? So we can say that the fixed point theory is most vibrant area of research. The existence of a fixed point plays a significant role in nonlinear analysis, as many real-world problems can be reformulated as a problem of finding a fixed point of nonlinear maps. Stephen Banach was the first person who noticed that each contraction in a complete metric space has a unique fixed point. So, one of the significant outcome of the fixed point theory is when a map under minimal suitable conditions has a fixed point. In fixed point theory, we keep minimizing the conditions under which the unique fixed point exists. So, the uniqueness of fixed point has been a significant area of research for more than a century. However, in the real world, there may arise situations when the fixed point may not be unique. So maps having non-unique fixed points may fix some geometric figures and find applications in artificial intelligence, neural networks, biology, economics, and so on. We call such a figure to be a fixed figure, and it naturally arises in numerous real-life problems. If the figure is in, like a circle, then we call it a fixed circle. If it is like an ellipse, we call it fixed ellipse. If it is like a hyperbola, then we call it a fixed hyperbola, and so on. So fixed figures have been investigated in metric spaces as well as in its generalizations like partial metric spaces, B metric space, MVB metric space, NB metric space, fuzzy metric space, and so on, exploiting numerous conditions and is fascinating problem to investigate. These geometric concepts resembles circle, disc, ellipse, and various other shapes and offer profound insights into behavior of self-mapping with multiple fixed points. So it opened up exciting possibilities for mathematical explorations and as well as practical applications. Suppose UD is a metric space and M is a self-mapping from U to itself. If we consider 3 points U0, U1 and U2 in this non-empty set U, and we consider R, which is a positive real number, then we know that circle is defined as the set of points such that distance of U from U0 is equal to R. Here U0 is the center of the circle and R is the radius of the circle. If place this equality by less than or equal to, then it becomes a disk. Similarly, we can define ellipse to be set of all the points such that its distance from 2 points U1 and U2, sum of its distance from 2 points U1 and U2 is equal to R. If we replace it by less than or equal to, it becomes elliptic disk. If we replace this positive sign by negative sign and take the modulus, then it becomes the definition of a hyperbola. And Cassini curve is a set of points for which product of distance from U to U1 and distance of U from U2 is equal to R. And Apollonius circle is defined as set of all the points U belonging to U such that distance of ratio of distance of U from U1 and distance of U from U2 is equal to R. Here U0 is not included in the set U. We define K ellipse to be the set of points U belonging to U such that its distance from U1, U2 up to UK is equal to R, sum of its distances. So the maps with non-unique fixed points can play a role in preserving certain geometrical figure. These geometrical shapes are collectively referred to as fixed figure, as we can say fixed circle, fixed Apollonian circle, fixed Cassini curve, fixed hyperbola, and so on. For example, if we consider a self-mapping defined as mu equal to u for all the points u greater than or equal to minus 3 and mu is equal to minus u for u less than minus 3, where u is nothing but a real number. In this case, the set of fixed points of this self-mapping M is denoted by fix M. And this is nothing but, fix M is nothing but minus 3 to infinity. Here 3 is included because you will notice that mu equal to u for all u greater than or equal to minus 3. So set of fixed point is the semi closed interval minus 3 to infinity. So if we define a unit circle centered at 0 and radius 1, it comes out to be set of all the point u such that modulus of u equal to 1. So it means what is minus mod u equal to 1? It means it consists of values minus 1 and 1. So it means this set belongs to this interval minus 3 to infinity. Means this is a subset of this interval because it contains minus 1 as well as 1. So it means we can say that this circle, this is a circle which is nothing but a set of point minus 1 and 1. This is a circle and in fact it is a fixed circle because these points belong to the set of fixed points. Similarly, if we replace it by less than or equal to, then we say that unit disk centered at 0 and radius 1 is defined as closed interval minus 1 to 1, and it also lies in the set of fixed point of M. So we can say that it is a fixed unit disk. Ellipse can be defined as a set of all the points such that modulus of u minus 8 plus modulus of u minus 12 equal to 6. This consists of points 7 and 13. And again, this lies in the set of fixed points as because it contains, set of fixed points contain both 7 and 13. So it is a fixed ellipse. An elliptic disk is this comes out to be closed interval 7 to 13. Hyperbola comes out to be set of points consisting of 8 and 6. Cassini curve comes out to be set of points minus 1, minus under root 7, 1 under root 7. And Apollonian circles come out to be set of points consisting of 18 upon 5 and 14 upon 3. One can verify that all these points belong to fixed set of fixed points of M. So we can conclude that set of fixed point of the self-mapping M includes unit circle, unit disk, ellipse, hyperbola, Cassini curve, Apollonian circle, because they are all contained in the interval minus 3 to infinity. So in other words, a fixed figure is a set of points in the function's domain where every point within that figure is a fixed point of the function. However, this is not always the case, as there can be a self map that preserve geometric figure while not fixing all its points. For example, if we consider a self mapping mu equal to 1 upon u, where u belongs to C, here 0 is not included, and value of m at 0 is 0. Then in this case, map fixes the geometry of unit circle mod u equal to 1, while it does not fix all the points. So this concept have been generalized and studied from various mathematical perspectives. These notions differ significantly from those traditional figures which we used to get in Euclidean spaces. The investigation becomes particularly fascinating and natural when dealing with self maps that possess non-unique fixed point. The exploration of innovative conditions ensuring that a given figure qualifies as a fixed figure presents itself as an imminent problem of significance in both practical applications and theoretical problem solving. These are some of the generalizations of fixed figure. First fixed circle result was given by Nihal Osgar and Nihal Tess. This was published in 2019. Although the means this was accepted in 2018, I think, but it got finally published in 2019. And after this, all these results were generalized. This was a result of fixed disk in rectangular metric space, fixed circle in rectangular M metric space. These are the generalizations of fixed circles. Again, fixed circle in multivalued. This is fixed ellipse which we defined, and these are more generalization: fixed circle and fixed disk in MVV matrix space. This again we give near fixed circle and near fixed disk in matrix. So there are so many generalizations existing in literature of fixed circle. These are also the generalization of fixed circles under different conditions in different metric spaces. This is fixed Cassini curve. This was given by Dhananjay Gopal in fuzzy metric spaces. So from various findings, we can draw the following conclusions. That circles and their generalization in different spaces may have shapes distinct from those in Euclidean spaces, and their shapes can change based on underlying metric and other parameters such as radius, center, major axis, and foci. For details, one may refer to these papers: fixed point to fixed ellipse in metric spaces and discontinuous activation function, and near fixed point, near fixed interval circle, and their equivalence classes in B interval metric spaces. Additionally, their fixed radii are not dependent on the center. Again, these are the works from one may refer. If we denote any figure as F, then uh, transformation under M of this figure F equal to F does not necessarily imply that F is a fixed figure of M. As we discussed in earlier slides, that all the points of the figure may not be fixed point. Self may not necessarily fix all the points of a given circle. When a self map fixes a disk or an elliptic disk, it also fixes a circle or an ellipse. But the reverse may not always be true. Fixed disk and fixed elliptic disk are not unique, and all disk and elliptic disk within a fixed disk or elliptic disk are also fixed. These are some of the references. Our recent work, if anyone interested in this direction, may refer to these papers. When the foci of an ellipse-like curve are concurrent, it behaves like a circle. Activation functions are crucial decision makers in neural networks, influencing learning and stability. Common activation functions such as ramp, RELU, and leaky RELU exhibit fixed point sets that include fixed figure. This highlights the significance of fixed figure outcomes in the context of activation function. Discontinuous activation functions such as Mexican hat type introduce non-linearity and offer storage capacity compared to their continuous counterparts. For further details and references on the topic, one may refer to these papers. So the study of fixed figure has been a subject of exploration in matrix spaces and their broader generalizations involving various contractive conditions. So this work provides a comprehensive exploration of fixed figures, focusing on the geometry of multiple fixed points across different spaces. However, there remains an open problem associated with hyperbolas. Because hyperbolas have two unbounded connected components, making it challenging to conceptualize the notion of hyperbolic disk. Because by disk we mean by definition is bounded, and this inherent bound nature conflicts with the unbounded characteristic of the hyperbola. So one may think in this direction also. So it is a fascinating question to investigate the conditions under which the bounded connected subcomponent of the hyperbola must contain a collection of fixed point. So there are many applications of fixed points in different branches. In real life, fixed point indicates a situation where a steady state condition or equilibrium is reached. For instance, in the context of gene network, fixed points are often seen as stable patterns of gene expression on the basis of particular biological processes. In economics, the Nash equilibrium of game is a fixed point of the game's best response correspondence. In compilers, fixed point computations are used for program analysis, for example, data flow analysis, which is often required to do code optimization. The vector of page rank, values of all web pages, is a fixed point of a linear transformation derived from worldwide web's link structure. However, in physics, more precisely, in the theory of phase transitions, linearization near unstable fixed point has led to the mathematical explanation of the critical phenomenon. Logician Saul Kripke makes use of fixed point in influential theory of truth. The stationary distribution of Markov chain is the fixed point of the one-step transition probability function. After locating these fixed points in a system, the stability of each fixed point can be determined, which enables engineers, scientists to establish how the system is functioning and responds to future conditions. There are some applications to system of equations. Suppose we are given a system of and equations in unknowns of the form like this, where gi are continuous real valid function of the real variable xj. If we write sj equal to gj plus xj for any point x equal to x1, x2, and xn, we define hx equal to h1x up to hnx. Then a fixed point x bar belonging to n-dimensional real space of hx is a solution of system of equations. So recently, we used different fixed point iterations to generate aesthetic fractals. What we did, we developed escape criteria using distinct iterations and then developed an algorithm to explore the fractals. We did estimation repeatedly for points x and y in the plotting region. Depending on the computational behavior, the color of the pixel is selected. The parameters are examined in every iteration to check if critical escape stage is attained or not. If this stage is attained, we stop the calculation, sketch the pixel. Then we examine the next x and y points. The
Professor
color of
Anita,
every point demonstrate the rate. Yes.
Professor Anita, could you please conclude? Could you please conclude?
Okay, no problem. I can conclude. Yes, I can conclude in 2-3 minutes. I will skip the portion. Okay, is it fine?
Yeah, it's fine.
Is it fine?
Yeah, it's fine.
So we
Thank you.
examine the next section. The color of every point demonstrate the rate of reaching the escape point. The black color generally demonstrate the parameters which do not succeed to escape prior to iteration limits. On the other hand, the brighter shade demonstrate escaping points. This provides visual description of the number of cycles necessary to attain the escape stage. So this is the definition of Mandelbrot set. I'm skipping because our time is almost over. And this is the definition of Julia set. And this is the Picard iteration. Everyone is aware of this. This is one-step feedback procedure. This is Mayan iteration. This is also one-step feedback procedure. This is Ishikawa iteration. This is Noor iteration. Noor is 3-step and Ishikawa is 2-step feedback procedure. And we tried to explore fractal for this particular function sin z minus az plus c. Here z is a complex variable and a and c are complex numbers. So this is the fractal which we obtained for in Picard orbit. You can see the number of colors are limited for in case of Picard orbit. This is a quantic Mandelbrot set in Picard orbit. In Mayan orbit, the figure is very colorful and there is a ring in between it. And if we increase the size of n, the size of ring also increases. This is quantic Mandelbrot set. This is septic Mandelbrot set in Mayan orbit. And this is higher order Mandelbrot set. As we increase the value of n, the fractal tends to be circular. This is in Ishikawa orbit. This is again in Ishikawa orbit. This is higher order Ishikawa orbit. This is in Noor orbit. This is like a swastik symbol, which we use in our homes also. This is in Noor orbit. This is again in Noor orbit. This is for higher order in Noor orbit. So these are some of the conclusions that we have limited number of colors for Picard orbit, and whereas for other iterations we get very colorful fractal. If anyone is interested, may refer to these papers. So I'm skipping the part. These non-unique fixed points also have applications in neural networks. I'm skipping this portion because there's no hardly any time left. So thank you very much. Hope I finished in time.
Thank you very much, Professor Anita, for an inspiring and interesting talk. And thanks for enlightening on the generalized figures. And thank you once again for your invited talk.
Thank you, Professor Anita Thomas, Madam. On behalf of organizers, I thank you for accepting our invitation and delivering this wonderful lecture, Madam.
Thank you.
Madam, I am Srinivas Rao, Organizing Secretary. Hello. Hello.
వినిపిస్తుంది చెప్పండి మాట్లాడండి సరే
Madam, very good evening. Very good evening, Madam. I am Srinivas Rao, Organizing Secretary of this conference.
Yes.
Thanks for your acceptance and your invited talk. Thank you very much, Madam.
Hope I try to finish in time.
Exactly, Madam. Exactly.
Yes.
Okay, Madam. Thank you.
Thank you. Thank you so much.
Right, Madam. Next.
Hello. I think I am Alamayo. You have jumped me above invited talk. There is one time remaining. I am Alamayo. I think you jumped me before the invited talk. 1% remaining. I'm online presenter, but you jumped me above Alamayo.
No, the paper presentations after one more invited lecture. We will call you.
Okay, thank you. Okay.
So next in this session we have one more invited talk.
Just 1 minute.
Madam, okay.
Madam, we are tell us, Madam. Yes, Madam.
Actually, I wanted to invite all of you to Rishikesh. Recently, I'm going to organize a conference on non-linear analysis in the memory of Professor S.L. Singh. If anyone or old researcher know him, so it would be my pleasure if you join us in Rishikesh on May 10th, 11th, and 12th.
So kind of you, Madam. Thank you very much.
Thank you so much.
Thank you, Madam. We are running 1 hour behind the schedule, Madam. So we are happy.
Okay, send your invitation.
Do send the brochure to the department, Madam. We will circulate it.
Okay.
Thank you, Madam. Now in this session, we have the invited talk by Professor Vasundhara, Madam. And I request Sujata, Madam, to please chair the session.
Good afternoon, one and all. It's a great privilege to introduce our beloved mentor, Professor Vasundhara Devi, a paragon of mathematical genius. I want to tell this, and a beacon of knowledge in the realm of numbers and logic, and profound insights and innovative approaches. Approaches have not only enriched the field of mathematics, but have also ignited a passion for the subject in the hearts of countless students. With an illustrious career adorned with accolades and ground-breaking research, Professor Vasundhara stands as a towering figure, inspiring a new generation of the thinkers and problem solvers. After pursuing your CV, madam, I want to write this problem solvers. And today we are honored to have our share and our wisdom and experience and guiding us through the fascinating world of mathematics. Professor J. Vasundhara Devi, Professor in Mathematics, GVP College of Engineering, Visakhapatnam. She completed her PhD in Qualitative Behavior of Impulsive Differential Systems under the guidance of Professor V. Lakshmi Kantam, Florida Institute of Technology, Melbourne, Florida, USA in 1992. MPhil and MSc in Andhra University, 38 years of teaching experience regarding research experience, research professor for International Federation of Nonlinear Analysis from 2005 to 7, postdoctoral research fellow, Florida Institute of Technology, Melbourne during 23rd May to 4th August 2003. 3 students obtained MPhil and 6 students obtained PhD. 1 is submitted thesis and 3 are registered for PhD. Research projects completed DST project from 2009 to 2012 and the NBHM National Board of Higher Mathematics project in 2000 from 2012 to 2015 and sub DST project is undergoing from 2017 granted. Then she is having many research publications, edited volumes, editor-in-chief. She is a member of many editorial boards like Journal of Malaysia, Journal of Mathematics, Journal of Nonlinear Studies, Journal of International Federation and Nonlinear Analysis, Journal of Fractional Dynamic System. She is a reviewer for many journals like American Mathematical Society Reviews, USA, Journal of Australian Mathematical Society, Australia, International Journal published by the Elsevier Springer, last madam. For many other journals published from various countries, she authored many book chapters. She is having 100 research publications and presented many papers in various international national conferences. She is life members many societies. She organized many conferences and workshops. Almost every year she will organize any conference seminar. And still many are there in Madam CV. So, now, over to the Madam. Thank you, Madam. No, I invited Madam to give a research talk.
Thank you very much, Madam. అవన్నీ అబద్ధాలను అనలేను కానీ చాలా ఎక్కువగా చెప్పారని మాత్రం అనగలను. I think it is unnecessary. You all of you know me as from a long time, and I am what you know, and that's enough. Thank you very much. Masharu KPR Sastri gariki అనేక నమస్కారాలతో, and with all respects to all the other members, some of Dr. Ravinath Babu garu, KM Sharma garu, all of my seniors, Dr. Venkateswarlu, my whole contemporary and peer, Dr. Murthy garu, Dr. P.N. Srinivas garu, Dr. Nanaji garu, and all other illustrious persons, Dr. Anura Kameswari garu, Dr. Sujata garu, and everyone. మీరు కూర్చోలేదు, కనిపించలేదు. So if I missed anyone, I'm so sorry. My respects to each and every one of you, and greetings to all the youngsters. I am putting this talk in honor of Professor Meenakshi Sundaram garu, for the simple reason that Professor Meenakshi Sundaram garu was responsible in some ways for the PhD of Professor Lakshmi Kantam garu, who is my guide. So with all respects to him, I thought as the conference is also in supporting SMS association, so I thought I would dedicate this talk to Professor Meenakshi Sundaram garu. Okay, and my area is, I'm going to talk right now on fractional differential equations. But before that, let me just introduce fractional calculus. Now, if there is a repetition, I would like to avoid this part. Can I continue, or do you want me to avoid it? Okay, fractional calculus actually came up with a question by Leibniz. he introduced the notation for the nth derivative dnx by dtxn. Then L'Hopital asked him what happens if n equals to half. So that query led to many mathematicians of that era working in that area, and they all came up with different notions, trying to understand what it means. Now I will just give you a simple example to introduce this concept in mathematical modeling. So we have illustrated this with an example. Now, if you know the stress-strain relationship in viscous fluids, it follows that notion sigma t is equal to, it's actually proportional to first derivative of epsilon t, or sigma t equals theta derivative of epsilon t. And Hooke's law for modeling stress-strain relationship for elastic solids follows that rule. So if you want to model a viscoelastic material, then automatically you're going to get that form. Sigma t is equal to nu d to the power of k epsilon t, where d to the power of k denotes the kth derivative. So that k should be between 0 and 1, which is logical. So the concept of a fractional derivative occurs naturally in the setup. So how would you define a fractional derivative? So that question came up and people started thinking in various ways, and all of us know as mathematicians, we try to generalize things. And as a part of generalization, there are some things that we observe, that derivative and integral are inverse of one another. And this Cauchy's formula, which says that n integrals can be reduced to one integral in this form. Okay? So that in f of x that n denotes n iterated integrals, and this formula is one that is already known, very well known. So someone said, okay, in place of n, if I put q, what would happen? So that's what they did to extend in the fractional case, so q belonging to R. So exactly what they did was wherever n is there, they put q, and as gamma function is a generalization of factorial, so in place of n minus 1 factorial, they put gamma q. And that's how they define the fractional integral. This is again the gamma function, just to give a feeling of it. And this Mittag-Lagrange function is nothing but a generalization of the exponential function. If you replace the gamma with factorial, you can clearly see that exponential function coming up. Now, the Riemann-Liouville integral, which is a very famous standard fractional integral, was defined again using that in function which I have introduced before. So in place of gamma q, if you put the factorial, and in place of q, if you put the n, you can see the standard integral that was already there. And therefore, okay, I have to give you this notation. We have used d minus q, and I've said it's fractional integral. So d denotes the derivative. D power q means the qth derivative. Because we have written d minus q, it will denote the integral. Okay. I hope I'm not going fast, but okay, sorry. So here is the fractional Riemann-Liouville fractional derivative. Can I use the board, please, so that it will be easier for you to follow? Chalk piece. Chalk piece.
Next.
Chalk piece. See, what happens is the derivative, as is in the ordinary case, we observe that the derivative and the integral are reciprocals, but there will be small differences in them, which I'm not going to go into the details of it. But what I would like to show you all is that if you have q is any real number, then we are going to, if q is any real number, we are going to introduce that q is between n less than q less than n plus 1. So you take this into understanding that d to the power of q can be written as d to the power of n minus q plus n. It's like similar to just an understanding. Okay. Now this or I'm going to write this as minus n plus q. Okay. So basically this t minus n will be the integral and t to the power of n plus q will be the derivative. So that's what we have done over there. I can write this as actually t power n, t power minus n plus q, and therefore the nth derivative over there and the integral involving the fractional. This is the nth derivative and the integral inside is t minus n plus q. So basically, with that definition, Riemann Liouville has given the fractional derivative, and with that derivative, what happened was when I take the derivative of a constant, fractional derivative of a constant, let's say 1, then it is not 0 because it went into the integral. After the integration, we have done the differentiation. Therefore, it is not going to be 0. So then, what is happening? The original ordinary, if I reduce the q to an integer, the standard results are not coming true. So then, what happened? Caputo is one guy who said, okay, we will change this notation. Instead of writing like this, we can write like t to the power of minus n to t to the power of n plus q. So the integral is outside and the derivative is inside. So once that happens, what happens if you look at the case where q is less than 1, you can see over there that the derivative is inside. So when I take x as a constant, the derivative of a constant becomes 0 and therefore the results will hold. So what happened is with this Caputo derivative, the standard result of the derivative of a constant is 0 for integer derivatives holds good. Therefore, this Caputo fraction derivative has gained attention of most of the researchers because it stood up to the concepts of the ordinary derivative and the initial conditions could also be used in the applied in the fractional case as is given. Now, how do you find the solution of a nth order linear fractional differential equation? So we will look at the first ordinary differential equation. All of us know for the differential equation 1, the solution is 2. So what they did was, they instead of writing d dash is equal to ku, d is equal to ku, they have written dn to the 1 by n equals to ku. That 1 by n is the fractional part and nth derivative of the fractional part. They get this gimmick, and as I said earlier, exponential function plays the role of Mittag-Leffler function plays the role of a exponential function, and we know that the first order linear differential equation solution is exponential function. Similarly, you can show that for the nth order differential equation, fractional differential equation, you get that summation involving the Mittag-Leffler function, where you can see that the roots are the characteristic function of r power n equals to k. Okay, so in place of d power n equals d power 1 by n, you take it as some k. So k power n equals to ku is the fractional differential equation, and you get n roots. Similarly, you can work with it. Okay. Okay. So you will observe that the linear or ordinary differential equation and the fractional differential equation are same because you have just changed the notation. So you equate them and you come to an understanding that and work with them. It will work out. So I'm not going to the details over there because it will be difficult to follow. So now you look at that equation 5. In place of Qn, if you just put the N, ordinary N, you can see that it's a linear, non-homogeneous fractional differential equation. But the Qn may be of any order, so they try to reduce it to get some sense out of it. So how do you do that? You assume that Q is the greatest common divisor for Q1, Q2, Qn in 5, and then reduce into a form like this, where it looks neat. So if I write b power q as some k, then it will be k to the power of m plus b minus 1 k m minus 1 so on. It will look like a nice differential equation where the fractional operator is there and you work with it. Okay? మీరు ఆపరేట్ చేస్తున్నారు. So if we know, all of us know if you have a non-homogeneous equation, we write down the characteristic equation. That's what they did over here similarly. And also because the m roots are distinct, you get a similar solution. The work is similar. Okay. Next. Next. So if the roots are repeated, you get a similar solution. Next. I just wanted to show you all. Actually, I wanted to talk about stability, but before doing that, I just wanted to show how linear system, the equations or solutions will be there. Because what I basically wanted to show was, for an ordinary differential equation, if you want to talk about stability, all of us know that if the roots are negative, then we can talk about stability. We have the stability for the system. The same results actually hold over here, but they have an extra condition that the roots really need not be negative. Okay, the next one. Next one. Okay, maybe I lost it somewhere. So if you see this, suppose there are roots over here, then even if some of the roots are non-negative, then also this system will have a stability. That's the extra property we get. That's what I wanted to show because we are talking about stability. So even for linear differential equations, fractional differential equations, when the roots are non-negative, we may still get stability in case of fractional differential equations. Next. So when I wanted to talk about stability, let us consider the layman's view. Say for example, if I have a single pole, if I just give a push, it will not be stable, it will fall down. But suppose there's a two-legged stand, then also the stability will not be that much. There will be, if you push it a little harder, it will fall. Now if we have a tripod-like thing, we know that we need a little more strength for it to push down. The stability is more. And if we have a bench with 4 legs, then it is very, very stable. So the concept of stability varies this is the idea of stability. That is, small changes or small pushes or small perturbations should not change its behavior or must keep it intact. Now, when it came to the first concept of stability came with mechanical systems and what we call as critical points, and we work with them. That's the idea over there. So you consider the critical point and you talk about stability around the point. But what happened was, Lepenow is a mathematician who had actually was given his thesis in 1892, and he said that without knowing the behavior of the solution, he stated the stability of the system. That's the genius of that scientist. So basically, that's why Lepenow system had become very, very famous, and people started working with it. Actually, there are more than 200 books on Lepenow stability, and people started working it, extended it, generalized it, refined it. There are millions, there are lots of works on it. Okay, so this Lepenow concept, what it does is that it tells you the behavior of the solution without knowing what the solution is. Actually, I put this result here. which I told you all that even if the Ri is positive, we can get a stability. Next. You can just see the result. I already talked about this. So Rj bar should be negative, where Rj bar is nothing but Rj bar A, which is the Rj is the root. So even if the Rj is negative, Rj bar can, if Rj is positive, Rj bar can be negative and you can get up to it. Okay? So that's how you get the stability. You can talk about exponential stability over here. Next. Next. So various concepts, stability concepts for general fractional differential equations. So we consider the equation 11, which is a Caputo fractional differential equation, initial value problem. We assume that the f is continuous. It is defined in a region D, and it is smooth enough to guarantee the existence and uniqueness of solutions and the continuous dependence on initial values of the solutions of the equation are there. Okay. Now, what we need to understand is that the stability is actually continuous dependence in one setup, and I am going to draw a small figure to explain to you all the stability concept, which actually is also continuous dependence of solutions on initial values. So what happens is, suppose we are trying to launch our satellite vehicle, say from Sriharikota, say, then what happens? We do a lot of simulation, we do a lot of research, saying that for all various parameters, we are going to launch the satellite. All simulation is done. So for understanding, let us say we'll take temperature, wind speed, and humidity as 3 parameters that you will understand. So they have done a lot of simulation between the temperature, say, should be between 20 degrees to, or let's say 27 degrees to 28 degrees centigrade. Then the wind speed should be from 1 knots per hour to 2 knots per hour. And the humidity is, say, from 65% to 66%. A lot of simulation is done, and the procedure is they have seen that the satellite launching will be done. But on the day of satellite launching, all of us know that if the weather is bad, they are going to cancel the launch. But suppose the wind speed is like, say, the temperature is, say, 26.9 degrees centigrade. The wind speed is 0.9 knots per hour, and the temperature is, say, some 66.1 degrees centigrade. 66.1%. Should we launch or should we not launch? So what is happening? Our initial values are some, say, x naught, but there is a small deviation and we are having with an x naught bar initial value. Should we launch our satellite or should we not launch our satellite? So for that consideration, what I do is, if we say that this difference is less than some delta or something, then can we reach what we want to do? So for that, there is a procedure which is actually similar to the limit concept, because all of them are limits. Basically, everything is a limit. So if we understand the limit concept, we have continuous dependence, stability, and everything. So suppose I want to launch my satellite somewhere over here in space. So if I want to launch here, I will not give this, but I will say that in some neighborhood. So I will say in epsilon neighborhood, I want to launch my satellite. So once I do that, then if I come back here and say, if I want to fall here, what is the error that I can make? So if this is the error that I can make to reach my goal, then we say that we have continuous dependence of solutions, because even if there's a small change in the initial value, you're going to get a new solution. That new solution also will be follow the same pattern. So basically, that is what is continuous dependence of solutions, and that is what is stability. In fact, this is also the limit concept. So with this understanding, we will go to the next slide. Next slide, please. Next slide. So what is happening? We were talking about critical points in Lyapunov theory. In Lyapunov theory, we are talking about the solution in a critical point. We are talking about 0, 0 as the equilibrium point. So we try to link both of them. For the system plan to have a critical point 0, 0, what we need to have is that we need that condition 13. Okay, without that condition 13, x of t is identically equal to 0, will not be a solution for that system. So to get that, we need the criteria 13. Next. Okay, how much? I think my time is nearly up. So if there is no zero solution, if you have to study about stability about another solution, what you do is you make a transformation y equals to x minus 5 and reduce it to a new system so that you have the zero solution and you can talk about the stability of the zero solution. I think I'm nearly done so far. Next. So these are the concepts of equistability of the focus. Okay, let us look at the stability concept clearly, and then we will, in couple of minutes, I'll finish all the stability properties. So we have a solution, zero solution, and let xt t0 x0 be any other solution starting at t0 x0. Then when we say that, okay, I'm going to finish off the stability definitions in using the figures. So what happens is, suppose this is the zero solution, and our t0 x0 is some point over here. Say, let's say t0 x0 is some point over here. So for the system x of t identically equal to 0 to be a solution, if I take plus epsilon and minus epsilon in some region, then our solution that starts over here must be, if it starts in the delta region over here, then plus delta and minus delta, it will remain in this epsilon region. That is what will give you the stability concept. Now, if uniform stability means if I start at any other point, t1 x1, t1 x1 say, within this delta region, then also the same thing must hold. That is, this delta will be independent of t1, t0. Then that's when you say that it is uniform stability. When we talk about asymptotic stability, what we say is that after some t, before some t, the epsilon, the solution starting at t0 x0 can go in any other way, even above the epsilon. But after the point t, it should slowly go to 0. So this is what is asymptotic stability. When we talk about this t can depend on epsilon and t naught. If this t depends only on epsilon, it becomes a uniform asymptotic stability. Okay. Now I would like to only talk a little about these are the stability concepts, and there are theorems talking about giving results when we get stability and etc. under what criteria we get stability. But there are different concepts. One concept that I'd like to introduce to you all is these have been extended variously, and what one concept is practical stability. For practical stability, what it does is this. So if I talk about stability, by the definition of stability, an aeroplane that has gone through turbulence is unstable. Because when I give you an epsilon delta region, an aeroplane, when it goes through turbulence, it goes like 1,000 feet up and 1,000 feet down. Suddenly there's a lot of oscillation. So theoretically it is not stable, but practically it is stable. So they introduced a concept called practical stability. And then there is another concept which is very interesting, which is called as stability in two measures. What they did was, there are many various concepts of stabilities. We have only seen stability, asymptotic stability, uniform asymptotic stability, but there are properties like eventual stability, partial stability, and so on. So someone came up with the notion: can we put all these in one definition and study? So what happened was they introduced the concept of what is called as stability in two measures. So what happens is there are two measures, H0 and H1, which will act as our normal distance function, our modulus function, or norm function, depending on where we are. And these concepts are introduced, and stability in two measures have also been studied. All these results have been extended for fractional differential equations. There is a lot of work that has been done, and I know I'm overrunning, so thank you all so much for giving me this wonderful opportunity. I am indebted for giving me an opportunity to talk here. Thank you so much. Namaskaram.
Thank you, madam. Any queries? Any questions from the audience? Thank you so much, madam. On fractional differential equations, we taught fractional integral, Riemann fractional derivatives, nth order, linear order differential equations, nth order, linear fractional differential equations, and Lebnow's stability and the different types of stability and all we taught. Thank you so much, madam, enlightening lecture. Thank you. A small felicitation.
Let's have a look at the differential equation from mechanics point of view. Suppose if you look at the ordinary differential equations, you attribute velocity to dy by dt. You attribute to acceleration to d square by dt square. Suppose I want to talk about d 3 by 2 by dt 3 by 2. What do you think I attribute to this particular derivative?
But I think I do not know basically. But what they say is, as I give you the example of BCom, the concepts that have third derivative and fourth derivative, if there is a concept that is involved in between, you can actually model it to a fractional differential equation of the kind. So if you have a third order differential equation and a fourth order differential equation that is coming up in modeling, and if there is a concept that comes both of them, then obviously the relation should be in between 3 and 4 orders. So you link it up to something like a fraction derivative. That was the example that I gave you to the stress strain relationship of Newton's law and the Hooke's law. So you have to generalize that. Basically, I do not.
Some sort of continuity between 2 and 3 or 3 and 4.
That's all.
That's how you have to look at it as perhaps.
Perhaps.
Thank you.
Chairman, no, this is formality. So, no, this is a courtesy, madam. Please. So I request Professor K.P.R. Sasaguru, Chairman of the Association, please to honor it. J. Vasundhara Devi garu.
Organizing committee.
Yes, and all the faculty members are please join us.
Sir, please.
ఇప్పుడు
Thank you very much.
Thank you very much, madam, for your wonderful invited speech. And next we have some more paper presentations. So all the paper presentations in this hall only. Any more offline presentations?
Small interruption, madam, please. Before, sorry for interruption for the usual schedule. Our student
Offline and online in this hall only. Before proceeding with the online paper presentation, are any more offline paper presenters here? Yes, two more remain.
let them complete with offline. Then they will move on to online.
Photo, please. Sunil, please come. No. For photo. Yes, come. Sorry. Please. Please, all the staff members, please join with us. Please come. I request all the staff members, please come and join with us for photo session. Sunil sir. Our president, please, KKM Sangharam, please come and join with us. Amen, sir, please.
Thank you, sir.
Madam, please proceed, madam.
We have some more paper presentations, offline and online. Before proceeding with the paper presentations, one of our MSc students, she wants to give a lecture on review lecture, applications of group theory. Yes, so we welcome her. So we can say it is an invited lecture too. It is one more invited lecture. Online ICPAEMS we have two offline and some we have a
ICPAEMS
Introduce yourself and start.
Group theory, yeah?
A great class, good evening to one and all. I am Vasavi. I am a student of first year MSc Mathematics in this prestigious Andhra University. I feel privileged to share my presentation in this international conference. Before getting into my presentation, let me discuss something noteworthy. We all belong to a family, aren't we? Yes, we all belong to a family. We all belong to mathematical family. Isn't it? Yes, we do. And we all knew this, the prominence of mathematics and its applications. How these mathematical applications are used adversely in all the other fields and in many other dimensions. We have been using these applications of mathematics from Stone Age, and we were still using it in more advanced way. And I promise you that we are going to use all these applications in our future as well in a more effective and in most efficient manner. I hope everybody is going to accept with me. Yes. Let's get into, I think everybody got my point at what am I going to explain today. My topic is based on completely applications. It is based on completely applications, and as we all knew, these applications of mathematics are as vast as an ocean. So I have chosen a part of it that is from abstract algebra, that is from applications of mathematics. Sorry, applications of group theory. How these applications of group theory is useful for the development of the country and as well as the world. We all knew this. What is a group theory? Group theory is a branch of mathematics that deals with study of symmetry, structure, and it provides a framework for understanding the properties of algebraic structures and their applications in diverse mathematical domains. This group theory is a tool to determine symmetrics and structures. It is coined, the group is a term coined by Galois around 1830. And this group theory is also called as symmetric theory. Welcome to the power of group theory and the applications of mathematics. In this presentation, we are going to explore practical applications of group theory in various fields. Before getting into that, we are going to use these basic applications. By using these basic theories, we are going to use in applications. Group operations, subgroups, and group homomorphisms. Applications of group theory. Applications of group theory in computer graphics. Computer graphics. What is meant by computer graphics? Computer graphics is nothing but a technology which is used to generate a digital image on a computer screen. We more often see this in photography, cinematography, video making, and whatnot, even in the televisions as well. This is well known to each and everyone. This group theory is used to analyze, transform, and in 3D modeling of computer graphics. Analysis. Group theory enables the systematic analysis of geometric transformation in computer graphics, facilitating the understand the symmetric and patterns within the visual data. Transformation. Utilization of group theory in computer graphics algorithms can efficiently represent and manipulate complex transformations, ensuring accurate rendering and manipulation of 2D and 3D objects. 3D models. Group theory principles underpin the development of algorithms for creating, transforming, and animating 3D models in computer graphics, enabling realistic features to the virtual environment. Applications of group theory in robotics. I think no one in the seminar hall might be immature to the word robot. We all knew this. The robots are future to us. And this, what is meant by robot? A robot looks like a human being and perform all the complex activities that are done by a human being. The study of robots is simply called as robotics. To create a robot, this group theory is highly essential. To analyze a robot, to enable a robot, and to optimize a robot, we use this prominent theory called group theory. Analysis. Group theory provides a framework for analyzing kinematic and dynamic properties of robotic system, facilitating the understanding of complex motion planning and control strategies. Next. Enabling. By leveraging group theory principles, robotic engineering can enable robots to perceive and navigate their environmental more effectively, leading in advancement in autonomous navigation, manipulation, and coordination. Optimize. Applying group theory concepts allows optimization of robotic trajectory, joint configuration, and task execution, leading to enhanced performance, energies, efficiency, and overall system effectiveness. Application of group theory in crystallography. What is crystallography? Crystallography is nothing but study of crystals and its structures. Crystallography means it tells the arrangement of an atom in a crystalline solid, and it also binds the atoms together. In this crystallography is completely based on chemistry, but moreover, we use math applications, that is group theory. Symmetric analysis. Group theory is used to classify, analyze the symmetric properties of a crystal. Crystals exhibit various types of symmetric operations as rotation, translation, reflection, inversion. By applying group theoretic principles, crystallographers can categorize crystals into different symmetric classes and understand their structural characteristics. Applications of group theory in crystallography is also used in space group determination and crystal structure prediction. Crystal structure prediction is nothing but predicting, means guessing the structure of the crystal. Application of group theory in genetics. Application of group theory is also used in genetic code as well. What is meant by genetic code? It is a key structure. It sets a instruction for the gene to help or to make the protein. Gene means nothing but it tells the cell to make a protein. And it is also mostly helpful in this. Even though this is a biological concept, we use this based on this mathematical group theory. By using this group theory applications, we are going to correct errors in this DNA mechanism. Next. Evaluationary constraints and structural properties are also going to be studied by using this group theory application in this genetics. Next. Real world. Up to now, we have discussed only a few applications of group theory, and now let's have an eye how this group theory is going to impact on the real world. Real world impact. Real world impact of group theory extends to diverse aspects like engineering, medicine, finance, and information technology. Its applications continue to drive innovation and advancement across various domains. And I couldn't stop myself by concluding this, that the power of group theory in mathematical applications is undeniable. Its impact spans across the diverse fields driving innovations and shaping the future of technology and scientific discovery. So, we mathematicians, now the ball is in our hand. So, we are the torch bearers for our future generation. The future is still in our hands. So, I feel very privileged and thankful to be a future mathematician, and thank you so much for giving this great opportunity. I feel privileged. Thank you.
Thank you very much, Vatmi. Very nice to see younger generation interested in research of mathematics. We would definitely want to encourage you. I request Professor KPR Shastri garu, please bless her with this token. Yes.
You have to study further.
We are mathematicians.
Lecture by politicians. No. So, we should do that in future. Thank you. Thank you. Prominent computer scientist. I'm honored to say that. There like that. Okay, thank you.
Thank you. Now let's have the paper presentation session. Ma'am, I request Professor Vinita Madam to please chair the paper presentation session. And even Nanaji, offline paper presentations kuda kontamandi exunnadu. Please chair the session. Offline paper presentations.
Six ఉంటుంది ప్రాపర్ ప్రెజెంటేషన్స్ గోల్డెన్ రేషియో సైటింగ్స్ సిక్స్త్ పేపర్ అంటే నా దృష్టిలో సెకండ్
Good evening to all professors, scholars, and my dear friends present over this gathering of the international conference organized by Andhra University, Visakhapatnam. Myself, Dr. Prashant Sutkar, working as an assistant professor in Science College, Nanded, Maharashtra. It's this college, and it's one of the oldest college from 1969. So, my topic of presentation is micropolar fluid wedged between viscous fluid saturated with nanoparticles. This is the outline of the presentation. That is fluid. Fluid is a substance which can flow, and fluid is classified into compressible, non-compressible, and also Newtonian, non-Newtonian. Newtonian fluid means that obeys Newton's law. Non-Newtonian fluid that does not obeys Newton's law. For example, jelly, some blood, and others. So, viscous fluid. I have considered here viscous fluid and micropolar fluid. Micropolar fluid is a fluid in which there are micro rotations like our blood or any other animal blood, and fluid flowing channels. And I have considered heat transfer in the flow. So this is physical configuration of my presentation. It contains three regions. Region 1 and region 3 is filled with viscous fluid, and region 2 is filled with micropolar fluid. With that, in region 1 and region 3, there are some pores or the fluid which contains pores, or it contains pores. And in region 1, 2, and 3, there are nanoparticles that are highlighted by colored spheres that may be green and all. So this is the geometry. So these are mathematical formulation which contains BNF, that is viscosity of fluid in region 1 and region 3. KNF is the thermal conductivity in region 1 and region 3. BNF by K is the porosity parameter, and delta P or delta X is the pressure gradient used in region 1 and region 3. These are governing equations for region 2nd. And these are governing equations for region 3rd. There are 14 boundary conditions, out of which 8 are velocity conditions and 6 are temperature conditions. So these are the temperature conditions that we can see. So using the governing equations are non-dimensionalized using the governing parameters as can be seen on the screen. So these are the solutions of the governing equations obtained in 6A, 6B. So the equations are highly nonlinear and they are coupled. So any exact solution cannot be calculated. So I have used the perturbation method, and using perturbation method, I have the solution that is for velocity ui, temperature theta, and micro-rotation velocity ni. So the parameter perturbed is what? Epsilon is nothing but EC into PR. So using perturbation method, I got the solution that we can see the first order, zeroth order, and first order solution. As we can see, it is given by theta 11, theta 21, u11, u21, and zeroth order solution for in absence of material parameter K that we have theta 10, theta 20, theta 30. In that way, we have the solution for case 1, that is in absence of material parameter. So it is followed by case material parameter in absence of material parameter. In the absence of viscous dissipation and material parameter, we got the equation, the simple equation which can be solved by exact solution. So we have exact solution, and using the solutions and boundary conditions, I have plotted the graph using the software Mathematica and Origin. So this is the sketch for temperature for material parameter that we can observe. As the material parameter increases, the temperature decreases. So sketch for velocity and micro-rotation velocity for distinct solid fraction. In region 1, region 2, region 3, there are nanoparticles. The nanoparticles used are graphite oxide, magnesium oxide. So these are the temperature profile for distinct nanoparticle or distinct material parameter. For the values are taken from in absence of material parameter, and that is for unit 0.5. Next one. So these are the sketches for velocity, micro-rotation velocity for distinct porosity parameter, and this is the temperature profile for
Last one.
material. Okay, this is. There are many tables which highlights the relation between material parameter, viscosity, and the effect of nanoparticle on the geometry or on the figure that can be highlighted as in configuration. So this is the variation for cell rotation viscosity. So the table drawings are like this. So I have used many references, but some of which that are highlighted by 1, 2, 3. So I thank the organizer for giving me an opportunity to discuss the details of my research work here. So due to time limit, I am unable to explain the nature of the graphs. So I thank once again for an opportunity. Thank you.
Thank you, Prashant Garu.
Next slide presentation. Almayu, are you able to hear? Yeah. Are you ready with your presentation?
Yes.
I
Yes,
think,
yes, I'm ready. Yeah, madam, I'm ready. Yes, thank you.
yeah. Welcome to the presentation. Just you can start your presentation. Title is Fractional Polynomial Mixed Effect Model for Variations of Children Weight, Trajectories, and Determining Associated Factors. Yeah.
Okay.
Just, time limit is 6 minutes. Just present your start your presentation and try to conclude it within 6 minutes. Open your presentation. I think we can see your screen, but open your presentation.
PowerPoint Halgabali.
Yeah, PowerPoint.
Yes, madam, is that visiting?
No, no. No, no.
The screen is visible, but presentation is not right. Open your presentation. We can see only empty screen.
I'm asking to open the PDF tab.
Almain, just open the PDF one. I think you are done with PDF, no?
I think need to be visible. Is that visible? But I can open the PowerPoint.
But it's not visible to us. Open that one.
We can see your screen.
Your empty screen only we can see.
Okay, okay.
Open that PDF once.
PDF tab.
Okay, madam. I can't share, madam. How? I can't share. Madam.
Yeah, Almain, PDF tab is there, no?
Yeah, I can share it. How I can share it?
Left hand side. Your third tab, I think. Open the third tab on your screen. You have 4 tabs, no? Third tab is PDF, fourth tab is meter. Open the third one.
Okay.
Just the tab before the meter one.
Yeah, already the tab.
Yeah, open the PDF.
Yeah, I opened that one. Yes, here I have clicked. Please present now. I clicked present now.
Yeah.
Entire screen.
Click on entire screen.
Click on entire screen.
Entire screen. Okay.
Yeah.
Share.
Now start sharing.
Okay.
But your
Now I can
PDF
open the PowerPoint.
Yes, open. Yes, we can.
Yeah, open the, yeah.
Now it is open?
Yeah, it's open.
Okay. Sorry, the disturbance. I am Alamayo. This is what.
Time limit is 5 minutes. Do it quickly. Right.
Yes, this is fractional polynomial effect model for variation of children weights, growth trajectory, and its associated factor in the four low and middle income countries: India, Ethiopia, Peru, and Vietnam. I am Alama Yusuf from Ethiopian Scholars here, AU, and my research guide is Professor Munsabi from Department of Statistics. So this is first. I say thanks for the organizer here, the ICPAEMS organizers. So the outlines you have introduction, literature, and methodology and results. So I will based on introduction, method, and results parts. Under the introduction part, a children physical growth rate is the best predictor for their eventual physical weights. Biological, socio-economic, environmental, and maternal factor affect children's weight growth. And it seems like that for the introduction part. Here are random fit measures weight growth variability across individual, accounting for genetic, environmental, other individual specificities that are not included in fixed effect. This random effect measure, those are not included in fixed effect. Researchers use random effect in the model to account for variability and individual variations, improving prediction and improving insight to the factor affecting children weights. And I will say something about the statement of problem. Let's see the first two ones. Understand the variation in children with growth trajectory. That means researcher on children physical growth is limited. So understanding variation in weight growth trajectory among different population is crucial. The second one is identifying factors that influencing the children with growth. There is a lack of comprehensive research that identifies and quantifies the various factors influencing children with growth trajectory in diverse socio-economics and environmental context, and others also there. The other is there is a research gap is there, but after all the research gap, however, none of the previous study did not analyze variation of children weights, growth trajectory, and associated factors. So this study aimed to analyze variation in children weight growth and identify associated factor in the four low and middle income country, India, Ethiopia, Peru, and Vietnam, using fractional polynomial models. Significance is the first one. This study has significant implication for public health policy and intervention aimed at improving children growth and developmental globally. Madam. Hello, madam.
Yes.
Yeah. Is that okay?
Yeah, it's good. You are left with results and conclusions.
Yes. Okay. Literature also yes. Let's go to the methodology parts. This is the data taken from the longitudinal data taken from UK, United Kingdom Data Service, which manage and distributes the Young Life Study projects. By using this link, the researcher will be registered on them. Then they have given some user and passwords. Then you can take the data. 5-time measuring goes 7,140 children from all the 4 countries, yields of 35,700 observations. That means one children will be observed 5 times. The response variable will be the weights and have different predictor, different independent variables. This is a model. This is, I think, the application of fractional polynomial mixed model. That's the application. Then both random intercept and random slope can be included to capture the variability between cluster and subjects in terms of their baseline levels, a rate of change over time, as they said. We have given the equation is here. So here we have, that means let's back out the equation. Here we have the powers. That those 2 powers, a combination of 2 powers will be selected. That means Pj, maybe it is -1, -2, -1, -0 this fraction, or 0 on 2, 3. Among all the possible combination of those powers, the best fitting model is evaluated based on its deviance AIC and IC criteria. That means basically this will be selected, the combination will be selected. Most times this is started doing this one to select which one is best, which one is fitting the data. Okay. The other is what the estimation we are using maximum likelihood estimations. The maximum likelihood involves estimating both fixed and random effects. The estimation is typically carried out especially statistical software, which is mixed effects. That means Yes.
Conclude your presentation.
Okay. Conclude my. But let's say one or two slides to say the main one. Here are what rate of changes. I think the table we have this one and instantaneous rate of changes. From here we can get the derivation of this one. For India, for Ethiopia, for Peru, then we can get the graph of this one. The graph of this one means it indicates that this the first one is that means the plot of change weight growth rate by countries. For example, this one there are four plots. That means Peru is better than Vietnam. Vietnam is better than India. India is better than Ethiopia. Ethiopia has among the four halves low growth of rate in children. The same as for child here, I think the child no significant. The same as for rural areas, urban and rural area. Rural area have growth significant growth rate of the urban areas. Thank you. The conclusion that means the result contribute to understanding children weight growth trajectory variation and their associated factor in the four low and middle income country. The longitudinal weight growth of children was significantly enforced by country, sex, residence, parental education, household size, wealth, access to safety drinking waters, access to reliable electricity. Those are significant factors for children weight. However, education levels of mothers and fathers and access to sanitation were not associated to trajectory of weight of children. They, yes, there was a variation in, yes, madam?
Time is up.
Okay, 1 minute. 1 minute. Okay, there is a variation in children weight growth rates among the four low middle income country. So further, the Peru had higher rate of growth than the others. Therefore, organizations like WHO and the nation or the country Ministry of Education should, the country of Ministry of Health should pay close attention to children weight growth status and those related factors to plan for future actions. In contrast, it is low in Ethiopia after early infancy and in India during the initial years of life. The finding of this study can be used to identify disparity or variation in children wages. As a limitation, our study have some limitations that means mostly related to a small number of variables like birth weight, body mass index, children nutrition status, healthcare consumptions are not included in the UK data. For further, they are recommended to include those variables. So this is a recommendation like competition for those variables. That is all of them. Thank you.
Yeah, thank you. Thanks for your presentation.
Thank you.
May I call the next presenter, Anila Badimala?
Yes, I'm there. Just a second, I'll share the screen.
Yeah. Start your presentation. Title is Reducing Lattices and Introduction to the LLM algorithm.
Shall I start my presentation?
Yeah, Anila. Anila, you can start your presentation.
Yes. Good evening, everyone. Today I'll be briefing you on the topic of lattice-based cryptography and lattice reductions. So when we talk about lattice reductions, imagine it is a way to simplify features into more manageable forms. And at the heart of it all is the LLL algorithm, our guide to navigate this intricate landscape. So moving on to the next slide, I have my abstract. It talks about the LLL algorithm, which is invented by Hendrik Lenstra, Arjen Lenstra, and Lovaas Lenstra. It is named after its inventors, LLL algorithm. It is a powerful tool in lattice theory and computational number theory. This algorithm is used for lattice reductions, which involves transforming a given lattice basis into more shorter and more orthogonal basis. This algorithm iteratively modifies the basis vectors using Gram-Schmidt orthogonalization process and side reduction steps. These LLL reduced bases have vectors which are more shorter and nearly orthogonal. So let's see a step-by-step process for finding LLL reduced bases using LLL algorithm. So in my next slide, I have brief introduction on cryptography, which is broadly classified into symmetric cryptography and public key cryptography. So as previous speakers have already spoken about these cryptographics, I'm not getting into the detail. So coming to the public key cryptography, which mainly deals with lattice-based cryptography. This lattice-based cryptography have basis vectors which are not orthogonal. So we use this LLL algorithm to reduce these basis vectors to more shorter and more orthogonal as possible. So when it comes to reducing the lattices, we have two main problems, which is shortest vector problem and the closest vector problem. In cryptography, these two, SVP and CVP, are two important problems because they underline the security of many lattice cryptographic systems. Moving on to my next slide, which gives the introduction about lattices. So here we talk mainly about the definitions of lattices. These lattices are generated by a set of linearly independent basis vectors. These have more important applications in cryptography, coding theory, and optimization problems. This process involves finding a basis for a lattice, which I have already spoken, that is as short and as orthogonal as possible. So this LLL algorithm was first proposed in 1982 by Arjen Lenstra, Hendrik Lenstra, and Laszlo Lovász. Serves as one of the most efficient lattice reduction algorithm of today. So in my next slide, I'll be talking in detail of lattice reduction. So lattice reduction is a technique to find the basis for a lattice. So to reduce this lattice, we use one algorithm, which is the LLL algorithm. This LLL algorithm mainly works on two steps. The first step is Gram-Smith orthogonalization process, and the second one is size reduction process. So how to find the shortest vector? So as I told you about the shortest vector problem and the closest vector problem, I'll be mainly talking about how to find the shortest vector. So I'll be talking about the working procedure, which mainly involves 5 steps. First, given a lattice with the basis vectors, so converting these original to orthogonal vectors, we use this process of Gram-Smith orthogonalization process. So given any vectors, we can use this process to convert vectors into more orthogonal vectors. After the vectors are converted to orthogonal vectors, we check the Lovász condition. If the Lovász condition is not satisfied, then we swap the vectors accordingly and repeat the process. So if we first start with Gram-Smith and then the Lovász condition, and then which talks about size reduction. If this is not worked, then we swap the vectors and come back again to Gram-Smith. So this process goes on and on if the Lovász condition is not satisfied. But once if the Lovász condition is satisfied, then the resultant vectors are the LLL reduced vectors. Then after the vectors are reduced, we name those as LLL reduced vectors. And among the reduced vectors, we find the length of each of the vector. So the vector which is having the minimum length is known as the shortest vector. So moving my next slide, here I'm presenting you with an smallest example as possible. Here I have taken 2 basis vectors in a 2-dimensional space. So given the original basis V1 and V2, we first using the Gram-Smith orthogonalization process and converting U1, U2 to V1, V2. After the used vectors, yeah, just a minute. Yes. So here we are using the example. So this is just a 2 basis vector problem. So if the Lovász condition is satisfied, then we move on to checking the orthogonality. To check checking the orthogonality of any 2 vectors, we just use the inner product. So after we find out, then we use the shortest vector, then we find out the length. So whichever has the shortest vector, that is known as the shortest vector. So these are the limitations, as you can see on my scale, on my presentation. With this, I conclude, and I thank all the organizers for this wonderful opportunity. Thank you all.
Thank you, Anila, for completing within 5 minutes. Thank you. Next, Nandini. Nandini.
Yes, ma'am. Yes, ma'am. I'm there.
Are you ready?
Yes.
And Nandini is going to present her paper on a study on NTRU public key crypto system. Start your presentation. Share your screen.
I think you are able to see the screen now. Hello? Hello?
Yeah, Anila?
Nandini, are you able to see the screen, ma'am?
Yeah. It's perfect. Let's start your presentation.
Good evening, everyone. First of all, I would like to thank everybody for giving this opportunity. So myself Nandini, I'm from Sri Sathya Sai University for Human Excellence. My topic is study on entry public key crypto system. So in this presentation, I'll be discussing about basic concepts of entry crypto system and the concepts like key creation, encryption, decryption, and other how to choose the other parameters. So N2 means nth degree truncated polynomial ring. In this cryptography, we'll be using polynomials. Mostly polynomials will be used. This was invented or introduced by Hofstein, Pfeiffer, and Silverman in early 1996. So this is a public key crypto system where we use two different keys for encryption and decryption. And it is also probabilistic crypto system, which gives us multiple opportunity create cipher text for the same message. And it is extremely faster than RSA. So entry is very fast because we use truncated polynomials. The time consuming part in this encryption or decryption is polynomial multiplication, which is the dot product of two vectors. If you consider polynomial of length n, then it requires n square multiplication. So both encryption and decryption takes big O of n square steps, where each step is extremely faster. That's where it is faster than RSA. And it is a lattice-based quantum resistant cryptography. N2 is a quantum resistant cryptography. It is not easy to break this script because it is a lattice-based cryptography. In order to break it, it's very necessary to find the shortest vector. In the previous presentation, we saw that if they take only two bases, it is very big process to find the shortest vector using LLL algorithm. So if we take larger dimension, it is very difficult. That's why it is quantum resistant cryptography. So now let us see the algorithm of the N2 cryptography. There are main four parts: public parameter creation, key creation, encryption, and decryption. So these are the parameters we choose. And key creation, we choose two polynomials. First, we'll choose f, which is in the 2 of d plus 1 comma d, which is invertible in RQ and RP, where RQ is a polynomial where coefficients belongs to ZP and having a degree of less than n minus 1. That means it is coefficiented by x power n minus 1. And we will compute inverses for f in RP and RQ. And we have to choose another polynomial g which belongs to 2 of d comma d. And we have to compute the public key h using fq star g and fq. So when we compute, we choose the message and another random polynomial r in 2 of d comma d. And then we have to compute we have to convert plain text into ciphertext using a public key. So decryption will be followed like this. So we'll be computing f star e under mod q. And when we center lift f star e, we get a, and computing fp star a, we'll get the message. So how does this decryption work? So when pg star r plus f star m is exactly equal to a, then only we are able to get the message. So why does it work? Because if you consider pg star r plus f star m, so largest possible coefficients of convolution product g star e is 2d. If we consider largest possible coefficients of convolution product of f star m is 2d plus 1 p by 2. So if you put in the equation 1, we get half of 6d plus 1 into p, which is the most essential condition for the decryptions to occur. So whenever we f star e is computed, when we center lift, it gives exact value of a is equal to pg star r plus f star m. If we consider this q is greater than 6d plus 1 p condition. So same thing, whatever we discuss entry algorithm, I have given an example by taking these parameters. So these are the key creation and encryption, decryption. So that's all. Here, when we are computing A, we are getting this polynomial. So exactly when we compute pg star r plus f star m, we are getting same exact value. That's how encryption is working. So when, as I told before, whenever we use this condition, q is greater than 6d plus 1 into p, decryption never fails. And if the key creation and the operation and the key size is better than it is efficient than RSA key, because in RSA we use very large number of primes. Here, truncated polynomials we are using. That's why it is efficient. And as I earlier mentioned, it is post-quantum security. Its security relies on the difficulty of finding the shortest vector problem. As we know, in coming days, future, so we are expecting quantum computers. So quantum resistant crypto system is very necessary. That's why in the research field also the scope for the central cryptography is more. So these are the references which I used. Thank you for giving this opportunity.
Thank you, Nandini, for your nice presentation. Next presenter is G. Srinivas Garu. He is available for offline presentation.
అక్కడ పవర్లెస్
My pranams to our Guru Sri KPR Shastri Garu, dear distinguished guests, both online and offline, and esteemed faculty members of Andhra University and students of Department of Mathematics. It is a privilege to participate in the international conference on pure applied and engineering mathematical sciences 2024. As the time is running, I would like to confine myself to only 10 minutes talk. Today, 5 minutes. So I divided my paper presentation idea into three parts. First one is introduction. Second, analytical definition supported by its geometric significance, and finally the concluding part. First of all, what we mean by golden ratio sightings. In a literary context, refers to instances where the golden ratio, a mathematical proportion represented by the value approximately equal to 1.618, is observed or utilized in various contexts such as art, architecture, nature, and design. It is often associated with aesthetically pleasing proportions and harmonious compositions. Now coming to the introductory part, before going to define golden ratio, how it evolved from the normal concept of ratio and proportion. The ratio of two abstract quantities A and B is to compare A versus B, which is the quotient of A and B. When two equal ratios are taken, the equality of those two equal ratios is called a proportion. Now, golden ratio is defined geometrically as the ratio of the lengths of two line segments that allows us to make equality of two ratios. That is, the longer segment, if L denote the longer segment length and S denote the shorter segment length, then the ratio of L and S is given by L by S equal to L plus S by L. So analytically, how we prove? L by S equal to L plus S by L implies L by S equal to 1 plus S by L, taking X equal to L by S. We get a quadratic equation X plus 1 by X. By solving the roots of By solving the equation, the roots of the quadratic equation x plus 1 by x are found to be root 5 minus 1 by 2 and root 5 plus 1 by 2. Root 5 plus 1 by 2 is denoted by 5 and root 5 minus 1 by 2 is minus 1 by 5. So when you are going to claim that 5 and 1 by 5 are roots of that, we have to substitute them in the equation and check whether they satisfy or not. So obviously we can verify that 5 and 1 by 5 satisfies the equation x square plus x minus 1 equal to 0. See, the beauty in these two roots is the product and the difference of these two roots is 1. Geometrically, this ratio is supported by constructing a rectangle with the help of a square. Let us take one step further to create a rectangle whose sides are in the golden ratio. To do that, we begin with a unit square ABCD with midpoint capital M of side AB and then draw a circular arc MC cutting the extension of side AB at point E. We now can claim that the line segment AE is partitioned into the golden ratio at point B. This should be substantiated from the figure given. To verify this claim, let us consider AB by BE. So AB by BE, so to prove that from the right angle triangle MBC, where MB is half, BC is 1, using Pythagoras theorem, MC length is root 5 by 2.
Srinivas Garu, please conclude.
So, geometrically, the proof is obvious. Now, coming to the conclusion part, for centuries, artists and architects have identified what they believe to be the most perfectly shaped rectangle. This ideal golden rectangle has also proved to be the most pleasing to the eye. The desirability of this rectangle has been borne out by numerous physical experiments, psychological experiments. For example, Fechner, a German experimental psychologist inspired by Adolf Ising's book, Der Golden Schnitt, began a serious inquiry to see if the golden rectangle had a special psychological aesthetic appeal. His findings were published in 1876. Fechner made thousands of measurements of commonly seen rectangles such as playing cards, writing pads, books, windows, and so on. He found that most had a ratio of length to width what was close to 5. He also tested people's performance and found most people preferred the shape of the golden rectangle. Thank you one and all for giving me this opportunity.
Thank you, Srinivas Garu, for your presentation on golden ratio.
Clear.
Thank you, everyone. First,
Yes. So with this, we are done with the paper presentations. Before moving to the next item, I thank Professor Vinuta Madam for chairing the paper presentation session. And, honor you for that. Thank you very much. In few minutes, we will start our valedictory function.
సెంటర్ పెట్టేసి సెంటర్ ఫేస్
స్టేజే కదా సరిగ్గా ఉందా సరిగ్గా
Now we start the program with a prayer by Bhagyalakshmi. गणनायकाय गणदेवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि गानचतुराय गानप्राणाय गानान्तरात्मने गानोत्सुकाय गानमत्ताय गानोत्सुकमनसे गुरुपूजिताय गुरुदेवताय गुरुकुलस्वामिने गुरुविक्रमाय गुह्यप्रवराय गुरवे गुणगुरवे गुरुदैत्यकलक्षेत्रे गुरुधर्मसदायाध्याय गुरुपुत्र परित्रात्रे गुरुपाखण्डकण्डकाय गीतसाराय गीततत्त्वाय गीतगोत्राय धीमहि गूढगुल्फाय गन्धमत्ताय गोक्षयप्रदाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि Respected chief guest of today's function, Professor G.V. Ravindranath Babu Garu. Thank you, sir, for accepting to be our chief guest within a short notice. And respected guest of honor, Professor P. Avadhani Garu. I thank you too, sir. And the organizing secretary, Professor C.H. Srinivasarao Garu, Chairman UASMS, Professor C.H. Srinivasarao Garu, the organizing secretary. And then Chairman UASMS, Professor K.P.R. Shastri Garu, President UASMS, Professor K.K.M. Sharma Garu, Professor N.V.S. Murthy Garu, Professor P.D.N. Srinivas Garu, Professor Nanaji Rao Garu, Professor N. Ramakrishna Garu, Professor S. Ravikumar Garu, Professor K. Venkateswarlu Garu, delegates and participants of the conference, welcome you all to the valedictory function of this conference. Very happy to reach this stage of celebrating valedictory of the conference with a success note. In general, the purpose of holding a conference is to provide a platform to share the views on some topic or a theme. This two-day international conference, ICPAEMS 2024, International Conference on Pure Applied Engineering Mathematical Sciences, has really brought together many people working in various areas to share their knowledge here on this platform. Hope this interconnectivity encourages and helps the young researchers to gather all the ideas and move forward to generate more and more ideas. Now we have reached the end of two-day international conference. I thank all the delegates and participants for cooperating in all aspects, and I request you all to forgive us in case of any lapses. Now I request our guest of honor, Professor Avadhani Garu, to address the gathering in this contest.
Well, good evening, all of you. I am really honored to be on stage opposite to my Guru Garu, Professor KPS Shastri garu. ఆయనకి మేము చదువుకునేటప్పుడు మేము అనుకునేవాళ్ళం ఆయన్ని దేవుడు అని పేరు మేము పెట్టుకున్నాం. సచ్ ఎ నైస్ మ్యాన్. And I am here in the university because of him. Proud to say that he is my teacher. And also I am proud to say that he is my student who was Registrar once. I mean, Registrar in charge of Andhra University for some time. And of course, galaxy of experts, galaxy of intellectuals, youngsters, the bright mathematicians of tomorrow. And people say IT and India's talent. You're all. Coming days, I'm sure, after seeing the presentations, I was thinking, well, what best can happen better than this? Incidentally, when UAMS, I am from Visakhapatnam actually. My father, grandfather, everybody from Vijayanagar. We are all Uttarandraites. So it's good. It's true. It's good that somebody like my Guruji is trying his all efforts to bring in mathematical thinking, mathematical culture, mathematical activities in Uttarandhra. From all over the world, obviously international it is. So it has come all the way. After listening to a few of the things, I just wanted to share a few of my ideas actually. So I thought the mathematicians do a lot of things, as that girl, that lady, first year MSc student, who is at Nakka, what is that? Basari. As he rightly said, there are many applications, but then we are not getting the credit of it. Just to tell you a simple example. There is a conference like this. There is a conference in US lo. ఒక ఆయన మ్యాథమెటిక్స్ కాన్ఫరెన్స్, ఒక ఆయన ఏం చేశాడు, ఆయన ఫ్లైట్ మిస్ అయింది. ఒక హోటల్లో జరుగుతుంది అనమాట. ఫ్లైట్ మిస్ అయిపోతే ఆ ఫ్లైట్ ఆ కంపెనీ వాళ్ళు ఏం చేశారంటే, బాబు రేపు మార్నింగ్ దానికి ఫ్లైట్ లేదు కాబట్టి ఈ హోటల్లో నేను పెడుతున్నామని వాళ్ళు హోటల్లో పెట్టారు. అది ఏం చేయాలి, మీ అందరిలాగే మ్యాథమెటిక్స్ లాగా మిగతా సినిమాలు చూడటమో లేకపోతే ఇలాంటి సరదాలు ఏం లేవు. మ్యాథమెటిక్స్ చేయడం, మ్యాథమెటిక్స్ వినడం, తినడం, కనడం అన్ని మ్యాథమెటిక్సే. అలాంటప్పుడు సరే ఇక్కడ మ్యాథమెటిక్స్ కాన్ఫరెన్స్ అవుతుంది కదా, ఏదో కూర్చుందాం ఏదో చూద్దాం వెళ్ళాడు అనమాట. ఇతను మ్యాథమెటిక్స్ కాదు యాక్చువల్, అలా అటువంటి అనమాట. వింటే అక్కడికి వెళ్ళాక ఏం జరిగింది, ఇలాగే చెప్తున్నారు అనమాట. ఒకడేమో ఒక ఆల్గరిథం, ఇంకో ప్రొసీజర్, ఇంకోటి చెప్తుంటే ఈయన అవన్నీ జాగ్రత్తగా విన్నాడు. జరిగింది చెప్తున్నాను అని విని వాళ్ళ దగ్గరికి వెళ్ళి నాకు ప్రొసీడింగ్స్ కాపీ ఇవ్వగలరా అని అడిగాడు. ఇచ్చాడు. ఇస్తే అందులో కూర్చొని కొన్ని ఆల్గరిథమ్స్ బండిల్ చేసి he brought out another algorithm called PGP, pretty good privacy. That is what being used now for the security of emails. To send an email from one place to another, so what do? It requires some security. That is encryption, decryption కావాలి. దానికి అవన్నీ అతను ఏం చేయలే, మ్యాథమెటిక్స్ వాళ్ళు చేసినవన్నీ కలిపాడు అంతే చేశాడు. But nobody knows about it. It is the mathematics people's contribution. They never claim anything. Unfortunately, the patent should have been for mathematics. They never claim. I just tell you another example. మీరందరూ ఏటీఎం కార్డు వాడుతుంటారు కదా, ఏటీఎం కార్డు. ఇమాజిన్ a situation where ఏటీఎం కార్డు పెడితే ఏమవుతుంది, ఏదో పిన్ను పాస్వర్డ్ అడుగుతుంది, తన డబ్బులు ఎలా వస్తాయి బయటికి? లోపల డబ్బులు ఉన్నాయి. ఉన్న తర్వాత మీరు 2800 కావాలన్నారండి. 2800 కావాలి. మీకు ఏ డబ్బులు రావాలి? అప్పుడు ఎన్ని వస్తాయి? 2000 రూపాయల నోట్ లేదు, ఉందనుకోండి. పోనీ ఉంటే ఎంత వస్తుంది? ఒక 2000, ఒక 5000, ఒక 200 నోటు, ఒక 100 నోటు రావచ్చు. లేదా 4 500, లేదా 5 500, 4 500 రావచ్చు, 4 500, 800 రావచ్చు. ఎన్ని పాసిబిలిటీస్ ఉన్నాయి? హౌ డస్ ఇట్ ఆపరేట్? That is called a partition. Partitioning of a number. There is a recursive procedure for it. I think it is invented by Ramanujan. Ramanujan has given the partitioning. ఒకడు ఏం చేశాడు, పార్టీషన్ రామానుజన్ చేశాడు కదా అదంతాను. ఒకడు అమెరికాలో ఏంటంటే తిన్నం తాగడమే కదా, ఇంకేం లేదు. శుక్రవారం దాకా సంపాదించడం, శుక్రవారం అయిపోగానే మరి శనివారం అదే డబ్బులు ఉండవు. శుక్రవారం డబ్బులు ఉంటేనే ఉన్నట్టు. శుక్రవారం బ్యాంక్ ఆ బ్యాంక్ వెళ్ళిన టైం అయిపోయింది. బ్యాంక్ వాడు డబ్బులు ఇవ్వలేదు, నేను నో వే నవ్వు ఇట్స్ క్లోజ్. మరి ఏం చేయాలి, రేపు అంటే నువ్వు రేపు ఏం చేయాలంటే కావాలి ఫస్ట్ ఉంటే ఏం చేస్తావు ఇష్టం, మేము మాత్రం ఇవ్వలేమని చెప్తారు. దెన్ వాట్ హీ డిడ్, ఇంటికి వెళ్ళాడు. ఏం చేయాలి, ఇలాంటి కష్టం, ఈ ప్రాబ్లం వస్తే ఎలా సాల్వ్ చేయాలి, సీ ద థింకింగ్ ఆఫ్ ఇట్. అరే నాకు ప్రాబ్లం వచ్చేది రేపు ఇంకోటి వస్తుంది, ఇంకోటి ఎందుకు నాకు మళ్ళీ వచ్చే శుక్రవారం నాకు ఇదే ప్రాబ్లం వస్తుంది రావచ్చు. అప్పుడు ఏం చేయాలి అని ఆలోచించి కొంచెం మరి కసి ఉందన్నమాట. ఆకలి వేస్తుంది, తిండి లేదు, పట్టుకొని ఈ పార్టీషన్ ఆల్గరిథం చూడొచ్చు అని చెప్పి చూసి దాన్ని డిజైన్ చేసి చిన్న సర్క్యూట్ డిజైన్ చేసి పెట్టు. ఇట్ వర్క్ అవుట్. ఈ వెంట ద బ్యాక్ అండ్ సెడ్ యూజ్ దిస్, ట్రై దిస్, ఇట్ వర్క్ అవుట్. సో హూస్ క్రెడిట్ ఇట్ ఈస్? ద లాస్ట్ స్పీకర్ మన శ్రీనివాస్ చెప్తున్నాడు కదా, గోల్డెన్ రేషియో. గోల్డెన్ రేషియో ఏం తెలుస్తున్నా? గోల్డెన్ రేషియో అసలు కథ చెప్తాడు మేడం. ఓకే, సో ఏంటంటే ఒకడు ఏం చేశాడంటే ఒక చెవుల పిల్లి జత పెంచాడు. చెవుల పిల్లి జత అంటే ఆడా మగ ఒకటి పెంచాడు అంతే. చెవుల పిల్లి అంటే ర్యాబిట్ ఇంగ్లీష్ లో మాట్లాడాలా, తెలుగులో మాట్లాడాలా, దాని నుంచి వైదిక భావంలో ఉన్నాను, తెలుగులో మాట్లాడితే బాగుంటుంది కదా అనిపిస్తుంది. ఎందుకంటే మేము మ్యాథమెటిక్స్ చదివేటప్పుడు మాకు ఇంగ్లీషు రాదు, తెలుగు రాదు. మ్యాథమెటిక్స్ లో కొంచెం మా గురువు గారు కొంచెం మ్యాథమెటిక్స్ చదివింది, కానీ ఇలా మాట్లాడడం అంటే కష్టమే. ఇప్పుడు అందరినీ చూస్తాం, తరతలు ఆడించేస్తారు. ఆ పిల్లలు వచ్చేసి మాకు భయం వేసేది స్టేజ్ రావడానికి. ఇట్ ఇస్ ఏ లాట్ ఆఫ్ డెవలప్మెంట్ మ్యాథమెటిక్స్ డిపార్ట్మెంట్ లో లైఫ్. సో పాయింట్ ఏంటంటే ఒక పేరు మగ ఆడ పెంచాడు. చెవుల పిల్లి కూడా లక్షణం ఏంటంటే పిల్లల్ని ఎక్కువ పెట్టేస్తుంది అనమాట. ఎంత ఎక్కువ పెట్టేస్తుందంటే మీకు ఒక ఇన్స్టెన్స్ చెప్తాను. ఒకడు ఏం చేశాడు, చెవుల పిల్లలు బాగున్నాయని చెప్పి అమెరికా నుంచి ఓ 2-3 పేర్స్ని ఆస్ట్రేలియా పంపించాడు ఎవరికో ఫ్రెండ్కి. వాటి ముద్దుగా ఉన్నాయని చెప్పి వాడు ఇంట్లో పెంచుకున్నాడు. పెంచుకుంటే పిల్లలు పెట్టేసి ఆఖరికి ఆస్ట్రేలియన్ గవర్నమెంట్ కొంతకాలం ఒక 5 ఏళ్ళు పోయిన తర్వాత 10 ఏళ్ళు పోయిన తర్వాత వాటి బాధ భరించలేక మిలిటరీని దించి వాడు షూట్ చేయించింది, తప్పించారు. అంతకాలం పెట్టేస్తాయి. ఆ కథ పక్కన పెట్టండి. ఇంతకీ చెవుల పిల్లలు ఒక ఆడ మగ కదా, అతను ఏం చెప్పాడంటే ప్రతి 2 నెలలకి ఒకసారి పిల్లలు పెడతాయి. అస్యూమింగ్ దట్ ఈచ్ pair of male and female give birth to only one pair every 2 months. Mathematics kada. So one pair we started F1 or F0, 0th month lo only one pair. First month lo ఎన్ని ఉంటాయి? 1 pair. 2 ఉండవు, 2 నెలలకు పెడుతుంది మళ్ళీ. సెకండ్ మంత్ లో ఎనదర్ పేర్ వస్తుంది, 2 pairs. థర్డ్ మంత్ లో అలాగే లెక్క వేసుకుంటూ వెళ్ళాడు. అంటే 10th మంత్ కావాలనుకోండి, 10th మంత్ లో ఎన్ని ఉంటాయి? 9th మంత్. అస్యూమింగ్ దట్ నథింగ్ డైస్, అన్ని బతికే ఉంటాయి అనుకున్నాం కూడా, అది కూడా ఒక ఎగ్జాంప్షన్ పెట్టుకున్నాం. 10th మంత్ లో కావాలనుకోండి, 9th మంత్ లో ఎన్ని ఉంటాయో అన్ని ఉంటాయి. 10th మంత్ లోకి 8th మంత్ లో ఎన్ని ఉన్నాయో అన్ని పేర్లు యాడ్ అవుతాయి ఎక్స్ట్రా. సో F10 is equal to F9 plus F8 or Fn is equal to Fn minus 1 plus Fn minus 2 with F0 is equal to 1 and F1 is equal to 1. That is the recursive equation. You can solve it. The ratio of Fn by Fn minus 1 is the golden ratio. అక్కడతో అయిపోలేదు కదా. The golden ratio, that is the golden ratio though. సో గోల్డెన్ రేషియో అక్కడతో అయిపోతే అది వేరు. ఆ గోల్డెన్ రేషియో ఏంటంటే, గోల్డెన్ ఎందుకన్నారు, గోల్డ్ ఎందుకైంది? ఏయు అంటే ఏంటి? ఆంధ్ర యూనివర్సిటీయా? ఏయు అంటే కెమిస్ట్రీలో గోల్డ్. ఆంధ్ర యూనివర్సిటీ ఇస్ గోల్డ్. ఓకే, సో గోల్డెన్ రేషియో ఏంటంటే, ఆ గోల్డెన్ రేషియో యొక్క ఆ గోల్డెన్ మాటకు అర్థం ఏమిటంటే, తర్వాత చూస్తే రేషియో ఎనీ నేచురల్ ఫినామినన్ హ్యాస్ దట్ రేషియో. ఫర్ ఎగ్జాంపుల్ మన చేతి వేలు తీసుకున్నాం అనుకోండి, ఈ పెద్ద వేలు నుంచి
ఈ మధ్య వేలు నుంచి ఈ దేనికి రేషియో ఇస్ గోల్డెన్ రేషియో. మనకి ఒక పువ్వు తీసుకున్నాం అనుకోండి, మందారం పువ్వు కానీ లేకపోతే బంతి పువ్వు, ఫర్ ఎగ్జాంపుల్ బంతి పువ్వు తీసుకుంటే అందులో ఆకులన్నీ ద ప్యాటర్న్ ఫాలో సమ్ ఈజ్ రిలేటెడ్ టు గోల్డెన్ రేషియో. బెండకాయ కట్ చేసాం అనుకోండి, సన్ఫ్లవర్ ఫర్ ఎగ్జాంపుల్, నేను నెట్ లో కొట్టచ్చు, మీకు తెలుస్తుంది. ఆయన గోల్డెన్ రెక్టాంగిల్ లాగా చెప్పుకున్నాడు, కానీ సన్ఫ్లవర్ బెండకాయ కట్ చేశారు అనుకోండి, అక్కడ ఉండే గళ్ళు ఉంటాయి కదా, గళ్ళు, దే హ్యావ్ సమ్ రిలేషన్షిప్ విత్ గోల్డెన్ రేషియో. అండ్ తేనె పట్టు with golden ratio. So that is what golden ratio is. The contribution is by mathematicians. But unfortunately, nobody knows about it. Nobody thinks about it. ఇంకో జనరేషన్ చెప్తాను మీకు. 1947లో ఏమిటి వచ్చింది మనకి? ఇండిపెండెన్స్ వచ్చిందని అనుకుందాం. ఓకే, 1947 ఇండిపెండెన్స్ వచ్చిందని అనుకుంటే అప్పుడు ఏంటంటే పాకిస్తాన్ ఇండియా విడిపోయాయి కదా. పాకిస్తాన్ నుంచి చాలా మంది వచ్చారు ఇండియాకి, గాంధీ సీకులు అంటే వలసనండి లేకపోతే రెఫ్యూజీస్ అనండి వడెవర్. వాళ్ళందరికీ భోజనం పెట్టాల్సిన బాధ్యత మనమే పడింది. మామూలుగా ఏం చేశారు, భోజనాలు ఎక్కడో టెంటర్లు వేసి భోజనాలు పెడుతున్నారు, అంతా చేస్తారు. ఎక్కడైనా సరే మన వాళ్ళ చేతివాట ఉంటుంది కదా. కరప్షన్ ఈజ్ ద ఓల్డెస్ట్ ప్రొఫెషన్. తినడమే డబ్బులు. ఈ ఐసీఎస్ ఆఫీసర్లు వాళ్ళందరూ తినేస్తుండేవారు అనమాట. తినేస్తున్నారని తెలుసు, కానీ ఎలా పట్టుకోవడం? మళ్ళీ రెడ్ హ్యాండ్ గా పట్టుకోవాలి. తింటుంటారు ప్రతి వాడును, కానీ వాడిని పట్టుకోవాల్సిన ఉండాలి. అప్పుడు ఎవరో చెప్పాడు అనమాట, నెహ్రూ గారి దగ్గర, సార్ తినేస్తున్నారండి వాళ్ళు, విపరీతంగా ఖర్చు రాసేస్తారు దొంగ లెక్కలు, ఎలాగండి అని అంటే, అప్పుడు సర్దార్ పటేల్, నెహ్రూ గారు ఏం చదువుకోలేదు కదా, సర్దార్ పటేల్ ఏమన్నాడంటే, ఓకే వి గివ్ ఇట్ టు మ్యాథమెటిషియన్స్, దే విల్ సాల్వ్ ఇట్ అన్నాడు. నలుగురు మ్యాథమెటిషియన్ పిలిచారు. పేర్లు ఎందుకు రండి, ఇప్పుడు నేను నెట్లో ఉంటుంది, ఇదంతా నెట్లో ఉంది, నేను నా సొంతమే కాదు, అండ్ ఇట్ ఈస్ ఫ్యాక్ట్ ఆల్సో. సో ఏం చేశారంటే మ్యాథమెటిక్స్ నెహ్రూ గారు, వీళ్ళేం చేస్తారండి సుతముఖ ఇది పట్టుకుని ఇలా చేస్తారని, సుతముఖ మీద బోర్డు మీద రాస్తారు, ఏదో చేసుకుంటారు, వాళ్ళు ఏం సాల్వ్ చేస్తారండి, లేదు లెట్ us try. సరే వీళ్ళేమో 4 కాగితాలు 2 పెన్నులు పడేయండి మాకు అన్నారు. అంతే. వాళ్ళు ఏం చేశారు, డేటా తీసుకున్నారు. తీసుకొని ఏం చేశారంటే, ఒక మనిషికి ఇన్ని కేజీలు బియ్యం అయితే ఎంతమంది మనుషులు, దానికి ఎంత కూర అవుతుంది, ఎంత ఉప్పు అవుతుంది, అంటే 100 మందికి వండాలంటే ఎన్ని కేజీలు రైస్ కావాలి, ఉప్పు ఎంత కావాలి అని రేషియోలు పట్టుకొచ్చేసారు. చూడండి, రేషియో పట్టుకొచ్చిన తర్వాత వీళ్ళు ఏం చేశారు, ఎక్కడ మిగులుతుంది డబ్బులు, బియ్యం బస్తాల దగ్గర డబ్బులు మిగులుతాయి కానీ ఉప్పు బస్తాల దగ్గర డబ్బులు మిగలవు కదా, ఉప్పు చాలా చవక. వీళ్ళు ఏం చేశారు, 100 బియ్యం బస్తాలు కానీ 1/2 కేజీ ఉప్పు అని రాశారు అనుకోండి, ఈక్వేషన్ ఇస్ రాంగ్. ఎక్కడ తేడా వస్తుంది, బియ్యం బస్తాల దగ్గర తేడా వస్తుంది. అన్ని ఈక్వేషన్ వేసేసి, సార్ ఈ డిపార్ట్మెంట్ మీరు సర్విలెన్స్ చేసి దొరికిపోతారు అని చెప్పి చూస్తే పట్టుకుని దొరికిపోయారు. సర్ప్రైజ్డ్. సో ద రేషియోస్ ఇట్ హెస్ కమ్ అవుట్. సో అండ్ దెన్ Nehru then have identified the power of knowledge, the power of mathematics, the power of intellectuals, the power of professors, and then started IITs. That's how it started IITs. ఇలాంటివి ఎన్నో ఇన్స్టెన్స్ ఉన్నాయి. ఎన్ని ఇన్స్టెన్స్, ఫర్ ఎగ్జాంపుల్ రిమెంబర్, ఇప్పుడు మనం అనుకుంటున్నాం ఇంకోటి, ఇప్పుడు పెన్ డ్రైవ్ పెట్టి వేశారు కదా, మీరు ఏదో సినిమాలు వేశారు, ఎంతసేపు సినిమాలు కాదు, అదే ప్రెజెంటేషన్. పెన్ డ్రైవ్ పెట్టారు కదా కొంతమంది, పెట్టారా? అది ఎవరు కనిపెట్టారు? ఆ పెన్ డ్రైవ్ కనిపెట్టిన ఎవరు తెలుసా? అజయ్ భట్. ఏదో చెప్తే అర్థమవుతుంది, ఇండియన్. సో ఇలాగా బూలియన్ ఆల్జీబ్రా, మేము చిన్నప్పుడు ఏదో చదువుకున్నాం బూలియన్ ఆల్జీబ్రా అని. ఏమిటో ఈ బూలియన్ ఆల్జీబ్రా అని, 2 వాల్యూడ్ లాజిక్ 0, 1 అని. అండ్ రిమెంబర్ దట్ బూలియన్ ఆల్జీబ్రా ఇస్ బేసిస్ ఫర్ ఎవ్రీథింగ్ ఇన్ కంప్యూటర్స్, వెదర్ ఇట్ ఇస్ ఆర్టిఫిషియల్ ఇంటెలిజెన్స్ ఆర్ వెదర్ న్యాచురల్ ఇంటెలిజెన్స్ ఆర్ robotics, what she said, and anything, any digital, for example, digital movies, this, that, 0 and 1, ultimately, that is Boolean algebra. But మనం చదువుకుంటాం కానీ we never use it. సింపుల్ థింగ్స్ అనమాట. ఇప్పుడు ఫర్ ఎగ్జాంపుల్ హ్యూమన్ బాడీ, ఇప్పుడు dy/d ఆయన అడిగాడు పాపం, అంటే ఐ వాస్ థింకింగ్, ఐ మీన్ వాట్ షుడ్ బి దట్, సి dy/dt, d²/dt², మధ్యలో d⁴/2 ఉంటే పరిస్థితి ఏంటని అడిగాడు మన వైస్ ఛాన్సలర్ గారు, ఫార్మర్ వైస్ ఛాన్సలర్. ఐ వాస్ థింకింగ్ వాట్ కుడ్ ఇట్ బి, అంటే ఒక డెరివేటివ్ ప్లస్ నెక్స్ట్ కంటిన్యూటీ ఏదో. మరి నేను మ్యాథమెటిక్స్ వదిలేసి మ్యాథమెటిక్స్ చదువే వదిలేసి ఇప్పుడు 10 ఏళ్ళు అయిపోయింది, మ్యాథమెటిక్స్ వదిలేసి ఇంకా చాలా కాలం అయిపోయింది. వాట్ కుడ్ ఇట్ బి? That is inquisitiveness. That is what is required. So incidentally, మనకి చాలా అంటే యాక్చువల్గా ఏంటంటే ఒకడు ఏం చేశాడు ఇలాగ ఇంక్విజిటివ్నెస్ తోను మనం ఇన్ని పనులు చేస్తున్నాం కదా, జనరల్లీ ఏం చేస్తాం, ఆప్టిమైజ్ చేస్తాం, ఆప్టిమైజేషన్ అన్నమాట. మన నేచర్ ఏం చేస్తుంది, నేచర్ అని చెప్పి అనుకొని నేచర్ డస్ ఫర్ ఎగ్జాంపుల్ చీమలు ఉన్నాయి, చీమలు దే ఫాలో ఏ ప్యాటర్న్, వాటి అన్ని లైన్లో వెళ్ళడం అదంతా చూసుకుంటాయి. అలాగే తేనె పట్టు వాడికి కావాల్సిన ఎంత బాగా కట్టుకుంటాయి ఇల్లు, ఆలోచిస్తే అర్థమవుతున్నాడు. మనం కట్టుకోలేకపోతున్నామని ఒకడు ఆలోచించాడు. ఆలోచించి నేచర్లో ఏమేమి ఆపరేషన్స్ ఉన్నాయి, ఏమిటి చేస్తుంది, 3. ఒకటి క్రాస్ ఓవర్, అంటే మగ ఆడ ఉంటే పిల్లలు పుడతారు. నెక్స్ట్ మ్యూటేషన్, ఇదే 3 ఆపరేషన్లు. వాడి జెనెటిక్ ఆల్గరిథమ్స్ అని పట్టుకొచ్చాడు. Now which is there. Now what I mean to say is, see, you have come up to master ఇందాక అన్నారు, అమ్మాయిని పిలిచి అన్నారు, నేను విన్నాను. ఏంటంటే నువ్వు చెప్పే బాగుంది, దాన్ని అప్లై చేయి, డోంట్ బి ఎ పొలిటీషియన్, బి ఎ మ్యాథమెటిషియన్ అన్నారు ఆయన. ఇట్స్ ట్రూ. సో బేసిక్ ఏంటంటే మనం అక్కడి నుంచి ఎందుకు వెళ్ళలేపుతాం ముందుకి. ఇప్పుడు ఇందాక ఆయన ఎవరో ఇథియోపియా ఎవరో మ్యాథమెటికా వాడానన్నాడు. ఇథియోపియా అతను కాదు, ఇంకెవరో మ్యాథమెటికా అనేది ఇట్స్ సాఫ్ట్వేర్ టూల్ which can solve differential equations of any order. నేను వాడాను. సో అలాంటివన్నీ ఉన్నాయి. మనం ఇంకా డిఫరెన్షియల్ ఈక్వేషన్ సాల్వ్ చేస్తామంటే కాదు. సో యూ హ్యావ్ టు థింక్ అబౌట్ దాట్. ఇప్పుడు మన హ్యూమన్ బాడీ ఉంది, హ్యూమన్ బాడీ ఈజ్ ఎ మెషిన్, obviously it's a machine, it's a computer, that's it, it's one that computes. కానీ ఒకటే డిఫరెన్స్, ఈ ఏదైనా మెషిన్ బాగు చేయాలనుకోండి, ఆ మెషిన్ ఏం చేయాలి, స్విచ్ ఆఫ్ చేసి అప్పుడు బాగు చేయాలి, అంతే కదా. ఈ మెషిన్ వర్కింగ్ కండిషన్ కూడా బాగు చేయాలి, అదే ప్రాబ్లం. దట్ ఈస్ ద బిగ్గెస్ట్ ఛాలెంజ్. బట్ ఇందులో ఫ్లో ఉంది, బ్లడ్ ఫ్లో ఉంది, ఇంకో ఫ్లో ఉంది, ఇంకా క్రోమోజోమ్స్, ఇందాక ఎవరో చెప్పారు క్రోమోజోమ్స్, 23 క్రోమోజోమ్స్ తెలుసా, 23 పేర్స్ మొత్తం. మనకి 23 పేర్స్ మనకి మొత్తం బాడీలో. ఆ జినోమ్ సీక్వెన్స్ అని అమ్మాయి ఎవరో చెప్పింది ఇందాక, ఎవరో మన అక్క అమ్మాయి వాసవేగా చెప్పినట్టు జినోమ్ సీక్వెన్స్ అంటే ఏంటి తెలిసిన, జినోమ్ కోడ్ అంటే దేర్ విల్ బి 4 న్యూక్లియోటైడ్స్, ATGC, దట్స్ ఆల్, 4 న్యూక్లియోటైడ్స్. వాడి పేర్లు 89 ఏదో ఉంటాయి, మనకి పేర్లు అక్కర్లే కదా, ఎక్స్ అనుకోనులాగా ATGC 4. ఈ 4కి ఇలాగా పెద్ద 3 బిలియన్ లెటర్ సీక్వెన్స్ ఉంటాయి. అంటే ATGC, GCAT అలా 3 బిలియన్ ఉంటాయి. It seems, it is not yet proved yet, but it seems every human being has a unique feature of that, a sequence. That could be your code. అంటే మనం ఫింగర్ ప్రింట్ వేస్తాం కదా, ఫింగర్ ప్రింట్ ఉండదు, ఆ కోడ్ ఫిక్స్డ్ అనమాట. దాని నుంచి ఏంటంటే వన్ కెన్ గెట్ ఆల్ సార్ట్స్ ఆఫ్ థింగ్స్. ఫర్ ఎగ్జాంపుల్ గ్రూప్ 3 అప్లికేషన్ చెప్పుకోవచ్చు కదా అమ్మాయి, ఇట్స్ పాసిబుల్. సో లాంగెస్ట్ సీక్వెన్స్ ఏంటి, లాంగెస్ట్ కామన్ సీక్వెన్స్ ఏంటి, హెరిడిటరీ ఏంటి, ఇవన్నీ వస్తాయి. గ్రూప్ 3 అంటే గుర్తొచ్చింది, యాక్చువల్లీ ట్రాన్స్పోర్టేషన్ ప్రాబ్లం విశాఖపట్నంలో పెద్ద ప్రాబ్లం అది. రియల్లీ ఇఫ్ యు సీ, లెఫ్ట్కి తిరగడం, రైట్కి తిరగడం, స్ట్రెయిట్గా వెళ్ళడం, యూటర్న్ తిరగడం, 4. LRUS, ఈ 4 కలిపి డ్రైవింగ్ అనేది ఆపరేషన్ పెట్టుకుంటే దట్ బికమ్స్ గ్రూప్, దట్స్ ఎ గ్రూప్. And applications. Incidentally, transportation problem, traveling salesman's problem, ఇలాంటి చాలా ఉన్నాయి. ఇప్పుడు ఏంటంటే ఒక నెట్వర్క్ ఉందనుకోండి, మన నెట్వర్క్ అంటే ఇది ట్రావెలింగ్ సేల్స్మన్స్ ప్రాబ్లం. మనం జనరల్గా మీరు వినే ఉంటారు, ఒక సేల్స్ మన్ ఉన్నాడు, వాడు ఒక 5 సిటీలు తిరగాలనుకోండి, విశాఖపట్నం, విజయనగరం, ఏదో కాకినాడ, రాజమండ్రి అండ్ ఇంకో సిటీ విజయవాడ అందాం. అతను ప్రతి వారం అదే ప్రతి నెల 5 సీట్లు వెళ్ళి రావాలి. ఇక్కడి నుంచి ఇక్కడికి వెళ్ళిన సిటీ కాస్ట్ తెలుసు మనకి, ఒక సిటీకి ఇక్కడి నుంచి విశాఖపట్నం నుంచి విజయనగరం తెలుసు, విజయనగరం నుంచి ఇంకో తెలుసు. అతను వాట్ ఈస్ ద షార్టెస్ట్ పాత్, షార్టెస్ట్ వే, ఆర్ విత్ మినిమం కాస్ట్, షార్టెస్ట్ అంటే మినిమం కాస్ట్, విత్ మినిమం కాస్ట్ హౌ టు కవర్ ఆల్ ది, హీ హస్ టు కవర్ ఆల్ ది థింగ్స్, ఎలా కవర్ చేయాలి, అది ట్రావెలింగ్ సేల్స్మన్స్ ప్రాబ్లం. ఇఫ్ దర్ ఆర్ n cities and the cost of any 2 cities, the cost of travel between any 2 cities is known, then what is the shortest or with minimum cost? How can you cover all the entities and come back to the original? For example, విజయనగరం వెళ్ళి విశాఖపట్నం వచ్చేసి మళ్ళీ ఏదో కాకినాడ వెళ్ళి వచ్చేసి తర్వాత రాజమండ్రి వెళ్ళి వచ్చేస్తే బోర్డు ఖర్చు అయిపోతుంది. రాజమండ్రి వెళ్ళినప్పుడు కాకినాడ వెళ్ళి కాకినాడ రాజమండ్రి చూసుకుని విజయవాడ చూసుకుని వచ్చేస్తే తగ్గుతుంది. మనకు తెలిసిందే కదా. అలా అది ఎన్ పెరిగిపోతుంది అనుకోండి. ఎన్ ఫ్యాక్టర్ అంటే సొల్యూషన్స్ ఎంత తెలిసినా ఇట్స్ మచ్ కాంప్లెక్స్. అంటే పెరిగిపోతుంది అనమాట. 3 సిటీలు 4 సిటీలు 5 సిటీలు 6 సిటీలు ఇట్స్ ఆల్మోస్ట్ ఫ్యాక్టోరియల్ ఎన్ టైం పట్టేస్తుంది. సో ఎన్ పెరిగిపోతుంటే బాగా పెరిగిపోతుంది. దానికి మ్యాథమెటిషియనే ఒక ఆయన కర్మార్కర్ పేరున్నారా లేదా? కర్మార్కర్ అనే అతను ఒక ఆల్గరిథం కనిపెట్టాడు. దిస్ ప్రాబ్లమ్ ఈజ్ రిలేటెడ్ టు నెట్వర్క్స్. మనకి ఇప్పుడు వైఫైలు గీఫైలు వస్తున్నాయి కదా. ఇట్ ఇస్ అగైన్ సింపుల్ ట్రావెలింగ్ సేల్స్ ప్రాబ్లమ్ ఇట్ ఈస్. బట్ సొల్యూషన్ చాలా టైం పట్టేటటువంటి ఇక్కడ నెట్వర్క్ వైఫై ఎలా పనిచేస్తాయి? ఇందాక ఇలా తిరుగుతూ ఉంటుంది. చూసారా తిరిగింది ఇందాక? నెట్వర్క్ స్లో అయితే అలా తిరుగుతూ ఉంటుంది. ఆ తిరగడం ఎంతసేపు? అందుకని అంటే ఫాస్ట్ సొల్యూషన్స్ కావాలి. దానిపై ఇతను ఏం చేశాడంటే ఓ మంచి ఆల్గరిథం కనిపెట్టాడు. ఈజ్ దేర్ అండ్ పూణే నౌ కనిపెట్టి వెంటనే ఐబిఎం వాళ్ళు ఆయన తీసుకున్నారు విత్ లాట్ ఆఫ్ మనీ అండ్ సో ఆన్. ఐబిఎం ఇప్పటికి కూడా 25 ఏళ్ళు దాటిన తర్వాత ఆల్గరిథం బయటకి ఇవ్వచ్చు అనుకుంటారు, ఇంకా అవ్వలేదు అనుకుంటా. సో దట్ ఈస్ వాట్ ఈస్ మ్యాథమెటిషియన్ ప్రొఫెసర్ కర్మార్కర్ has come back to India. Now I think he stays in Pune. So what I'm trying to say is these are all the things which now I don't know why our department, I am proud to say that I belong to this department. My career started with this department. My life started with this department. I don't know why you have not applied for National Quantum Mission. నిన్న రాజశేఖర్ గారు కూడా చెప్పారు. నేషనల్ క్వాంటమ్ మిషన్ అంటే క్వాంటమ్ కంప్యూటింగ్ గురించి గవర్నమెంట్ ఆఫ్ ఇండియా 6,000 crores ఇస్తానని చెప్పింది. అందరినీ అప్లై చేయం. మరి ఆంధ్ర యూనివర్సిటీ అప్లికేషన్ వెళ్ళలేదు. ఏదో మీరు ఏం చేస్తారో చెప్పండి. ఎవరికి ఏమి రాదు. క్వాంటమ్ మిషన్ లో ఐఐటీలు చెప్పేస్తాక ఏం లేదు. ఇట్స్ న్యూ కాన్సెప్ట్, న్యూ థింగ్స్ కమింగ్ అప్. మీరు ఏదో ఒకటి ప్రపోజ్ చేస్తే ఉంటుంది. మనకేమి రాదు, మనకేమి ఫండింగ్ రాదు అనుకోవచ్చు. రాకర్లే. ఏమవుతుంది? మీ పేరు అక్కడ లేకపోతే నెక్స్ట్ మీరు ఉండరు అసలు. ఇప్పుడు మన ఆ లిస్ట్ లో మన పేరు ఎక్కడో ఉంటే ఓహో వీళ్ళు కూడా పెట్టారు ఇప్పుడు కాకపోతే నెక్స్ట్ ఇయర్ దగ్గర పిలుస్తారు. ఆ నెక్స్ట్ ఇయర్కే మన పనికి వస్తుంది. మన పేరే లేదు అక్కడ. అది ప్రాబ్లం. సో ఇప్పటికైనా ఐ డోంట్ నో వెదర్ టైమ్ ఇస్ దేర్ ఆర్ నాట్. డిపార్ట్మెంట్ ఆఫ్ మ్యాథమెటిక్స్ కెన్ థింక్ అబౌట్ ఇట్. దేర్ ఆర్ ఎన్ నెంబర్ ఆఫ్ ప్రాబ్లమ్స్ విచ్ కెన్ బి సాల్వ్డ్ with simple mathematics. I told you, this is in the quantum machine as well. Okay, and similarly ఇందాక చెప్పుకున్నాం కదా, ఇప్పుడు ఎంట్రపీ అని వినే ఉంటారు. ఎంట్రపీ అంటే ఏంటంటే మెజర్ ఆఫ్ డిజార్డర్లీనెస్, అంటే క్రమరాహిత్యాన్ని కొలవడం. అని కొలవడమే కదా మనం. క్రమరాహిత్యం అంటే ఒక ఈ పేపర్ తీసులో పడేసి అనుకోండి, ఇష్టం పడతాయి. మళ్ళీ తీసి మళ్ళీ పడేస్తే మళ్ళీ అలాగే పడవు, వేరువేరుగా పడతాయి. సో ఎంట్రపీ, ఆ ఎంట్రపీ నుంచి అంటే షానన్స్ థియరీ ఆఫ్ ఇన్ఫర్మేషన్ ఒకటి ఉంది. ఇవన్నీ కలుపుకొని ఓడేం చేశాడు, మ్యాథమెటిక్స్ ఓడేం చేశాడంటే కన్ఫ్యూజన్ అండ్ డిఫ్యూజన్ ఒక కాన్సెప్ట్ ఉంటుంది. కన్ఫ్యూజన్ చూసారా? కన్ఫ్యూజ్ చేయడం కూడా ఒక మ్యాథమెటిక్స్ పార్ట్. కన్ఫ్యూజ్ ఎలా చేయాలి, ఎందుకు కన్ఫ్యూజ్ చేయాలి? ఇప్పుడు ఓటీపీ, మీ ఓటీపీ వింటున్నారు కదా. ఓటీపీ అంటే 1 time పాస్వర్డ్. ఇప్పుడు మీరు ఏదో డేటా ఎన్క్రిప్ట్ చేసే డేటా బ్యాంక్ లో ఉంది, మీ యొక్క పాస్వర్డ్ అది కన్ఫ్యూజ్ చేయాలి. మీ పాస్వర్డ్ ఈజీగా మీరు పాస్వర్డ్ ప్రాబ్లం ఏంటంటే మీరు పాస్వర్డ్ పెట్టుకుంటే ప్రాబ్లం ఏంటి? మీకు గుర్తుండాలి. అందుకని మీ అమ్మాయి పేరో అబ్బాయి పేరో లేకపోతే మీ భార్య పేరో మరీ ఎక్కువ అభిమానుడు తండ్రి గారి పేరో తల్లి గారి పేరు పెట్టుకుంటారు. కానీ కొంచెం అటు ఇటు మార్చి, అంతే కదా. ఇది మనం గుర్తుండాలి కదా. అమ్మాయి పేరు అబ్బాయి పేరు గుర్తుంటాయి, మనకి గుర్తుంటారు కాబట్టి పెట్టుకుంటాం. అవి పెట్టుకుంటాం కాబట్టి అందరికీ తెలిసిందే, ఇది ఎవడో పట్టించుకుంటాడు అంతే. మీ అమ్మాయి పేరు ఏంటండి అదే మనం చెప్తాం గర్వంగా. లేదా ఆ అమ్మాయినే పిలిచారు. మా మనవరాలు నేను వెళ్తుంటే బీచ్లో పిలిచి నీ పేరేంటమ్మా అంటే ఖచ్చితంగా చెప్పింది. నేను మా మనవరాల పేరే పెట్టుకున్నానేమో, వాడు తెలిసిపోతుంది మన పాస్వర్డ్. సో అందుకని కన్ఫ్యూషన్ అనే కాన్సెప్ట్ పెట్టి దాన్ని పాస్వర్డ్ మనం టైప్ చేసినా అది అక్కడ అలా రాకుండా దానికి కొంచెం సాల్ట్ అని ఒక నెంబర్ యాడ్ చేసి, సాల్ట్ అంటే ఉప్పు కాదు, సాల్ట్ అనేది 12-bit నెంబర్ యాడ్ చేసి దాన్ని ఏదో చేసి అక్కడ చేస్తారు అన్నమాట, ఈజీగా రాకుండా. అయినా కానీ ప్రజలు బయట పెట్టుకుంటారు. వాళ్ళు దట్ బికమ్స్ ద టాలెంట్. దొంగోడు కూడా మంచి ఎఫిషియన్సీ ఉంటేనే దొంగతనం చేయగలుగుతాడు. ఏ ప్రొఫెషన్ అయినా సరే తెలివితేటలు లేకుండా జరగదు, కష్టపడకుండా డబ్బులు రావు. అది సో నిజమే, అది ఎవరైనా అంతే. అది అదే మొన్న గోదావరి ఎక్స్ప్రెస్ లో కూర్చుంటే ఎవడో వచ్చాడు ఒక ఆయన వచ్చాడు అనమాట. నా పక్కన ఎదుగుంటే ఒక ఆయన కూర్చున్నాడు. ఆయన దగ్గరికి వచ్చాడు. సార్ 100 రూపాయలు చేంజ్ ఉందా అని అడిగాడు. 100 రూపాయలు చేంజ్ ఉందా అంటే లేదన్నాడు. 100 రూపాయలు చేంజ్ లేదు. ఆయన 100 రూపాయలు లెక్కెట్టుకుంటున్నాడు. 10 ఉన్నాయి, లెక్కెట్టుకుంటున్నాడు. సార్ 100 రూపాయలు చేంజ్ ఇవ్వండి సార్ అన్నాడు. ఎందుకంటే మా పిల్లలు అదుగోటండి, ఎవడో పిల్లలు చూపించారు అక్కడ. ఆ పిల్లలు చూడండి ఐస్ క్రీమ్ కావాలన్నారు, వాడు 100 రూపాయలు చిల్లర లేదంటాడు, ఐస్ క్రీమ్ కూడా అన్నాడు. ఇతను 10 పదుల్లో ఇచ్చాడండి. ఇస్తే టప్పని పడి పారిపోయాడు, 100 రూపాయలు ఇవ్వలేదు అన్నారా. ఈయన వాడినగా పరిగెట్టాడు. వెంటనే ఇంకోటి వచ్చాడు ఈ సూట్ కేసు పట్టుకోవడానికి. అప్పుడు నేను ఆడుకున్న వాడిని పట్టుకున్నాను. నాకు తెలుసు, నాకు అర్థమైంది. అంటే టాలెంట్ అనమాట. వాడు 100 రూపాయలు చూపించి, వాడు ఎంత టాలెంట్ చూడండి. వాడు 100 రూపాయలు చూపించి డబ్బులు తీసుకునే 100 రూపాయలు ఇవ్వలేదు. అతను వీడు వెనకాల పరిగెడుతుంటే వాడు పోయాడు, ఇంకోటి వచ్చాడు. ఇద్దరు దొంగలు అనమాట. వీడు పట్టుకుంటే నన్ను చేయి విడిపించి పారిపోయాడు వాడు. కాదు సూట్ కేసు మిగిలింది. అతను వెళ్ళిపోయి ఒప్పుకుంటే ఈయన వచ్చాడు, వాడు పారిపోయాడు అని. వాడు పారిపోయాడు. మీరు వెళ్ళాక ఇది జరిగింది, జాగ్రత్త చూసుకోండి. టాలెంట్ తక్కువ అంచనా వేయకూడదు. దట్ ఈస్ దేర్ టాలెంట్. మోసం చేయడం కూడా టాలెంటే, తప్పేం లేదు. అంతే, ఇట్స్ ఎ నెగిటివ్ ఇంటెలిజెన్స్, దట్స్ ఇట్. ఓకే, సో ఇలాగా చెప్పాను కదా. ఎన్నో ఇందాక వింటూ ఉంటే నేను రాసుకున్నది ఇక్కడ కూర్చొని రాసుకున్నాను. అలాగే ఇంకా చాలా చాలా అప్లికేషన్స్ మ్యాథమెటిక్స్ వాళ్ళు మనకి ఎన్నో చెప్తుంటారు. కానీ మనం ఎప్పుడు కూడా వీ డోంట్ క్లెయిమ్. ఇట్ ఈస్ నౌ వీ హ్యావ్ టు కమ్ అప్ విత్ దిస్. There are so many opportunities. For example, graph theory. ఇందాక అమ్మాయి ఎవరో గ్రాఫ్ థియరీ గురించి మాట్లాడారు. గ్రాఫ్ థియరీ is lot of potential. In fact, matching problems. ఇందాక ఎవరో మ్యాచింగ్ ప్రాబ్లమ్స్ గురించి మాట్లాడారు. మ్యాచింగ్ అని మాట వాడలేదు కానీ మ్యాచింగ్ ప్రాబ్లమ్స్. మ్యాచింగ్ అంటే మ్యారేజ్ మ్యాచింగ్ కూడా మ్యాచింగ్ ప్రాబ్లమే. 1,00,000 మంది అబ్బాయిలు ఉన్నారు. ఇప్పుడు అబ్బాయిలు ఎక్కువైపోయారు, అమ్మాయిలు తక్కువైపోయారు. అబ్బాయిలు ఉన్నారు, ఒక అమ్మాయికి సంబంధం చూసుకోవాలనుకుంటుంది. అమ్మాయి 1,00,000 మందిలో ఒకటి సెలెక్ట్ చేసుకోవాలి. ఎలా సెలెక్ట్ చేసుకోవాలి? ఎక్కువగా అమ్మాయిలే కనిపిస్తారు. ఇన్సిడెంటల్లీ ఆంధ్ర యూనివర్సిటీలో 70% ఇప్పుడు అమ్మాయిలేట. కొన్ని డిపార్ట్మెంట్లో అబ్బాయిలు లేరట, మన వీసీ గారు చెప్పారు. సో ఇట్స్ గుడ్ దట్. సో ఎలా సెలెక్ట్ చేసుకోవాలి? వాట్ ఆర్ ది పారామీటర్స్ ఫర్ మ్యాథమెటిక్స్? ఇప్పుడు మ్యాచింగ్ అనమాట, మ్యారేజ్ మ్యాచింగ్. ఎలా సెలెక్ట్ చేసుకోవాలంటే ఒక అమ్మాయి మ్యారేజ్లో సెలెక్ట్ చేసుకో, అమ్మాయినా అబ్బాయినా, X to Y or Y to X, whatever. సో ఎలా సెలెక్ట్ చేసుకోవాలి అంటే యూ హ్యావ్ టు ఐడెంటిఫై పారామీటర్స్. దిస్ ఇస్ ఎ బిగ్ ప్రాబ్లమ్, ఐ టెల్ యూ, ఇన్ కంప్యూటర్ సైన్స్. ఇట్స్ ఎ మ్యాథమెటికల్ ప్రాబ్లమ్. పీపుల్ ఆర్ ట్రైయింగ్ టు రిజాల్వ్ ఇట్. సో యూ నీడ్ టు ఐడెంటిఫై ది బేసిక్ పారామీటర్స్. మ్యారేజ్ కావాల్సిన పారామీటర్స్ ఏంటి? ఏజ్, బ్యూటీ, క్యారెక్టర్, డీసెన్సీ, ఎడ్యుకేషన్, ఫైనాన్స్, తర్వాత గౌరవం, హెల్త్. ఏదో పెట్టాను పేర్లు, ABCDEFGH. A ఫర్ ఏజ్, B ఫర్ బ్యూటీ, C ఫర్ క్యారెక్టర్, D ఫర్ డీసెన్సీ, E ఫర్ ఎడ్యుకేషన్, F ఫర్ ఫైనాన్స్, G ఫర్ గౌరవం, H ఫర్ హెల్త్. ఇవి మ్యాచ్ అవ్వాలి. మ్యాచ్ ఎగ్జాక్ట్గా అవ్వవు. ఎందుకంటే ఒకవేళ మంచి హెల్తీగా మంచి బాగుంటాడు కానీ వాడితే డబ్బులు ఉండకపోవచ్చు. ఏదో ఉద్యోగం ఉంటుంది, నార్మల్గా ఉంటాడు. అప్పుడు ఏం చేయాలి? ఉద్యోగం లేదు కానీ మానేస్తావా? ఉద్యోగం కాదు, వాడి దగ్గర డబ్బులు లేవని మానేస్తావా? డబ్బులు బాగా ఉండొచ్చు కానీ ఆరోగ్యం బాగోలేకపోవచ్చు. అప్పుడు ఏం చేస్తావు? అందుకని ఏం చేయాలంటే అన్నిటికీ 0 to 10 లోపల స్కేల్లో వేసుకొని ఆ వాల్యూస్ కంపేర్ చేసుకొని ఏదో లీస్ట్ స్క్వేర్ ఫీట్ కడితే వాట్ ఈస్ ద మినిమం మోస్ట్, దట్ వుడ్ బి ది బెస్ట్ చాయిస్. ఇది డేటా మైనింగ్ లో ప్రాబ్లము అవ్వకండి, ఇట్స్ ఏ ప్రాబ్లం. ఇప్పుడు గోదావరి పుష్కరాలు జరిగాయి, 3 కోట్ల మంది స్నానం చేస్తారు. లేదా ఈసారి నెక్స్ట్ జరిగితే 5 కోట్ల మంది స్నానం చేస్తారు. హౌ డు ఐడెంటిఫై సంబడి? హౌ టు గివ్ ద ఫెసిలిటీస్ టు దెమ్? ఇట్స్ ఆల్ మ్యాథమెటిక్స్, నథింగ్ ఎల్స్. మీరు కంప్యూటర్స్ లో ప్రోగ్రామ్ చేయగల, దే ఆర్ ఆల్రెడీ టూల్స్. మీరు ఐడియా ఇస్తే చాలు, దట్ ఈస్ డన్. ద ఓన్లీ థింగ్ ఈస్ వీ హ్యావ్ టు కమ్ అప్ టు దట్ లెవెల్. ఇంక ఈ మ్యాథమెటిక్స్ లోను మనం ఇంకా డివైబిడిటి దగ్గరే ఉండిపోయి కాకుండా డివైబిడిటి తర్వాత డివైబిడిటి దేనికి? బ్లడ్ ఫ్లో వల్ల, బ్లడ్ ఫ్లోలో ఎలా వెళ్తుంది? IIT కాన్పూర్ లో ఎంటెక్ బయాలజీ స్టార్ట్ చేస్తున్నారు. ఇమాజిన్. ఎందుకంటే వాళ్ళకి కావాల్సింది ఏంటంటే నౌ ఆత్మనిర్భర్ భారత్. మనం ఎవరికో ప్రాబ్లం సాల్వ్ చేయడం కాదు, మన ఇండియాలో ప్రాబ్లం సాల్వ్ చేసుకోవాలి. మనకుండే రెగ్యులర్ ప్రాబ్లమ్స్ వేరు. మన పేపర్లో ఎక్కడో పబ్లిష్ చేస్తే వాడెవడో వాడుకుంటున్నాడు, అంతే కదా. పార్టిషనల్ అర్థం కానీ ఏదైనా సరే మనకెలా ఉపయోగపడతాయి? మనం ఎలా వాడి దగ్గరికి వెళ్ళి వాడు పేటెంట్ తీసుకొని మన దగ్గర డబ్బులు తీసుకొని వాడు మనకి ఇస్తున్నాడు. ఇలా కాకుండా ఐఎమ్ షూర్ సి గ్రేట్ థింగ్స్ హ్యావ్ స్మాల్ బిగినింగ్. తెలుగులో చెప్పాలంటే ఏం చెప్పాలి? మర్రి విత్తనంబు వృక్షంబునకునంత విశ్వదాభిరామ వినురవేమ. మర్రి చెట్టు ఉత్తరం ఇంతే ఉంటుంది, కానీ పెద్ద షాక్ ఆఫ్ సెల్. అలాగా ఇలాంటి కాన్ఫరెన్స్లు దే ఆర్ బిగినింగ్ ఫర్ గ్రేట్ థింగ్స్ టు హ్యాపెన్. మీరందరూ ఇప్పుడు కాన్ఫరెన్స్ లో పాల్గొనే వాళ్ళందరూ మీ ప్రెజెంటేషన్లు ఆ తర్వాత రాబోయే కాలంలో మీ యొక్క డైరెక్షన్ ఫిక్సప్ చేస్తాయి. అండ్ ఐఎమ్ షూర్ everybody becomes great because opportunities are plenty and you have the talent. You should have. ఇంకేడు మిస్సింగ్, ఇంకేడు కావాలి? ఆపర్చునిటీస్ ఉన్నాయి, టాలెంట్ ఉంది, ఇంకేడు కావాలి? గ్రాబ్ ద ఆపర్చునిటీ. ఆపర్చునిటీ knocks your door twice. Once when it comes, second time when it goes. Already it has come to you. You have knocked the door. It has knocked the door. Now it is up to you to grab the opportunity. And well, ఇది ఎక్కువ మాట్లాడేస్తున్నాను. ఐ థాట్ మా డిపార్ట్మెంట్ కదా, నాకు చాలా ఆనందం వేసింది. ఇలాంటి కాన్ఫరెన్స్ ఆర్గనైజ్ చేస్తున్నారు. మా గురువు గారికి ప్రణామాలు చెప్పుకోవాలి. కానీ ఇలాంటి కాన్ఫరెన్స్ మా టైంలో ఏమి ఉన్నట్టుగా నాకు గుర్తురాలే. సో థ్యాంక్ యూ ఆల్ ఫర్ దిస్ ఆపర్చునిటీ. ఐఎమ్ షూర్ ఐ హావ్ డన్ సమ్ కంట్రిబ్యూటెడ్. ఐ హావ్ told you something which might lead you to some success. Thank you all.
Thank you, Professor Ardhani Garu, for such inspiring speech. We thought we missed an invited lecture by Professor Ardhani Garu, but now we had a invited lecture on applications of mathematics. So, next, I call upon Sujata Madam to talk on the proceedings of the conference, report of the conference.
Good evening, Mananda. First of all, Gurubhyo Namaha. With the permission of my Guru, Professor KPR Sastry Garu, I am going to give a report, a conference report, sir. Can I, sir? Thank you, sir. So this is a conference report based on both the days, 2 days. Day 1, the conference started with the inaugural function. Chief guest of the inaugural function, Professor KPR Sastry Garu, Chairman of UASMS and President of SMSMS. Guest of honor by Professor GP Rajshekhar Garu, Department of Mathematics, IIT Kharagpur, President of UASMS and Vice President of SMSMS, Professor KKM Sharma Garu, Director of the conference, Professor P. Anuradha Kameswari Garu, and Convener and Organizing Secretary, Professor C.H. Srinivas Rao Garu, and inaugurated the conference with the lighting the lamp and prayer song by Professor M.V.R. Kameswari Garu, Geetham University. Keynote address 1 by Professor YJ Cho, online presented and chaired by the Professor GVR Babu Garu. First, we invited talk by Professor Kanya Ja. These are also online and chaired by the Professor K. Rajendra Prasad Garu. Second invited talk by Professor P.P. Murthy Garu, that is also online and chaired by the Professor P.D.N. Srinivas Garu. Followed by paper presentations, both offline and online. Offline 11 presentations was done and online 14 presentations were done. Keynote address, second keynote address by Professor G.V. Ravindranath Babu Garu and chaired by the Professor G.P. Rajshekhar Garu. And third invited talk by Professor G.P. Rajshekhar Garu and chaired by the session by Professor M.V.S. Murthy Garu. And coming to the second day, that is the 31st today, second day of the conference started with the fourth invited talk by Dr. K.N.V.V. Varaprasad and chaired by the session Professor K.K.M. Sharma Garu. Fifth invited talk by Professor Vishnu Narayan Mishra and chaired by the session Dr. M.V.R. Kameswari. Sixth invited talk by Professor G. Nanaji Garu and chaired by the Dr. K.N.V.V. Varaprasad Garu. Seventh invited talk by Professor Ramesh Kumar Watts and this is online, chaired by the Professor B. Muniswamy Garu. Eighth invited talk by Professor D. Dhananjay Gopal and chaired by the Professor Vishnu Narayan Mishra. Ninth invited talk by the Dr. A.S.V. Ravikant Garu online and chaired by the Professor G. Nanaji Rao Garu. And followed by the paper presentations. And today offline presentations are 17 and online presentations are also 17. 10th invited talk by the Professor Hemant Kumar, that is also online and chaired by the Professor N. Ramakrishna Garu. 11th invited talk by the Professor K. Venkateswar Garu and chaired by the Professor P.D.N. Srinivas Garu. 12th invited talk by the Dr. Dina Sunil, chaired by the Professor N.V.S. Murthy Garu. And 13th invited talk by the Professor Anita Tomar, online, chaired by the Professor P. Anuradha Kameswar Garu. Last but not the least, the 14th invited talk by the Professor J. Vasundhara Devi Garu, chaired by the Dr. Sujata, and total 266 registrations done in this conference. It's a very big number, and both offline and online together. Finally, we have few sponsors. Those are Diamond Energy Services, Vijayawada, 50,000, and Gayatri Degree College, Tuni, 10,000, SV Degree College, Tuni, 10,000, Gayatri Degree College, Kotavaratla, 10,000, Sri Sai Siddhartha Education Institution, Gajapati Nagaram, 10,000. So totally 90,000 sponsor amount we got it from the sponsors. Finally, this conference ended with the valedictory function. Thank you.
Andhra University has supported us with 20,000. But Professor Madam has missed mentioning it. And we had the influence of our organizing secretary, sir, in providing us with lunch, 2 sponsored lunches and 1 sponsored dinner. They're all possible because of the influence he has used, our organizing secretary has used. Now I request our Chief Guest, Professor Ravindra Babu Garu, to please give his address.
Pleasant evening this is. Respected President of this valedictory function of this International Conference on Pure Applied and Engineering Mathematical Sciences, ICPAEMS 2024, P. Anuradha Kameswar Garu, Head of the Department of Mathematics, Andhra University, and Organizing Secretary of this conference, C.H. Srinivas Rao Garu, well organized, and today's guest of honor, Professor P.S. Avadhan Garu, excellently he delivered his lecture. And good morning to all of you. And my dear department colleagues, Professor P.D.N. Srinivas Garu, Professor Nanaji, Professor S. Ravi Kumar, Professor N. Ramakrishna, good evening to all of you. And most important person in my life in fixed point theory is Professor K.P.R. Sastry Garu. My pranam to Professor K.P.R. Sastry Garu. Today I am here and talking with you proudly, saying that it is with the krupa of Professor K.P.R. Sastry Garu. And he is mentor to me. And now, respected Professor K.P.R. Sastry Garu, Chairman of UASMS and President of SMSMS, and Professor K.K.M. Sarma Garu, he is my classmate when I studied MSc, both are classmates and co-research also with under the guidance of one professor, Professor S.V. Krishna Garu. We both did PhD under Professor S.V. Krishna Garu. Myself did in differential equations with impulse effect, whereas he did in fuzzy non-linear spaces. And later, we entered into the fixed point theory. It encouraged us a lot. Myself and Professor K.K.M. Sarma also, we did work in fixed point theory. And Professor K.K.M. Sarma, President of UASMS and Vice President of SMSMS, and Professor P. Kameswari, Director of this conference, Professor C.S. Srinivasarao, Convener ICPAEMS 2024, Vice President of UASMS and Secretary SMSMS. Good evening to all of you. Dear delegates from various parts of the country and abroad, and who attended this conference online and offline, good evening to all of you. And here I wish to say one more thing. Professor J. Vasundhara Devi, she was junior to me. And she also did MPhil under the guidance of Professor S. Krishna Garu, and she did PhD at Florida Institute of Technology, I think, under the guidance of Professor V. Lakshmikantan Garu. She was my junior. And here I wish to say, first, I thank the Department of Mathematics, Andhra University, and Uttarandhra Society for Mathematics and Mathematical Sciences, and Professor S. Meenakshi Sundaram Memorial Society for inviting me as chief guest for this valedictory function. I congratulate Professor P.A. Kameswari, Director of the conference, and Professor C.S. Srinivasarao, Convener, who organized successfully in a befitting manner. Excellently, they organized. In this conference, so many topics are covered. Its name is International Conference on Pure Applied and Engineering Mathematics, and the delegates, the participants, the invited talks who have given invited talks, all have did justice to this title of the conference. I'm very happy for that one, because its area is broad area. Pure applied and engineering mathematical sciences means not as if it is in one area, if it is in one subject, only narrow, it will be narrow. But it has given an opportunity to participate many mathematicians to discuss their problems. It has given this the conference platform has given an opportunity to discuss many more problems. Professor Avagan Garu has given in many directions, many directions, the opportunities and to do research, many opportunities to do research. So it is a great opportunity to all of you to think about this one and work in those directions. Here, most of the delegates some are students are also here and new entrants in the research. I wish to give suggestion. How to do research? How do we get ideas? Once you get an idea, it is not easy to pursue that one and get success. Okay, so many people. ఒక పక్షి ఉందండి, ఎగురుతా ఉంది, ఆహా చూసేసి మనం విమానం చేసేసి అంటే అంత తేలికైన వ్యవహారం కాదు. చెప్పుకోవడానికి తేలిగ్గా ఉంటుందండి, టెక్నిక్ తేలిగ్గా ఉంటుంది, కానీ ఆ టెక్నిక్ ను ఉపయోగించి మనం ఆ స్థాయికి ఎదగడం అనేది ఇట్ ఈస్ వెరీ డిఫికల్ట్ అండి. అందుకే నేను ఒక విషయాన్ని ఎప్పుడు చెప్తా ఉంటానండి, ఏంటంటే ఆల్వేస్ స్టడీ టెక్స్ట్ బుక్స్. ఇప్పుడు మీరు వీఆర్ ఆల్ మ్యాథమెటిక్స్ స్టూడెంట్స్, సో వీ హ్యావ్ టు స్టడీ మ్యాథమెటిక్స్ టెక్స్ట్ బుక్స్. క్యాలిక్యులస్ కావాలి, ఆల్జిబ్రా కావాలి, అనాలిసిస్ కావాలి, టోపాలజీ, డిఫరెన్షియల్స్, ఆల్ సబ్జెక్ట్స్ ఆర్ నీడెడ్. ఎంఎస్సి స్టడీస్ సబ్జెక్ట్స్, ఆల్ సబ్జెక్ట్స్ ఆర్ నీడెడ్. బియాండ్ దట్ వన్ ఆల్సో, ఇఫ్ యూ వాంట్ టు డూ రిసర్చ్, బియాండ్ దట్ వన్ ఆల్సో యూ హ్యావ్ టు స్టడీ సమ్ మోర్ బుక్స్ టు గెట్ నాలెడ్జ్. ఆఫ్టర్ దట్ you have to fix your topic. Topic means subject. Then related research papers or monographs, you study those monographs according to your goal. You prepare yourself in your mind how to solve your problem or how to solve your problem. That one, like that, you study. Then only you can get success. Here for research, there are two directions. One is you pose a problem suppose you wish to do some problem in differential equations or integral equations, whatever it is, or mathematical problem, mathematical modeling problem, whatever it is, you take that problem. While doing that problem, you need some mathematics, pure mathematics, or some lemmas or some new structures you need. Then you develop that need according to your goal to get the benefit or to get the success of that goal. So the development will be like that. The other one is we have some work. Work means in suppose I am interested in fixed point theory, so I study metric fixed point theory and its developments. Yesterday I have given some information like that I studied, and after that one you generalize, you improve. Like that also you can do research. So in these two directions, choose your way and do your research work. You will surely get success. And whenever you study, you will have so many doubts. Ask those doubts, to clarify those doubts by asking your director, or otherwise it is better you discuss with your colleagues. మేము స్కాల్స్ ఉండేవారమండి, మేము చదువుకునే రోజుల్లోనూ డిపార్ట్మెంట్ లో స్కాల్స్ రూమ్ ఒకటి ఉంటుంది. అక్కడ మేము ఏం చేసేవాళ్ళం అంటే ప్రాబ్లమ్స్ ని డిస్కస్ చేసేవాళ్ళం అండి. నిజంగా చెప్తున్నా, ఇప్పుడు నాకు ఏదైనా ప్రాబ్లం రాలేదనుకోండి, ఒక మ్యాథ్స్ వెళ్ళి బోర్డు మీద దాన్ని క్లియర్ గా చెప్పేవారు. ఇన్ ది సేమ్ వే వాళ్ళకి తెలియదు, మేము వెళ్ళి బోర్డు మీద చక్కచక్క వెళ్ళడం, వాటిని బోర్డు మీద ఎక్స్ప్లెయిన్ చేయడం. అది మిమ్మల్ని చాలా ముందుకు తీసుకెళ్తుందండి, చాలా చక్కగా ఆలోచించే విధానాన్ని తీసుకొస్తుందండి, చాలా మిమ్మల్ని సక్సెస్ వైపుకి తీసుకెళ్తుందండి. మరొక విషయం ఇక్కడ, నవేడేస్ మీరు యూ విల్ గెట్ యువర్ రిజల్ట్స్ ఓకే, కానీ నవేడేస్ అప్లికేషన్స్ ఆఫ్ ద రిజల్ట్స్ అబ్టైన్డ్ ఈజ్ ఇంపార్టెంట్. అప్లికేషన్ చాలా ఇంపార్టెంట్ అండి. అందుకోసమే ఏం చేస్తామంటేనండి, మన if we some result we obtained, then we are getting an example in support of that result. And ante kadandi, if you relax any hypothesis condition, then the result may fail. Such examples are also very very important. So aa rakanga kuda meeru cheste daniki it will be, you will be get benefited. And the research paper will be published in Science Citation Indexed Journal. So like that, all of you do hard work, and at the same time you search for applications, and even applications ni jo add cheste, it will be an added benefit to you and society ki adi upayogapadutundandi. Tarvata ninnati రోజున Professor G.P. Rasek delivered a talk on PD and used shorter fixed point theorem to get existence of solutions, and showed engineering applications also. So అక్కడ 3 directions లోనూ ఆయన టాక్ ఇచ్చారండి. అది నాకు బాగుంది, బాగా నచ్చిందండి. తర్వాత మరొక విషయం, ఇక్కడ మన స్టూడెంట్, ఫస్ట్ ఇయర్ స్టూడెంట్ వాసవి, సాధారణంగా ఏంటంటేనండి, ఇప్పుడు ఏమైనా మనం అబ్స్ట్రాక్ట్ ఆల్జిబ్రా అని చదువుతారు. అబ్స్ట్రాక్ట్ ఆల్జిబ్రా అని చదివితే ఇట్ ఈస్ జస్ట్ అబ్స్ట్రాక్ట్, ఇట్ ఈస్ నాట్, వీఆర్ అనేబుల్ టు అండర్స్టాండ్ లైక్ దట్ అలా అనుకుంటారు అందరూ కూడా, బట్ ఇట్ ఈస్ నాట్ ట్రూ. యాక్చువల్గా చెప్పాలంటే వాసవి ఎక్సలెంట్లీ షీ ఎక్స్ప్రెస్డ్ ద వ్యూస్ ఆన్ గ్రూప్ థియరీ. ఏమంటే అందులో ఉన్న అప్లికేషన్స్ అన్ని చెప్పిందండి. కాబట్టి ఇప్పుడు ఇందాక బూలియన్ ఆల్జిబ్రా అని చెప్పారు మాస్టర్, ఏమంటే బూలియన్ ఆల్జిబ్రా కంప్యూటర్ అప్లికేషన్స్ ఉన్నాయన్నారు. సో మ్యాథమెటిక్స్ చదివింది ఏది వృధా పోదండి. మనం చక్కటి మ్యాథమెటిక్స్ చేయడం, చక్కటి రీసెర్చ్ చేయడం, పబ్లికేషన్స్, మంచి పబ్లికేషన్స్ ఉండడం, ఇవన్నీ కూడాను మనం మ్యాథమెటిక్స్ కి ఎంతో జస్టిస్ చేస్తున్నట్టు లెక్కండి. తర్వాత ఈ చదవడం వల్ల ఏమిటండి ఉపయోగం ఏంటండి, మేము చదివేస్తున్నాము, వాట్ ఈస్ ది పర్పస్? ఏమంటే మనం పర్పస్ అంటే నేను ఒకటే అనుకుంటానండి, ఏటి గురించి అసలు ఆలోచించకూడదు, నాకు ఇది వచ్చేస్తుంది, దీనివల్ల నేను ఇది ఇచ్చేస్తాను అని. మనం వర్క్ చేస్తే ఆ వర్క్ కి సంబంధించి మనకు ఆపర్చునిటీస్ కూడా వస్తాయండి. ఆ ఆపర్చునిటీసే మిమ్మల్ని మంచి పొజిషన్ లో ఖచ్చితంగా నిలబడుతుందండి. అదే మీకు గౌరవం. ఆ గౌరవంతో ఎంతో సంతోషంగా ఉండగలుగుతారండి. సో విత్ దీస్ ఫ్యూ రిమార్క్స్ I wish to conclude, this conference is an inspiration to other educational institutions to organize mathematical conferences. I'm expecting many more international conferences of this sort from our department, C.H. Srinivasarao and other faculty members. It is my opinion. And so, try to do in that direction also. And thank you very much for inviting me as chief guest. Thank you one and all. Thanks very much. And
Thank you very much, sir, for your motivation and lecture. It really inspires all our participants and our students here. Next, we have paid stations. I request first, on behalf of the organizing committee, I invite Professor KPR Shastri Garu, Chairman Uttarandhra Society of Mathematical Sciences, to please occupy the chair and accept our felicitation.
Raju. Run master.
I request all the delegates to please join in the felicitation.
Yes. Thank you, sir. అసలు పైకి ఎక్కడ కాల్ మన సభ్యులకు ఉన్నాయి అసోసియేషన్ సభ్యులకు కూడా మాట్లాడండి తర్వాత రిజిస్ట్రేషన్ 2 విషయాలు మాట్లాడండి ఇప్పుడే మాట్లాడండి ఎక్కువ మాట్లాడి టైం అయిపోయింది
My dear friends, this is a rare and present event. I remember for long. And before that, I want to say something about UASMS and Professor SMS. The members of both the institutions, both the societies, they are active. Yesterday, I do not remember whether I named all those members or not. Professor Srivastav, Professor he is not here, and Professor Sujata. I was saying about them. There are other members. Professor Kamesri is there. She is from Gedam University. And Professor Ayyap Shastri was there from Gayatri Institute. And Bhaskar, I suppose I mentioned. And Venkateswar Rao from Junior College. And whom somehow to say Dr. Kiran, that I must mention now. Dr. Kiran, he was because Bhaskar demise due to COVID, we inducted Dr. Kiran into our fold, and these two institutions are in their baby stage, facing so many teething problems. So, I hope you agree, the present governing bodies or the executive bodies, they continue for some more time for a happy, healthy functioning of these two institutions. In this connection, I am very much grateful to the head of the Department of Mathematics, Professor Kamesri. Somehow I am shivering in my foot whether I can complete my talking or not. I don't. I got so much of cooperation from all corners. And Dr. Srinivasa, he helped a lot. Not only that, he gone a little out of the way and he roped in his wife, Venkatratnam, superintendent of police crime of this city. You know why? Perhaps many of you may not know. Dr. Kiran, where is he? Kiran is there? Where is he? He is not here? In a comfortable right with it. You know, we enjoyed a dinner last night. And Professor Sujata mentioned so many donors and all those things. And the primary donor, the entire donor, who donated, who is responsible for that dinner at Daswala yesterday is Dr. Kiran. My opinion. And he wanted to give a party on the occasion of his getting his PhD, and his director, supervisor, he just sitting there, Professor Kamesri from Getam. Surprisingly, you are sitting calm and your student also is sitting calm. How do I recognize from this distance? The supervisor and the student are there. And she is from Kamesri, her name also is Kamesri, he is from Gedam University. And what's your name? Kiran. Kiran, he sponsored the dinner yesterday. Many of you must have enjoyed it. and almost all enjoyed it. All enjoyed it except me. Somehow I don't enjoy that one. So I asked him to give me one more dinner. I don't like that. Okay. So these were, he is polite and she is also polite. And perhaps she encouraged him to sponsor this dinner, I don't know. But in this connection, why I am saying that Professor Srinivasa roped in his wife into this fold is that she came to that, she attended that dinner party. Not only that, she made the management of Daswala to give a significant discount in the cost. That's why I asked Kiran, don't take away that discount. Give me another dinner. Okay, sir. So, sir, it is thing. So many people have responded for our request to give some sponsoring or small amounts, even though it is small, and the rest of the amount is needed, and whatever we have to bear is beyond the total expenditure it is, the income it is, there is a difference here. So our governing body has decided to share it. Okay? Thank you very much.
Thank you very much, sir. Now we shall continue with the illustration of our chief guest.
I have forgotten. I have forgotten about this. Let me sit here first. Illustration is there? No? For others?
Ah, yes, sir.
Okay. Oh, my illustration is already over.
So, I request Professor Avdhani Garu to please felicitate our chief guest.
మీరు చెప్పారండి నాకు ఒక మాట చెప్పారు మీరు Blue. అది బ్యాగ్ ఇవ్వండి సార్ ప్లీజ్ మేడం క్లోజ్ సార్ సార్ బాగున్నాయి సార్ ఫిల్మ్ లేదు ఓకే సార్ ఇప్పుడు ఫిల్మ్ అక్కర్లేదు సార్ టెక్నాలజీ మారిపోయింది మాస్టర్ మాస్టర్
Now I request our chief guest, Professor G. Ravindranath Babu Garu, to please felicitate our guest of honor, Professor P.S. Avdhani Garu.
Madam, please close. Yes, ma'am. Usher, please. Right. Usher, Ravindra Babu. Okay. Madam, please, madam. Thanks, madam.
Now I request our chief guest and guest of honor to please felicitate our UASMS executive members, Professor Sujata Madam. Please, madam.
అక్కడికి వచ్చేయండి అక్కడ చేసేద్దాం సార్ అందరూ రాలేదు మాషాల్లా Please, all the staff members, please come and join with us. Thank you. Yes, sir. Okay, sir. Marshal, Rajavan, Marshal, thank you, sir. Sir, please, sir. Madam, please. Madam. Sir. Thank you, sir.
Now I request the next executive member, W.R. Kameshwari Madam, to please.
And please. Sir, please, Marshal. Yes, sir. Thank you.
వెరీ ఇంపార్టెంట్ అండి
I request Director and Head of the Department of Mathematics, Anuradha Kameshwari Garu, please occupy the appreciating chair. I request our Guru, Professor K.P.R. Shastri Garu and Professor Avadhani Garu, President of UASMS, Professor K.K.M. Sharma Garu, Professor G.V.R. Babu Garu, and Chairman Board of Studies, Professor P.D.N. Srinivas Garu, Professor Nanaji Garu, Professor Ravi Kumar Garu, Professor Ramakrishnan Garu, and all please come and join with us for felicitating the Madam Anuradha Kameshwari.
Madam, please, madam. Sir, please, sir. Madam, decorate, madam. Thanks, madam.
నాకు అంటే ఫెలిసిటేటింగ్ ముందు నాకు ఈ కార్యక్రమాన్ని సక్సెస్ చేయడానికి నా బెస్ట్ ఫ్రెండ్స్ ఇద్దరు వచ్చారు. వాళ్ళకి నేను సన్మానం చేయాలి. ఒకరు కామర్స్, ఒకరు కెమిస్ట్రీ. అంచేత విత్ యువర్ పర్మిషన్ అంచేత ప్రొఫెసర్ ప్రభాకర్ ప్లీజ్ కమ్ అండ్ జాయిన్ విత్ us ప్లీజ్. వాళ్ళు అసోసియేషన్ మొదటి నుంచి నాకు దే హెల్ప్ మీ ఎ లాట్ రిగార్డింగ్ దిస్ కాన్ఫరెన్స్. ప్లీజ్ a token of memory and
Order అయిపోయింది. He says it must be done. Marshal, మీరు చెప్పండి.
ఒకసారి big round of applause please.
Madam. Thank you, sir.
Next person, Professor G. Venkateswara from Department of Chemistry, is also best friend and he helped me a lot regarding this conference.
ఫోటో తీసాను మేడం క్లోజ్ మేడం మేడం మాస్టర్ సార్ దగ్గర సార్ ప్లీజ్ సార్ మాస్టర్ థ్యాంక్ యూ సార్ శ్రీనివాసరావు
నేను రిజిస్ట్రేషన్ చేసుకుంటాను కానీ మరి డయాసిక్ మాట్లాడాలి ఎప్పుడు మాట్లాడాలో తెలియదు. తర్వాత మీరు అందరూ నాకు డయాసిక్ 2 నిమిషాల తర్వాత మాట్లాడుతున్నారు ఆఫ్టర్ రిజిస్ట్రేషన్. ఓకేనా? అంటే కార్యక్రమాన్ని ఎంత
Now I request Srinivasrao garu to accept our felicitation from Chief Guest Ravindranath Babu garu, Guest of Honor Professor P.V.S. Avadhani garu, and his guru K.P.R. Shastri garu, P.D.N. Srinivas garu, Nanaji Rao garu, Ravi Kumar garu, K.M. Sharma garu.
Thank you, sir.
Next is certificate distribution for paper presentations. So we call upon the names of the paper presentation presenters. One more felicitation to the executive member, Kiran. Mr. Kiran, please.
W1. General sponsor and executive USMS executive member. Sir, please. Master, please. Thank you, sir.
Vishwajit Rath. K. Bhushanam. K. Bhushanam. N. Madhubala. Sir.
My Churma. Okay.
In Sai Tejashwini.
Ma. Thank you, sir.
G. Srinivasarao.
చప్పట్లు ఒకసారి ప్లీజ్ దయచేసి సార్ ప్లీజ్ సార్
K. Nirisha. K. Nirisha.
Madam, please.
D.V. Padmaja.
Madam, please, madam. Big round of applause, please. All of you.
K. Vijay Prasansa. Mr. G. Srinivasarao.
Madam, please, madam. Sir, please, sir.
Ms. M. Madhuri.
Continue చేయండి మేడం.
A. Bharati.
Sir, please, sir.
A. Bharati. G. Srikanya.
Okay.
B. Padmavati.
Ma, please, ma. Ma. Ma, please.
C. H. Vijay Kumar. Sir, Mr. G. Srinivas. R. Bulli Babu. Mr. R. Bulli Babu. Mr. R. Bulli Babu. Miss G. Divya Kumari. Miss E. Kanakamaha Lakshmi. Helena. Mr. P. Tejeshwar Rao.
Master P, sir. Sir.
Sir, now we have best paper presentation offline given to Miss K. Nirisha for her paper on a statistical analysis of non-Newtonian nanofluid flow model in a single phase squeezing channel. Offline mode lo best paper presentation ki select chesaru. Yes, ma'am. Now I announce best paper presentation online mode to Miss L. Josna for her paper Attack Bounds of RSA-like cryptosystems. With that,
Secondly, wanted to speak.
yes. So we have finished paper presentation certificate, and now vote of thanks is by organizing secretary.
All of you please sit down. దయచేసి అందరూ ఒకసారి కూర్చుంటారండి. అంటే బిఫోర్ saying the vote of thanks, so I would like to invite Mr. P. Durgarao. He is my student, so he helped me a lot right from beginning to the conference to till today evening this time. So ఆయనకి మా గురువు గారి చేతుల మీద ప్రొఫెసర్ జీవీఆర్ బాబు, ప్రెసిడెంట్ కేకేఎం శర్మ గారు, అవధానుడు మాస్టర్ గారి చేత ఆయన సన్మానం చేద్దామని మీ అందరూ అంగీకారంతో నేను ఒక ఇచ్చేద్దామని లాస్ట్ లో ఉంచాను. ప్లీజ్ ఫెలిసిటేషన్. దుర్గారావు ప్లీజ్ ఆట్ మీద ఫెలిసిటేట్ చేయి. ఇతడు ఈ మొత్తం అన్నిటికీ కూడా దుర్గారావు మొత్తం అంతా ఈ లెటర్స్ రాయడం కానీ అదంతా చేయడం కానీ మొత్తం అంతా చాలా హెల్ప్ చేశారు నాకు కాన్ఫరెన్స్ లో.
Then I would like to remind you of Miss Tarani.
Tarani my student here. Next one more important person, Tarani. No, అంటే మా స్టూడెంట్ కాబట్టి నేను సన్మానం అని నేను అనలేను, కానీ అమ్మాయి ఎంత చేసిందంటే ఈజ్ ఓన్లీ యూనిక్ రీసెర్చ్ స్కాలర్ అంతే, ఇంకా నేను చెప్పలేదు. కాబట్టి ప్లీజ్ కమ్ తరణి రామ్ ఒకసారి రా, గురువులే కాబట్టి నా ఒకసారి సన్మానం కాదు. తరణికి అంటే ఒక సన్మానం చేయొచ్చో తెలియదు, చిన్నపిల్ల అందుచేత కూర్చో ఆశీర్వచనం. ఓకే అయితే అలా
సో ఇంకొక వ్యక్తి కూడా ఉన్నారు, మౌనిక. అమ్మాయి కూడా చాలా హెల్ప్ చేసింది. అయితే మా గురువు గారి చేతుల మీద, వాళ్ళ గురువు గారి చేతుల మీద సన్మానం చేస్తే బాగుంటుందని నేను అనుకుంటున్నాను. సో నువ్వు వచ్చి ఈ సన్మానం యాక్సెప్ట్ కూర్చో.
మా ప్లీజ్
conclude చేద్దాం with vote of thanks.
I call upon Tejashwini and Madhubala also to please take blessings from Professor KPR Shastri garu.
Next generation. అలా చూడమ్మా, చూడ సరే. అలా చూడమ్మా. ఓకే.
మధుబాల, తేజస్వి వాళ్ళు కూడా పేరు చెప్పలేదు కానీ వాళ్ళు కూడా చాలా 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 హెల్ప్ చేశారమ్మా. నేను ఐ రియలీ అప్రిషియేట్ యువర్ ఎఫర్ట్స్ ఫర్ సక్సెస్ ఇన్ దిస్ కాన్ఫరెన్స్. ప్లీజ్. నౌ ఓట్ ఆఫ్ థ్యాంక్స్. మేడం ఒకసారి మీరు అందరూ కూర్చుంటే ఓట్ ఆఫ్ థ్యాంక్స్ చెప్పండి ప్లీజ్. కూర్చోండి సార్. 2 నిమిషాలు ముగించేస్తాను, చాలా సమయం అయిపోయింది కాబట్టి. ఆల్మోస్ట్ 7:45 అయిపోయింది కాబట్టి ఒక్క నిమిషం ఓట్ ఆఫ్ థ్యాంక్స్ చెప్పే ముందు, సో వై దిస్ కాన్ఫరెన్స్ ఈస్ కాండక్టింగ్ ఇన్ దిస్ డిపార్ట్మెంట్ ఆఫ్ మ్యాథమెటిక్స్, హూ ఇస్ ద ఇనిషియేషన్ ఆఫ్ దిస్ కాన్ఫరెన్స్? ఈ కాన్ఫరెన్స్ ని చేయడానికి ఒక చిన్న విషయం చెప్తున్నాను. ఏంటంటే, వన్ ఆఫ్ మై బెస్ట్ ఫ్రెండ్, క్లోజ్ ఫ్రెండ్ ఇన్ బ్యాడ్మింటన్, he promised me, he was big shot, he was the secretary of big industry, he promised me to sanction 10 lakhs rupees, organize any conference once upon a time while we are playing badminton. So on that day I took a decision. So now why don't I conduct a conference, national or international? So on the fine morning, I went to my Guru Garu KPR Shastri house and I told him, sir, we want to organize an international conference in our department with the collaboration of Department of Mathematics. Okay. So immediately my Guru Garu told me, just you go and ask your head of the department with your permission. So we will organize the conference. So ఆ రోజున నేను సరే ఆయన నాకు 10 lakhs ప్రామిస్ చేశాడు. నేను ఏమనుకున్నానంటే, ఫస్ట్ ఒక నిమిషంలో 60 సెకండ్లో ముగించేస్తాను. వచ్చిన అందరికీ కూడా నోవటల్లో రూమ్స్ ఇచ్చి, ఇన్వైటెడ్ టాక్స్ అందరికీ కూడా $100 ఇద్దాం. $100 ప్యాకెట్ లో $100 పెడదాము అని నేను అనుకున్నాను. 10 lakhs రూపీస్ వస్తాయి కదా అని. సో టైం డ్రాగ్ ఆన్ అవుతుంది. మా ఫ్రెండ్ నేను అడుగుతా ఉంటే ఇదిగో అదిగో అంటున్నాడు. లాస్ట్ కి ఒక 2 weeks ఉందనగా ఆయన ఇంకా హ్యాండ్స్ అప్. సో అప్పుడు నాకు ఐ కెన్ అండర్స్టాండ్ ద పిక్చర్. సో ఆన్ దట్ డే ఇక రూమ్ మాకు కంప్లీట్ గా ఇక ఫండింగ్ కలెక్షన్ వెళ్ళిపోయాను. సో వన్ ఆఫ్ మై అనదర్ ఫ్రెండ్ ఆల్సో ప్రామిస్డ్ మీ అండ్ అగైన్ హి చీటెడ్ మీ. సో ఇక లాభం లేదని నేను ఒకసారి ఎవరికైనా ప్రామిస్ చేస్తే
99.999% ప్రామిస్ ని ఫుల్ఫిల్ చేసుకుంటాను. .001 ఫెయిల్ అవుతానేమో నాకు తెలియదు, కానీ ప్రామిస్ చేశానంటే దాన్ని ఫుల్ఫిల్ చేయాలని చూసుకుంటాను. సో మేము మీటింగ్ పెట్టుకున్నప్పుడు మా గురువు గారికి నేను చెప్పాను, 5 లక్షలు పెట్టి నేను చేస్తాను సార్ అని. మా గురువు గారు ఇంత లావ్ అయిపోయారు. ఇంకా శ్రీనివాసరావు 5 lakhs కలెక్ట్ చేసి తెస్తానంటున్నారు. గో హెడ్, ఇంకా దేర్ ఇస్ నో లిమిట్, స్కై ఇస్ ద ఓన్లీ లిమిట్ అని అన్నారు. నేను కూడా అలా అనుకున్నాను. రాత్రి మీరు నమ్మరు, 2 weeks నుంచి కూడా, బిఫోర్ 2 weeks నుంచి 3 గంటలకు మెడికల్ వచ్చేసేది ఎవ్రీడే. నా వైఫ్ సో మెనీ టైమ్స్ ఆస్కుని, ఎందుకంటే మీరు టెన్షన్ ఫీల్ అవుతున్నారంటే, ప్రామిస్ చేశాను గురువు గారికి, వీళ్ళు చేతులు ఎత్తేసారు ఎలాగా అంటే, ఆమె ఏమందంటే మీరేం వెళ్ళకండి, మీ జీతం 2 లక్షలు, నా జీతం 2 లక్షలు, ఒక 1 month శాలరీ కాదనుకుంటే మీకు ఇది ప్రమాణం సక్సెస్ అవుతుంది, మీకు మంచి నేమ్ వస్తాను. ఆ రోజు నుంచి కొద్దిగా ధైర్యం తెచ్చుకుంటే, డిపార్ట్మెంట్కి వచ్చేసరికి డల్లగా ఉంటుండే అని, డల్లగా ఉంటే నా తరణి నాకు రీసెర్చ్ స్కాలర్ కాదు అమ్మాయి, ఆల్మోస్ట్ నాకు కూతురు లాంటి పిల్ల. ఓకే, సో అమ్మాయి ఎప్పుడు ఎందుకు సార్ ఎలా జరగాల్సి జరుగుతుంది, మీరు భయపడకండి అంటే, అప్పుడు నేను అనదర్ సిస్టర్ హెడ్ ఆఫ్ ద డిపార్ట్మెంట్ ఆఫ్ మ్యాథమెటిక్స్ ఆంధ్ర యూనివర్సిటీ శ్రీమతి అనురాధ కామేశ్వరి, నేను సిస్టర్లీ కన్సర్న్ అనమాట. ఆమె ఒకసారి చెప్పింది, మీ బిహైండ్ యువర్ బ్యాక్, యూ డోంట్ వరీ అని చెప్పేసరికి నాకు ఇంకా ధైర్యం వచ్చింది. తర్వాత మేము మీటింగ్ పెట్టుకునేటప్పుడు కామేశ్వరి మేడం, గీతం కామేశ్వరి ప్లస్ సుజాత, సెంజర్ సుజాత, వాళ్ళిద్దరూ మరొక 2 సిస్టర్స్ నాకు. వాళ్ళు ఏంటన్నారంటే, మీ వద్దు, మేము మా ముగ్గురు కలిసి వేసుకుందాము, మనిషి 25,000 అయితే 75,000 మన ముగ్గురు వేసుకొని మనం ఇచ్చేద్దాం, కంగారు పడకన్నా అన్నారు. సరే, అక్కడి నుంచి చాలా ఇండస్ట్రీస్ తిరిగాను, చాలా మంది చేస్తే, సో లాస్ట్ గా ఎన్టీపీసీ వాళ్ళు మా రిలేటివ్స్ పవర్ ప్రాజెక్ట్స్ ఉన్నాయి, వాళ్ళకి ఆయన ఒక 50,000 ఇచ్చారు ఇండస్ట్రీస్ వాళ్ళు. అలాగే మిగతా ఇందులో చెప్పారు కదా మేడం గారు, యూనివర్సిటీకి నేను మేడం గారు వెళ్తే మన వీసీ గారు ఒక 20,000 ఇచ్చారు, అది ఇంకా తీసుకోలేదు. అలాగే మిగతా నాకు క్లోజ్ ఫ్రెండ్స్ ఉంటే వాళ్ళు మనిషి 15,000 ఇచ్చారు, మేడం గారు ఒక 10,000 కలెక్ట్ చేశారు. ఎనీహౌ మొత్తానికి అందరికీ నేను అనుకున్నట్టు $100 పెట్టలేకపోయాను, కానీ అట్లీస్ట్ $25 వరకు పెట్టి వాళ్ళని కొద్దిగా గౌరవించారని నేను అనుకుంటున్నాను. ఒకనాడు తర్వాత మరి ఇలాంటి కాన్ఫరెన్స్ కండక్ట్ చేయాలంటే నా పర్సనల్ ఫీలింగ్ ఏంటంటే, దిస్ ఈజ్ సర్వీస్ టు ద మ్యాథమెటిక్స్ సబ్జెక్ట్. ఇది మ్యాథమెటిక్స్ సబ్జెక్ట్ ఒక సర్వీస్ ఇది అంతే. ఎవరైనా సరే చేయాలంటే చాలా స్ట్రగుల్స్ ఉంటాయి. ఈ కార్యక్రమం సక్సెస్ కావడానికి నాకు చాలా మంది ప్రధానమైన పాత్ర పోషించారు. అంటే నా ఫ్రెండ్స్ ప్రభాకర్, వెంకటేశ్వరరావు, సిఎస్ఆర్, మాకు తెలిసిన కాలేజీలు ఉన్నాయి, అక్కడికి వెళ్ళి నేను డబ్బులు కలెక్ట్ చేస్తాను, నువ్వు రాకని వాళ్ళు తెచ్చిన డబ్బులు అవి, నేను తెచ్చినవి కాదు. ఆ 40,000 వాళ్ళు తెచ్చినవి. ఈ రోజున వాళ్ళకి సన్మానం చేసిన చాలా చిన్నది. అలాగే 1 more బెస్ట్ ఫ్రెండ్ త్యాగరాజు అని, ఆయన ఇంగ్లీష్ లో ప్రొఫెసర్, ఆయన అయితే స్టిల్ ఈజ్ రోమింగ్, అన్ని కాలేజీకి వెళ్ళి మన తమ్ముడు అక్కడ ఆర్గనైజ్ చేస్తున్నాడు ఇంటర్నేషనల్ కాన్ఫరెన్స్, మీరు ఎంతో కొంత ఇవ్వాలని, ఎప్పటికీ ఈ రోజు కూడా స్టిల్ అదే పనిలో ఉన్నాడు అనమాట. అలాగే ఒక మిత్రుడు మధుసూదన్ రావు, ఇంకో మిత్రుడు పుల్లారావు, వీళ్ళందరూ కూడా అసలు నేనంటే ఏమిటి మరి పూర్వజనం నేను చేసుకునే పుణ్యం నాకు తెలియదు, కానీ అయితే వీళ్ళందరూ నేను కాన్ఫరెన్స్ చేస్తాననేసరికి నువ్వు వరి అవ్వట్లేదు, డబ్బులు నేను తెస్తాను అంటున్నారు అన్నమాట. అలాగా మరి మంచితనమో ఏంటో నాకు తెలియదు, వాళ్ళందరూ నాకు చాలా విధాలుగా హెల్ప్ చేశారు. అంతేకాకుండా ఇక పేరున నేను ధన్యవాదాలు చాలా అందరికి కూడా. అలాగే నాకు దుర్గారావు ఏంటంటే, నిజంగా ఆయన నాకు స్టూడెంట్ కాదు, నాకు తమ్ముడు, ఆయన నా కొడుకు లాంటి వాడు అన్నమాట. నిజంగా ఎంత హెల్ప్ చేశాడంటే ఈ కాన్ఫరెన్స్ కి నేను మరవలేను. ఇకపోతే లాస్ట్ అండ్ ఫైనల్ లాస్ట్ బట్ ఏంటంటే, నాకు లీస్ట్ లాగా రామకృష్ణ, రవికుమార్, వీళ్ళిద్దరూ ఎందుకు నువ్వు వరి అవుతా, నువ్వు ఉన్నాం కదా, నీకు ఎందుకు ఏం చేసినా ముగ్గురు కలిపి చేస్తాం కదా, నువ్వేం వరి అవుతావు, నేను గొప్ప. నిజంగా వాళ్ళు ఎంత బూస్టింగ్ ఇచ్చేవారంటే ప్రతిరోజు కూడా. ఆ తర్వాత మాకు డిపార్ట్మెంట్ లో ఏదైనా యాక్టివిటీ వచ్చినప్పుడు నాకు నా సమవయస్కులు కావచ్చు, కానీ పిడిఎన్ శ్రీనివాస్ గారు, అలాగే నానాజీ గారు, వాళ్ళు కూడా నాకు ఎప్పుడు చేదోడు వాదరుగా ఉంటూ, ఒకవేళ ఏదైనా నేను చిన్న తప్పులు చేసిన వాటిని రెక్టిఫై చేసి, ఇలా కాదు అలా చేద్దాం, అలా కాదు ఇలా చేద్దాం అని మంచి సపోర్ట్ ఇచ్చి ఈ కార్యక్రమాన్ని చాలా బాగా సక్సెస్ చేసినందుకు నేను సర్వత్రా వాళ్ళకి
కృతజ్ఞత తెలియజేసుకుంటున్నాను. ఇకపోతే మా గురువు గారి గురించి ఒక్క మాట చెప్తాను నేను. మా గురువు గారి దగ్గర 1992లో నేను జాయిన్ అయినప్పుడు ఆయన స్పీడ్ ప్లస్ స్పీడ్ అయితే హై స్పీడ్ అయిపోద్ది. నేను బాగా స్లో ప్లస్ లో అయితే డెడ్ స్లో అయిపోద్ది. ఆయన హై స్పీడ్, నేను డెడ్ స్లో, కాబట్టి నార్మల్ అయిపోద్ది, న్యూట్రల్. కాబట్టి ఆయన దగ్గర నేను శిష్యర్కం పొందడం అనేది నేను చేసిన పుణ్యం అనుకోను, మా పేరెంట్స్ చేసిన పుణ్యం అనుకుంటాను నేను. నాకు అలాంటి గురువు గారు దొరకడం నిజంగా నేను మరవలేను ఇప్పటికీ కూడా. నాకు జన్మన మా ఫాదర్ మా మదర్ ఇచ్చారేమో కానీ ఆ జన్మకి ఒక సార్థకత ఇచ్చింది ప్రొఫెసర్ కేటీఆర్ శాస్త్రి గారు. ఆయన మీ అందరికీ రీసెర్చ్ సూపర్వైజర్ అని తెలుసు, నాకు రీసెర్చ్ సూపర్వైజర్ కాదు, ఓనామాలు దిద్దినటువంటి గురువు గారు ఆయన. ఆ నుంచి ఈ వరకు ABCD ఆల్ఫబెట్స్ కూడా నేర్పించారు నాకు. మా గురువమ్మ గారు ఎప్పుడు అంటుండేవారు, గొప్ప కోపిస్ట్ ఆయన. దూర్వాస మహాముని గురించి మనం ఎప్పుడు చూడలేదు కానీ చదువుకున్నాము. ఆయనకి ఎంత కోపం ఉండదో మా గురువు గారికి అంతగా డబుల్ ఉండేది కోపం. ఇక్కడ కేకేస్తే ఆ రోడ్డు మీద కనిపించింది అన్నమాట, అంత గసిరేసేవారు. మా మేడం గురువమ్మ గారు అంటుండేవారు, ఎందుకంటే ఆ కుర్రోని అలా గసురుతారు మీరు అంటుండేవారు అన్నమాట. ఆమె కూడా నాకు కృతజ్ఞత తెలియజేసుకుంటున్నాను. తర్వాత అందరూ ప్రొఫెసర్ KKM శర్మ గారు, ప్రొఫెసర్ GVR బాబు గారు, ప్రొఫెసర్ మూర్తి గారు, వీళ్ళందరూ కూడా ప్రతిరోజు వచ్చి ఏదో కాన్ఫరెన్స్ పెట్టి శ్రీనివాసరావు నన్ను చాలా ఎంకరేజ్ చేసేవారు. అసలు నిజానికి మాట్లాడాలంటే ఈ రోజున కాన్ఫరెన్స్ ఆన్ ప్యూర్ అప్లైడ్ అండ్ ఇంజనీరింగ్ మ్యాథమెటికల్ సైన్సెస్ అని పెట్టింది ప్రొఫెసర్ రవీంద్రనాథ్ బాబు గారు ఆ పేరు పెట్టింది, నేనైతే కాదు. ఆయన నాకు ప్రతిరోజు కూడా శ్రీనివాసరావు అలా ఇది బాగుంటుంది, ఇది బాగోలేదు. నేను వెంటనే KPR శాస్త్రి గారితో తీసుకెళ్ళాను. సార్ ఇలా పెట్టారు మాస్టర్, ఎస్ గుడ్, గో హెడ్ అంటుండేవారు. తర్వాత మరి అన్నిటికన్నా నాకేంటంటే పెద్ద వజ్రాయుధం లాగా ఏంటంటే గాంధీ నా దగ్గర ఉన్నట్టు మా చెల్లి అనురాధ కామేశ్వరి నాతో ఉంది కాబట్టి నాకు ఈ డిపార్ట్మెంట్ లో ఇంకా ఎట్లాంటి కార్యక్రమమైనా, ఎంత బరువు కార్యక్రమైనా అది బాధ్యతగా ఫీల్ అవుతాను కానీ భారంగా ఫీల్ అవ్వను మేము, అది విషయం. సో నౌ చాలా సమయం అయిపోయింది కాబట్టి అందరికీ పేరు పేరున ఒకసారి ధన్యవాదాలు తెలియజేస్తున్నాను. నాకు అందరూ కూడా ఎంతో కొంత ఏదో ఒక రకంగా చాలా హెల్ప్ చేశారు. అసలు వెంకటేశ్వర్లు అయితే మా ఇద్దరం నాకన్నా కొద్దిగా వయసులో పెద్దవాయన ఎంత ఫ్రెండ్లీగా ఉండి, శ్రీనివాసరావు నువ్వు ఆల్రౌండర్, ప్రతి దానిలో ఉంటావు, నువ్వు గో హెడ్, నువ్వు చేయగలవు అని ఆయన నాకు చాలా ఎంకరేజ్మెంట్ ఇస్తూ ఉండేవారు. వెంకటేశ్వరుడు, నేను వెంకటేశ్వర్లు అని పిలను, కేలు అని పిలుస్తాను, కేవీలు అని పిలుస్తుంటాను, ఓకేనా. అప్పుడు ఇంజనీరింగ్ క్యాంపస్ లో కనిపిస్తే నువ్వు చేస్తావు, నువ్వు చేయగలవు అంటుండి నన్ను చాలా అన్ని విధాలుగా ప్రోత్సాహం చేయించారు. ఇక నానాజీ గారు ప్లస్ మా రవీంద్రనాథ్ బాబు గారు, PDN గారు, అంటే ప్రొఫెసర్ KKM శర్మ గారు మా గురువు గారు. ఆయన ఇంకా నేను గురించి ఏం చెప్పలేను ఇంకా. సో అంచేత నౌ ఐఎమ్ గోయింగ్ టు రీడ్ ద ఓట్ ఆఫ్ థ్యాంక్స్ విత్ బ్రీఫ్ మేనర్. Good evening, one and all. It is a great privilege to propose a vote of thanks at the end of enlightening and informative sessions carried during the conference. Honorable Vice Chancellor of Andhra University, Professor PVGD Prasad Reddy Garu, respected Chief Guest Professor GVR Babu Garu, Honorary Professors, Department of Mathematics, AU, respected Guest of Honor Professor Avadhani Garu, Professor retired Professor AU and Professor M.S. Murthy Garu, President of Valedictory Function Professor P. Anuradha Kameswari, and also Director of Conference. Our beloved Guru Garu Professor KPR Shastri Garu, Chairman of USMS and President of SMS, and retired Professor, Department of Mathematics, Andhra University, Professor KKM Sharma Garu, President of USM and Honorary Professor of Department of Mathematics, AU, and other executive members of USMS and SMS. I extend my heartfelt gratitude to you all for gracing this occasion. We would like to express our sincere gratitude to Professor GVR Babu Garu for his valuable insights on this conference. We want to express deep gratitude to Professor Avadhani Garu for his valuable perception on this conference. We would like to express our deep thanks to Professor KPR Shastri Garu for his unwavering support in every stage for the smooth extension of these events. We'd like to express our sincere thanks to P. Anuradha Kameswari Garu for her tireless support and encouragement.
Your contributions have been instrumented in making this event a grand success. I wholeheartedly thank to all the resource persons and keynote speakers whose enlightening discussion on various mathematical problems and applications have enriched our understanding. I want to extend profound gratitude to the advisory board, organizing committee, volunteers, students, research scholars whose tireless efforts behind the success and mode of the smooth execution of the conference. I sincerely thank to our department for providing necessary facilities to conduct the event of the conference. We express our gratitude, our sponsors and partners for their gracious support. We want to thank all the participants and delighted for their active participation and encouragement throughout the conference. I also express my special thanks to all the retired professors, Professor K.L.N. Swami Garu, Professor G.C. Rao Garu, Professor N.V.S. Murthy Garu for attending the conference, and I sincere thanks to all the professors who chaired the sessions for technical and paper presentations. Last but not least, I am very happy to express my thanks to our technical arrangement teams, media, press, photographers for their support. My special thanks to my scholars, Tharani, Durga Prasad, and Tejaswani Madhubala. My sincere thanks to Vice Chancellor since Vice Chancellor, Science College Principal, Registrar, and other high officials for their invaluable support and encouragement. Thank you, one and all, for being a part of this incredible journey. A big thanks to everyone. I'm also thankful for the non-teaching staff for their continuously supporting for success this conference. Thank you to one and all. Now, this function closes with the national anthem. ఎవరినైనా మర్చిపోయి ఉంటే కొద్దిగా క్షమిస్తారని మరొకసారి అందరినీ వేడుకుంటున్నాను.
ఎందరో మహానుభావులు
జనగణ మన అధినాయక జయ హే భారత భాగ్య విధాత